Hello everyone and welcome to this amazing session on Artificial Intelligence by Intellipaat. Artificial intelligence has taken the world by storm. The applications of artificial intelligence are limitless and large conglomerates like Google, Meta and Microsoft are betting hugely on the future of AI. One such very recent example is ChatGPT, a conversation language model that responds to you like you're having a conversation with another human being and can answer almost all of your queries. Even the largest search engines like Bing and Google are integrating such language processing models to give better search results to people. In times like these, being a skilled artificial intelligence professional will not just be beneficial but put you miles ahead of other candidates who are also planning to move to the AI domain. Gartner also tells us that customer satisfaction is expected to grow by 25% in 2023 in organizations that use AI. Now, if you are thinking AI will replace my job, then here are some statistics for you. According to Forbes, AI technology is expected to create 12 million more jobs than it's expected to replace. AI jobs are anticipated to be in high demand with 97 million specialists needed in the AI industry by 2025. Not only this, the market is expected to hit $1,597.1 billion by 2030 with a registered CAGR of 38.1% from 2022 to 2030. These stats themselves prove that the time to learn the skills for artificial intelligence is just about now. No matter what field of work you're in, having AI skills and being well versed with all the concepts will definitely bulletproof your career and its future. So sit tight and stay with us till the end of this session as we will take you through a very informational and learning journey of artificial intelligence. Learn through a series of hands-on, extremely crucial quizzes and in-depth explanations of all the core and complex concepts. Let us now jump on the agenda for this session, but before that, make sure you subscribe to our YouTube channel and hit the bell icon for regular updates. First, we'll begin with Introduction to Artificial Intelligence. Then we'll talk about Convolution Neural Networks. Then we'll look at Keras Sequential Model. Then Keras Sequential Model Hands-On. Then we'll talk about Keras Functional Model and Keras Functional Model Hands-On. Then we'll look into Convolutional Layer. Then we'll talk about pooling layer, and then we'll look at RNN Hands-On, and then we'll talk about understanding different recurrent neural networks. Then we'll look at types of RNN and issues with RNN, and we'll look at RNN Hands-On. Last but not the least, we'll look into interview questions for artificial intelligence. And with that, let us begin the first topic.
Artificial intelligence has revolutionized the way people think, learn and work in various fields from finance to healthcare and mobile apps. What's more interesting is that AI plays more of a role in our daily lives than we can imagine. From Siri and OK Google to various virtual player games and social media apps, AI is everywhere. It sure is the most happening topic in every business right now. It is the most wanted and exciting career domain right now in the market. Artificial intelligence or AI uses intelligent machines that build in a way that they react like humans. The primary process involved in making these smart machines is to carry out decision making, which analyzes and uses data available in an enterprise. It is similar to the human mind absorbing and synthesizing information and providing the required decision. So how does an AI work? AI systems work by investigating large amounts of data labeled training data, analyzing the data for correlations and patterns, and using these patterns to make predictions about future states. In this way, a chatbot that is fed examples of text chats can learn to produce lifelike exchanges with people, or an image recognition tool can learn to identify and describe objects in images by reviewing millions of examples. AI programming focuses on three cognitive skills: learning, reasoning, and self-correction. Learning processes. This aspect of AI programming focuses on acquiring data and creating rules for how to turn the data into actionable information. Reasoning processes. In this aspect of AI programming focuses on choosing the right algorithm to reach a desired outcome. In self-correction processes, AI programming is designed to continually fine-tune algorithms and ensure they provide the most accurate results possible. So there are four types of artificial intelligence. First, we have reactive machines. These AI systems have no memory and are task specific. An example is Deep Blue, the IBM chess program that beat Garry Kasparov in 1990s. Then we have limited memory. These AI systems have memory so that they can use past experiences to inform future decisions. Some of the decision-making functions in self-driving cars are designed this way. Theory of mind is the third thing. It means that the system would have the social intelligence to understand emotions. And finally, we have self-awareness. In this, AI systems have a sense of self which gives them consciousness. Now let's see what are the applications of AI. One of the best known healthcare technologies is IBM Watson. It understands natural language and can respond to questions asked for it. AI can automate grading, giving educators more time. It can assess students and adapt to their needs, helping them to work at their own pace. AI tutors can provide additional support to students, ensuring they stay on track. Banks are successfully employing chatbots to make their customers aware of services and offerings and to handle transactions that don't require human intervention. AI technologies are used in transportation to manage traffic, predict flight delays, and make ocean shipping safer and more efficient.
In this particular case, the examples that we have seen, right? If you focus, the images that we have taken were of the size, let's say 32 cross 32 pixels, 28 cross 28 pixels, right? These are very small sized images that we are feeding into an ANN model, right? But in reality, what happens is, in reality, you are going to be passing, let's say, an image which will have a very high resolution, right? So the number of pixels will be going into thousands, right? Maybe millions, right? So in that case, you can just imagine that how many features will be there in the input layer of the neural network. If let's say I imagine a normal image, a normal high quality image, there itself, I think there will be close to 100k pixels that will be there, right? So 100k into 100k pixels, if you're talking about, that will come to how many features? I think close to 10 million features, right? So 10 million features as an input. So you can just understand that how many parameters will be required to tune such an ANN, right? So hence it is not, an ANN will never be the model of choice for you when you're dealing with image data. For examples, we have gone ahead and we have seen image data which was not very high, like which did not contain a very huge amounts of pixels. But in actuality, in reality, you will almost always be going towards the CNN. Okay, so that's where the need for CNN was. Okay, so that's what we'll be looking at today, and then we'll see how a CNN is created, right? So disadvantages of a fully connected network. By a fully connected network, we mean what? We mean a dense neural network that we have been studying in the past 2 weeks, right? Then what is CNN? Different layers in CNN. Build a model with CNN using Keras, right? So this is the agenda for next week, I think till the middle of next week maybe, and we will be completing all these topics. Okay, now let us understand how our computer reads the images that we provide to it, right? So now first thing, I think this is clear to us, I will go through this, but if you see, a computer is not looking at the image, right? A computer is just looking at the different number of pixel values that you have for that image, right? Now if first of all, let's talk about how colored images are created, right? Colored images are actually created. You have three, okay. So you will have three panels, right? So let's say that this is your first one. Let me clear this. You'll have three matrices which will be very similar to this, right? So let's say the first matrix is this, the red one. Okay. Similar to that, there will be a green matrix. RGB, right? If you remember RGB, similar to that, there will be a green matrix which will have some numbers, and similar to that, there will be a blue matrix which will have some numbers, right? So there will be three panels that will be there. Now, all these matrices will be superimposed on top of each other to give you a colored image, right? Because if you remember the basics of physics, right? These three colors, that is red, green, and blue, these three colors combined can create all the rest of the colors that are there in the picture, right? So essentially, a colored image is nothing but three input matrices, each and every matrices corresponding to each and every giving the pixel value for that particular color, be it red, green, or blue, right? So whenever we are reading a colored image, the size of the colored image actually becomes three times as compared to a black and white image. A black and white image can just be like displayed by one particular matrix, right? There will not be three separate matrices required to represent a black and white or a grayscale image, right? So the initial difference over here is that, first of all, when you are dealing with colored image data, the size of the image automatically increases to three-folds, right? And that again increases the complexity of the neural network even further, right? This is how actually colored images are created. Okay, so now we also know that the image that a computer is seeing is actually not the image, but it it is a matrix which contains the pixel values for each and every block, right? For each and every cell, there will be a unique pixel value that will be uh, uh, linked to that particular cell, right? Now, if I look at this particular image, this again can be converted as, for a computer will be looking at three matrices each for red, green, and blue colors, which will have different pixel values, right? Now, to create green over here, maybe the red matrix has a value of something in the range of 0 to 265 on the top left block. Similar to that, the blue value will have some other value and the green value will have some other value, and that all those all combined will give you the final green color that you're looking at over here, right? That is how your colored image will be created, right? So when a computer sees an image, it will see a matrix of pixel values, right? So there will be different pixel values depending upon the resolution and size of the image. It will see a 32 cross 32 into 3 array of numbers, right? Now you see why we have multiplied this by 3, because depending upon the pixel. So let's say that for this image the pixels are 32 cross 32, right? Then because this is a colored image, this becomes 32 cross 32 cross 3, right? So that is how a computer will see. Each of these number is given a value from 0 to 255, same thing that we have been seeing till now, which describes the pixel value for that particular point. Okay, these numbers are then only inputs available to the computer, right? So to the computer, this image is never visible. To the computer, it is all a pattern of mathematical numbers, right? These are just mathematical numbers that we are talking about, and that is what is visible to a computer.
Let's have a quick quiz question, guys. And the question is, which of the following is a branch of AI? And your options are machine learning, cyber forensics, full stack development, or none of the above. Please mention your answers in the comment section below.
Okay, now the problem with a fully connected network, right? Again, same thing. If you see, if let's say I go ahead with an image size of 28 cross 28 cross 3, okay, what will happen is that yes, I can probably go ahead. It will be 784 multiplied by 3 features, somewhere around 2300, right? 2340, 2352 neurons will be there in the first layer, right? Now these 23, 42 neurons, 52 neurons, whatever are there, will be connected to the subsequent layers, whatever you have defined, right? So at the end of the day, you will have almost, let's say, 500,000 parameters to clear. Okay, so this looks like a decent size, and this is what we have worked with when we were working with a previous case. Okay, a single fully connected neuron in the first hidden layer of a regular in a typical neural network would have 2352 weights. Okay. Now these are the number of weights which can be tuned by a simple traditional neural network. Okay. Now let's say we have an image of 200 cross 200. Okay. Number of parameters, number of weights at the first layer will be how many? 120k. Just by increasing the size from 28 cross 28 to 200k, you can see that the total number of weights that need to be tuned only from the input layer to the first layer will be 120k, right? Now this becomes challenging. Okay. Now if I take this even further, right? Also we will have several such layers of neurons leading to several parameters, right? So this is just your input layer to the first layer. After that, from the first layer, there will be hidden layer number 2, hidden layer number 3, whatever you have defined, and then there will be the final output layer. So you can assume that the number of parameters will obviously be very, very high, right? ANN models can always be used when you are working with structured data, right? Structured data, you don't think of structured data having millions of features, right? But when you're dealing with image data, and when you're dealing with image data which is high resolution image data, right? Then we go ahead and we use CNNs. And CNNs are actually, you'll see in some time that CNNs are nothing but ANNs only with some transformations which are applied on the image data, right? We apply some kinds of transformations on the image data, and then finally it is connected to an ANN model only, right? So first we'll see what is the need of a CNN model, then we'll actually see what actually happens in an ANN model. But whenever you are working with structured data, right? Structured data as in if I look at customer data, I look at transactional data and all, in those cases, ANN is almost always way more capable than what is required, what is thrown at it. But looking at image data, you can very clearly understand that image data actually, see, each and every pixel represents a feature over here, right? Each and every pixel is a feature. So if your image resolution is 1024 into 1024, you have somewhere around 100k features, and these features will be leading to weights, will be leading to parameters being tuned, right? So it becomes very, very complicated for the neural network to process all these features at once. Whereas if I compare this to structured data, in structured data you will never have 1 million features, right? You can at max have 1000 features, 2000 features, 5000 features. With text data, let's say you can have 100k features, right? But not more than that. So that is why whenever you're dealing with image data, and nowadays you can see that the resolution of the images is not going down, it is going up only. With the launch of each and every new phone each and every year, the resolution of images are going up, and the CNN models that we are talking about, or the ANN models that we're talking about, will actually be working on the real world data, right? So you can just imagine the number of features that will be required, the number of features that will be created from an image coming out from a mobile phone, right? If let's say you upload a photo on Facebook, right? Now that photo again will be high, like the number of pixels will be very high in that particular photo, right? Now on your phone, your Facebook, let's say, has deployed a deep learning model on the cloud, right? But still, if you are sending millions of features to the deep learning model to train, it will not be able to give you predictions then and there. Whenever you tag a photo, you are within a second you are able to see the suggestions for the people who might be tagged, or who might need to get tagged in that particular photo, right? So that's the main problem. The problem is of size of data, and that is why there was a need to create a new methodology, a slightly changed methodology, which goes by the name of CNN. Okay.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Three means that we have three arrays, right? First, if I look at if I split this 32 into 32, right? Now if I give you an example, the same example. So let's say this 32 cross 32 cross 32 can be written something like this. Let's first take the red block. Okay, so this can be the first 32 cross 32 matrix. Okay, okay, this can be the first 32 cross 32 matrix. Then again you will have the second matrix which will be corresponding to green, right? Because to show a colored image you will need three matrices, red, green and blue, right? This again will be the next 32 cross 32 matrix. Okay, right? And then finally you will have blue as well, red, RGB, and this matrix again will be of the size 32 cross 32, right? This again will be of the size 32 cross 32. Okay, now this is the same thing that you are trying to read over here, right? This 32 into 32 into 3. So you can imagine that this red matrix that you are seeing is of the size 32 cross 32 pixels. That corresponds to 1, right? Then the second one, 32 cross 32, the second block corresponds to the green box, and the third one corresponds to the blue box, right? Now, all this combined, if you look at it mathematically, what is it? These are just three matrices of the size 32 cross 32. Hence, you will represent this as 32 cross 32 cross 3. Array size will be that. Okay. 3D images, once again, there will be another stack, there will be another dimension that will be added on top, right? So 32 cross 32 cross 3 will be just your colored image. But a 3D image in itself, it contains one more dimension, right? So effectively, for the computer, it will become a 4D image, not 4D, but if it is a colored image, which is 3D, right? So, okay, a colored 2D image will be represented in a computer by, let's say, if the size is 32 cross 32, you will represent it as 32 cross 32 cross 3, right? So, similar to that, a colored 3D image will also have a third dimension, right? Now, let's say the third dimension again is of the size 16. So, then in that case, it will be 16 cross 32 cross 32 cross 3. Yes. Okay, so again, you can see that the complexity will increase drastically. But uh, you can, working with CNNs, you can actually get your data in form of image, 3D images, and even you can have video processing as well, right? So video data, you can imagine what is video data. Video is actually multiple images that are stacked at one, as one, right? So one video might contain thousands of images, right? But we have CNN models which are actually able to classify videos as well. The subtitles and all that are being created in videos nowadays. YouTube, if you see YouTube generates subtitles by default, right? All this is being done by a deep learning model only. Okay. Okay. So now what we are trying to establish is we are trying to establish the need for a convolutional layer method, right? So over here again, when we move with when we process an image with of the size of 200 cross 200 pixels, a colored image, so that will once again be multiplied by 3. So you can imagine that there will be 120K parameters that will be required only to tune the connections between the input layer and the hidden layer number one, right? Then from there on, there will be some more weights that will be required, that will require tuning, right? Okay. So now we have established the need for a CNN, right? I hope this need is clear to each and every one of you, that why are we working with CNNs? Why ANNs will not be able to work with huge image data, or let's say high res image data. We can calculate a winner, right? So that's why, uh, in order to train a neural network, we are supposed to calculate the weights. But yes, when we are working with image data, in case of an ANN, again, it's not that we can't calculate the weights over here. It's just that the amount or the number of weights will be so high that your ANN will take probably months to train itself, right? If you're training, let's say, 1 million parameters, and 1 million, I'm saying, which is just a decent amount, it will be more than that. It will be billions of parameters, right? If you give a normal sized image to a ANN model, it will require billions of parameters to train that ANN, right? So it's not that it is impossible, but the problem is that the amount of computing speed that will be required will actually take months for that particular model to train. Okay, so that is why we need a model which is actually faster and which can process high resolution images in a more convenient way. Okay. Okay, so now let us understand what CNN is and how it helps to overcome this problem. Okay, we see a lot of things. Okay, but let's say that during night time you're on the road and there are multiple cars that are on the road, right? Now, looking at the, it's not, it might not be the case that you are able to see a particular car fully because the lights might be turned on. You might not be able to see what brand the car it is, which brand the car belongs to, and so on and so forth. But still, you are able to decipher. At times, you are able to decipher that okay, this is a Fortuner, this is let's say sedan, and so on and so forth. Right? You are able to do that, even though the image that you are seeing is not a very clear image. Right? It is just giving you maybe 10% knowledge about that image because you are not able to see the color, maybe you are not able to see the brand, maybe you are not able to see the specifics of the car, but still you are able to classify that okay, this is an SUV, and at times you are also able to classify what exact car is that, right? Now, similar to that, let's say at night there is a dog coming towards you. You will know that it's a dog. You will not think that it's a lion, right? Because you are what you are doing is that you are actually focusing on the different features that you are able to extract. Now, when you look at a dog coming at you in the dark, what do you look at? You look at the outline of that particular whatever is coming at you. And looking at the outline of that particular figure, you are able to make sense that, okay, this looks like a dog. Am I correct? Right? So what that implies is that there can be specific features that you can extract from an image, which might help you in classifying that image. You might not even require all the image data, right? So that is one point on which convolutional neural networks are based on, right? That is just one point. What the point being that convolutional neural networks actually they extract different features from the images, right? So now these features can be the outline of that particular image, right? The shape of that particular image, okay, so on and so forth. So there will be many things like this, many transformations like this, which a convolutional neural network will do. Now, what this will do is that this will also help us in reducing the size of the image, right? And this will also help us in identifying what in classifying that particular image to the correct. Okay, so did that uh, where CNN model is used? Okay, I'll tell you that. First of all, did that point make sense? The one that I was talking about. Uh, can we process image even if all the uh, relevant things are not available in that image? At times we can, right? At times you are able to classify. It's not that you will not be able to classify, right? You will be able to make out who your family members are by just looking at the back of them. Maybe they are walking on the road or they are amongst the mob. But at times you are able to make out that okay, this is my mother, this is my father, my sister, my wife, and so on and so forth, right? You are able to do that. You are not able to view the entire image. You are not able to view the entire person. Maybe you are viewing that person in the dark, but still you are able to, at times you're able to make sense of it, right? So that's what we actually apply in a CNN model, right? In CNN model, we get rid of all the features or all the parts of an image which are actually, which will help us in identifying that image, but which are actually making the size of the image too huge. Okay, so I'll come to that, but the gist was that a CNN is nothing but a CNN takes an image, transforms it, tries to extract multiple features out of those out of that particular image, the features which might be relevant for you in order to predict the target variable, whatever target variable there is, right? And then it will not maybe focus on the rest of the features, and then it will go ahead and classify, right? Now, if I give you a simple ask, I don't want you to predict the I just want you to predict what type of the car is going on the road, whether it is an SUV, whether it is a sedan, or whether it is a hatchback, right? Now, my question to you is, do you need the entire colored image to do that? Or you can just extract the silhouette of that image, or the outlines of a particular car, and will you be able to classify whether it's a hatchback SUV or a sedan? You don't require the entire image, right? You can just extract the required feature. Okay, now let's assume I ask you to classify the color of a car, nothing else. Now, in this particular case, all you need, you don't need to extract any feature, any outline or something. You just need to understand what color it is, right? For that, you will be focusing on specific pixel intensities, right? And those pixel intensities will be correlated to the different colors that you have. Okay. Now, what you are seeing over here is that for each and every different problem statement, there will be different features that might be required in order to predict. Okay, and that is what a convolutional neural network will do. It will list out all the features that are there, all the features that you can create. I will tell you how we create these features, right? After listing out these features, it will see what are the features which are actually helping you to predict the target variable, right? Now, target variable being car, whether what type of a car is, what color of the car is, and so on and so forth. And then on that basis, it will only give a higher weightage, or it will only focus on those features which are actually helping you to predict. Okay, so that is the main goal, or that is the main framework through which CNNs actually work. Okay, there are multiple good examples that are there. Video games, if I take the example of video games, right? So you would have seen consoles like PS4, Kinect, and all, right? Now, all these games that you are seeing, wherein the users' gestures are replicated onto the screen, right? Let's say that you are standing and you are playing a game of tennis. Now, you will, wherever you are standing, you will assume, you will imagine that you are serving a tennis ball, right? And the similar output will be visible on the screen. Whatever movements you are doing at in front of the tree, in front of the screen, that will be captured on the video game directly, right? How is that happening? That is happening through a CNN model, right? Your image data is being fed into the model. As soon as the image data is being fed into the model, so see, what is happening is that multiple images are being captured at a given point of time, because you are playing a video game and you are constantly moving, right? At each and every nanosecond, right? As and when your posture is changing, right? Let's say that you are in the position to serve. So what will happen is that that particular device will capture your image within a couple, like within nanoseconds, not even a second. It will predict that, okay, this is your angle and this is the kind of position you are in. Now, corresponding to that position, there will be a particular power that will be generated to the serve, right? Or there will be a particular location on which the serve will land. right? And combining the outputs from multiple images that you have generated within a span of a second, right? The model, the CNN model that is deployed in that console will be able to give the video game some specifics that, okay, this serve will go at a speed of, let's say, 100 kilometers per hour, because that's how the person who's trying to serve, his hand is, let's say, at a 60-degree angle, and the hand motion was, let's say, at 5 kilometers per hour, and so on and so forth. So all these things will be detected through that 1 or 2 seconds of motion of yours. And accordingly, whatever are the action that the particular video game needs to do, right? So let's say that the action is that you have to serve. So you will see on the screen then and there that the ball actually goes there towards the next side of the net, and then the computer in front of you or the person in front of you will hit that same process, will go on again and again, right? But you can imagine that how many images are being fed into the CNN model in such a quick amount of time, right? So for that, the processing should be faster, right? So we have one example, that is video games, medical results, right? So image data is used to detect, let's say, cancer detection. If I talk about cancer detection, right? So your X-ray data, all your X-ray data. So previously, I think when deep learning models were not there, all the data that is being going through would have to go through a doctor, or would have to go through a specialist who will look at that particular image and say whether you have a particular disease or not, right? But right now we are in an age wherein what will happen is that wherein you just need to feed in your X-ray data to a particular model, and within seconds, right? So there are apps, what they ask you is that you upload your reports, and just by looking at your report it will tell you whether you have a specific disease or not, right? How is that happening? That is happening because these models are being trained on millions of images data of similar, let's say, reports, right? Let's say that you're looking at X-ray results corresponding to whether a patient has cancer or not. So this CNN model would have been trained on millions of images of patients having cancer or not. And this again, this X-ray data is what is nothing but all pixels to a computer, right? So now on that basis, the app will be able to predict within seconds whether you have cancer or not, or what type of cancer you might have, right? So all these things are applications. Now, face detection and all, right? So you have seen there are companies which are installing cameras wherein if you are an employee, you will be able to walk in right away, right? You don't need to swipe, you don't need to have a card. Now, what is that? That is facial detection. All that happens because we have deep learning models, and there is at some point of time there is a CNN that will be involved, which will be predicting that, okay, this employee, I have the photo of this particular employee on my database. This is matching, so I can let this person know. Okay. Okay. So CNNs are nothing but CNNs are like your dense neural networks only that we have studied before, and are made up of neurons with weights that can be learned, right? So weights and bias values which can be learned. Each neuron receives several inputs, takes a weighted sum of them, and passes it through an activation function and responds with an output, right? So this is nothing else, right? A CNN is nothing else but an ANN with some added layers, right? So in case of an ANN, we were working with just dense layers, right? In case of a CNN, there will be some other layers that we'll have to add in order to process the image data, right? The whole network has a loss function, and all tips and tricks that we develop for networks still apply on CNN, right? So good news is that whatever you have learned in the previous 2 weeks, for ANNs, right? All that is applicable in a CNN as well, right? So that was why I was saying that you should be very, very crisp and clear on how an ANN actually works, because all those learnings will be applicable here, right? It's not that. So a CNN is image, some kind of image processing plus an ANN, right? So that some kind of image processing is something that we are looking at, we'll be studying, and the ANN we know how an ANN works. So as soon as we are able to process the image, we will directly go ahead and connect that with an ANN model. Okay. A convnet is sometimes I can call a CNN as a ConNet, right? So don't get worried. It is a convolutional neural network model only. A ConNet perceives images as volumes, that is three-dimensional objects, rather than as flat canvases to be measured only by width and height, right? So this is image data. It will be three-dimensional because if let's say that it is a colored image, there will be a third dimension that will be equal to 3 that will be added, right? So then how are convolutional neural networks different from neural networks, right? So now we will see how are convolutional neural networks actually different from the typical neural networks that we have. Okay. Now, convolutional, let's try to understand the definition of what convolution means. Convolution, to convolve, means to roll together, right? From mathematical perspective, a convolution is the integral measuring of how much two functions overlap as one passes over the other. Think of convolution as a way of mixing two functions by multiplying them. Okay, so convolution is nothing but convolving two functions or convolving two images into one and then seeing how similar they are, right? And that is what we do in the convolution part, wherein we apply different filters, right? And we will see that on application of that filter, how similar the image, that part of the image where the filter is being applied is to that filter, right? Now let's say I have a filter which detects the edge of a particular image, right? Now this filter I'm going to apply to my input image, and I'm going to see what is the resemblance of this filter with my image, so that I can extract whatever relevant features are there for me to extract, right? So that is what actually convolution does. I'll talk in detail about this a lot more, so don't get worried about the maths behind this, right? I'll tell you how exactly what exactly happens when we are talking about the different layers. Okay, now let's look at this, right? So if I tell you how a convolutional neural network works, right? So there will be multiple layers that I will have to apply. So ConVnet pass many filters over a single image, each one picking up a different signal, right? At a fairly initial layer, you could imagine them as passing a horizontal line filter, a vertical line filter, and a diagonal line filter to create a map of the edges in the image. I'll talk about these. CNNs take those filters, slice of the image feature space, and map them one by one. That is, they create a map of each place wherever feature occurs. By learning different portions of a feature space, convolutional nets allow for easily scalable and robust feature engineering. Okay, now the same points which I have told you, but we'll focus over here, right? If you, let's say the input data is the data of a car. Okay, now if you look at this is the image of a car. Final output is what? Final classification is whether it is a car, truck, airplane, ship, or horse, right? This is what we have to predict. Now what happens is that we will apply multiple layers. We will apply multiple layers of convolution. ReLU layer, this is a function that we always apply after we have applied this particular layer. So convolutional layer is always followed by a function, which is this particular function, ReLU, right? Now, once again, we apply convolution, ReLU, and then there is something known as pooling. I will talk about each and every layer in detail, but over here, I'm just showing you how a convolutional neural network actually looks like, right? Then let's say I apply a pooling layer. Then again, once again, I apply convolution. I apply ReLU, convolution, ReLU, pool, say so on and so forth. And finally, I'm able to predict, right? Now, what this convolution, ReLU, pool, what is this doing? All these layers are only doing one job. That is, they are extracting different features, different features, and they're combining those features together from the input image, right? And by extracting these millions of such features, right, might be possible that all the million features might not help me in predicting whether it is a car, truck, or airplane, but there might be some 1,000 or 10,000 features which might help me, right? So let's say that while we are extracting the features, there will also be one feature which will be the silhouette of the car, right? Now this silhouette of the car that is coming from this will match from the silhouette of the cars that we have given to this model while training, right? And because while training for this particular silhouette, the model had classified that this particular silhouette always corresponds to a car. It will give a very high probability to a car, right? So that is what it actually does. I'll talk about each and every layer, what is convolution, ReLU, pooling and all, right? But over here, I'm just showing you the architecture of a convolutional neural network model. That is how a convolutional neural network model looks like, right? So if I explain you a convolutional neural network model, right? So what will happen is that okay, so let's say I have my input data, okay, input image, okay. This input image will be, if I talk about the different layers that I will have, okay, my input image will be connected to, let's say, a convolution layer, conv layer, okay. This will be connected to a ReLU layer. Let's again, this is connected to a max pooling layer. I will talk about each of these layers, so don't worry about that. I'm just talking about the architecture here, right? Now this max pool layer, again, let's say one more convolution layer is there. Convolution. Then again a ReLU. Then again a max pool, right? Let's say after doing all these steps, I was able to extract all the required features, whatever I required, right? Now I will connect this with the dense layer, right? Now I will flatten my data. I will talk about each and every things, and the flattened data will then be connected to the typical ANN, the ANN layers that we had. Now, basically this part, the flattened output, right? This becomes the input data to the ANN, okay? This becomes the input data to the ANN, and you know how once when you have your data in a format which can be consumed by ANN, after that you know what an ANN will do, right? What will it do? It will define the different layers, right? So ANN, let's say I have hidden layer 1, okay, then I have hidden layer 2, and then I have my target, right? So this is how actually a convolutional neural network model will look like. Now, if you see from here till here, all this part is something that you have. Okay, so more about CNNs, right? A simple coordinate is a sequence of layers, and every layer of a coordinate transforms one volume of activations to another through a differentiable function. There are four layered concepts we should understand in a convolutional neural network, right? So there are four different kinds of layers which we will have in a convolutional neural network. One will be convolution, ReLU, pooling, and full connectedness. That is your ANN layer, right? Now, ANN layer, you are very clear about. ANN, we have what? We had a dense layer, so that will be one layer that we know about. These are the three new layers that we will be studying here: convolution, ReLU, and pooling. Okay. Okay. Before going deep into this concept, let's see an example, right? So let us take this example. So use case number 1, right? In this simple example, we will determine whether the image is of an X or of an O or an X, right? So let's say that the input image is this, right? You can see the pixels, right? Now, the black pixels, you can consider them as closer to values closer to 0, okay? And the white pixels, you can consider them as values closer to 255, okay? Now, if the input image is something like this, your output should be X. If your input image is something like this, your output should be O, right? This is our use case. Now, if you look at it, on the left hand side, this part is the target, right? This is the perfect output or input that you will expect, right? This one. But in reality, you will not get this, right? In reality, you will get different inputs. So the different people will write in a different way. Okay. Now your actual images that might be flowing into the model will be something like this. For X, you will have these images. Okay. You will have this kind of image. You can see for each and every X, the first X is almost very similar to the image that we are seeing on the left box. The second X is similar, but you can see that it is much more dense. The third X is also similar, but you can see that it is positioned on the top left corner. The fourth X is also similar, but you can see that it is tilted in a particular direction, right? So, but from a convolutional neural network model, you cannot expect. If let's say I'm creating a convolutional neural network model which detects a cat or a dog. Okay. Now, if my dog is sitting, if my dog is standing, if my dog is running, I will expect my convolutional neural network model to predict each and every time wherever in the frame my dog might be at, whether the dog is, let's say, the main part of the image or it is at the background of the image. I will expect my CNN model to predict that it is a dog, right? Now, similar to that, there can be multiple ways through which a person can write X. Okay. So I will expect my CNN model to classify all these cases correctly, right? Similar to that, you can see that for O as well, there are different ways through which people have written O, right? Some have written it in a dense manner, some have written it at the bottom of the image and so on and so forth, right? But you expect your CNN model to predict all these things accurately, right? Now, here there are multiple renditions of X's and O's. This makes it tricky for a computer to recognize them. But the goal is that if the input signal looks like images it has seen before, the image reference signal will be mixed into or convolved with the input signal. The resulting output signal is then passed on to the next layer, right? So we'll see what is happening here. Okay. Now let's say over here, if we look at this, right? So a naive approach to solve this problem is to save images of X and O and compare. Okay, so one thing, how we can solve such a problem is that one thing can be that I can compare each and every image that is coming in. Let's say this image, this image, this image with the saved image of X and O that I have, right? But will this approach help us? I have one image, or let's say I have some images saved of X and O. Every time I get an input, I will compare the input with the saved image and I will see whether it is matching. Let's say I have the image of X and O with me, right? I want my model to classify whether it is an X or an O, right? Each and every time an input image comes for which I have to classify whether it belongs to an X or an O, I compare that image with the images of X and O that are pre-saved. Okay. And then if the image matches my X or O that are saved with me, I will go ahead and say, if the image matches an X, I will say it is an X. If the image matches with O, I will say it's an O. If the image does not match with both the images, I will say it does not match with both of them. But does this look like a good approach to you? Now let's take this example. Okay. A naive approach to solve this problem is to save images of X and O and compare every new image with our examples to check which is a better match. To a computer, an image looks like a two-dimensional matrix of pixels with a number in each position, right? So this is what it will look like to a computer, right? All the black pixels will be at will have a number of -1. This I'm talking about scale data. All the white pixels will have the value of 1, right? So the input image will look like something like this, right? The image that is stored with us. The input image, let's say, is the image which is like this, right? This is also an X, but you can see that the ones are appearing at different pixel locations, right? The ones are appearing at different positions as compared to the image that is saved with us, right? Now, when comparing two images, if any pixel value doesn't match, then these images don't match, at least as per the computer. Ideally, we would like to be able to see X's and O's even if they're shifted, shrunken, rotated, or deformed, right? So this is a very key ask that we have over here, right? We would want to be able to classify X's or O's, even if they are shrunken, even if they are magnified, even if they are rotated, deformed, right? Whatever be the case, even if it is written by a 5-year-old person or child, right? But we should be able to classify those. And this is where your CNN actually comes in, right? So this was a very uh, naive approach, a very basic approach, which will almost always fail, right? So that is why we actually come to CNNs. Okay. probably I think we need a classifier which can be used with images and correctly predict what it is, right? Okay, so now if I look at this use case and try to solve it, how a CNN would be solving this, right? So a computer understands an image using numbers at each pixel value as shown in the figure. Here, blue pixels have -1, while the white pixels have a value of 1, right? Now, if you see, this is an X, and this is what a computer will see. It will see that for an X, ones will be there wherever there is 1, that is a white pixel, and wherever there is -1, it is a blue pixel, right? The computer doesn't know it is an X or it is an O. It is just trying to match the output. Okay. Now, let's assume that I do this. My input image is this. Okay, on the left hand side. This is my input image. Okay. This one. Yeah. Okay. This is my input image. Okay. This is my sorry, this is my saved image, the one which is saved with me. Okay. And this is my input image. Okay. What I do is I uh, I basically put them on top of each other, right? If you see, I compare them. When I compare them, if you just normally search and compare the values between a normal image and some other image, we would get a lot of missing pixels, which means this is not an optimal way of image classification, right? So this over here, if you can see, this was the naive approach which we were predicting, right? So over here, you can see that there are so many mismatches. So if I count the number of pixels, only 30% of the pixels, 40% of the pixels might be matching for these two images, right? So we might not be able to say with full confidence that these two images are an exact match, right? This is not something that we can do over here, right? But let's see how a CNN will solve this problem. Okay. Okay. So now what CNN does is, okay. So now what a CNN does is, CNNs compare images piece by piece, right? The pieces that it looks for are called features. By finding rough feature matches in roughly the same positions in the two images, CNNs get a lot better at seeing similarity than the whole image matching schemes, right? Now, what will happen is that CNNs will match features, okay? It will look at this, right? So let's say I pick this block from the input image, this block, okay? Now this block, if you see, it contains what? It contains two white pixels and two blue pixels, right? Now what it will do is that it will start matching this block, this feature, with each and every block of the image. It will match here, not a match, right? It will match here, not a match, right? This is not matching, right? Over here, this matches, no, right? But when it comes here, it sees that this is actually matching with the feature over here. But if you see, it is not matching at the it is matching at the corresponding space as well, but it is also matching at each and every possible blocks that can there be, right? So even if your X in the output image or in the X in your input image is slightly rotated, is let's say zoomed in or zoomed out, a CNN will be able to detect that, okay, this feature, that is this particular block, wherein there are in the diagonal there are whites, right? This is matching this particular block over here of the input image, right? So what it will do, it will say that, okay, this feature is a match. Okay. Now similar to this, if I focus on the green one will be a match for what? This one will be a match over here. Okay. And this similar feature will also be a match over here as well, right? But because this green is similar to this green, so that means that it's a good thing. It is matching here as well. It is matching here as well. Now, if I look at this one, purple one, over here, the feature is slightly different. And this is only matching here, right? But the matching will start from here, right? If I look at this particular, this is the feature that I'm matching now, yellow one. Okay. So what a CNN will do is that CNN will start from here, from the top part. It will see, is it matching? No. Okay, then it will move. It will move to the right, one block to the right. It will once again see if it is matching. No, right? It will keep on going. It will come till here, right? Now, let's say it comes here. It sees this part and this part is not matching. Okay. Now it moves to the right, one pixel to the right. And here now it sees that, yes, it's an exact match, right? If you can see over here, it's an exact match. So now through this, what a CNN is doing is that a CNN is actually comparing each and every feature, it is breaking down the image into features. And then on that basis, it is scanning through the entire input image and seeing whether that feature exists or not, right? And then on that basis, it is moving forward. I'll tell you more about this. Coming to the next slide, each feature is like a mini image, a small two-dimensional matrix of values, array of values. Features match common aspects of the images. In the case of X images, features consisting of diagonal lines and a crossing capture all the important characteristics of most X's. These features will probably match the arm and center of any image of an X, right? If you see, in case of an X, right, the features that are actually helping us are the features wherein the diagonal values are populated with 1, right? If you see, these are the features, either this one, okay, so these are the 3 features that will be very key for us whenever we are actually trying to detect an X, okay? What are those features? One is, so if you see this one here, this is your diagonal, okay? Or this is the one wherein there are cross diagonals, both diagonals are there, or this one where it is the diagonal in the other direction, right? So the CNN has identified that these are the 3 key features which can create any X, right? Any X can be created if these features are actually matching, right? Now it will try to match all these features with your input image. We define that input. That is the size of the convolution step that you have to take, right? So you will have to decide, you will have to define that when you are creating the convolutional layer, right? The smaller it is, the better, but again, it's your call. Okay, so now, yes, so if you see in this particular case, these are the 3 features which the CNN has extracted, right? But see, in reality, it's not that these will be the only 3 features that the CNN will extract. CNN will extract thousands of such features. But with training, the CNN will know that only these 3 features are the ones that are actually helping you to predict whether it is an X or not, right? So the weights of all the rest of the features that are there will probably be tending to 0, but the weights of features which are like this or similar to this will be tending to 1. Okay. See, depends upon the convolution layer. So that's why, let's say you apply a convolution layer and you apply a convolution matrix of 2 cross 2, right? Then in that case, for that layer, all the features that will be detected will be the 2 cross 2 features, right? But in that 2 cross 2, maybe the center, this feature, right? The center feature that we are seeing, we might not be able to extract that feature, right? So let's say I go ahead with a convolution step of 2 cross 2. In that case, I will only be extract these features, right? These features that are there, maybe. Okay. Right. Now, let's say after that, I apply one more convolution layer wherein I give the size as 3 cross 3, right? A size, the size of the step. Now, in that case, you will also be able to identify this feature. Okay. So that depends upon the number of convolution layer you are having. You can have any number of convolution layers, and these convolution layers can have different sizes of the convolution matrix that you are applying on top of the data. Okay, right? So let's say you apply 3 convolution layers in your data. The first convolution layer is applied, and the size of which is, let's say, 2 cross 2. Okay, so that convolution layer will map all the 2 cross 2 matrix features that are there with your input image. Now, let's say the second convolution layer that you have applied, you have given the size as 3 cross 3. Okay, so in that case, the second convolution layer will give you 3 cross 3. Okay. Okay. So now looking at the convolution layer, what exactly happens here is that it is, first of all, convolutional layer is the first layer of the CNN, right? When presented with a new image, the CNN doesn't know exactly where these features will match, right? So you can imagine that when a new image is given to a CNN, it has a bunch of convolutional filters that are there, but it doesn't know where these filters are going to match, right? So it tries them everywhere in every possible position, right? As I showed you, what will happen is that the 2x2 matrix will move across the entire image and see what are the different areas wherein this particular feature is matching, right? In calculating the match of a feature across the whole image, they act as filters, right? I'll tell you what we mean by this. Okay. When presented with a new image, the CNN doesn't know exactly where these features will match, so it tries them at each and every possible position, right? In calculating the match of a feature across the whole image, they act as filters. I'll tell you what this means. The math used to perform this is called convolution, from which convolutional neural network gets their name, right? We have 4 steps in convolution. Line up the feature in the image, multiply each image pixel by the corresponding feature pixel, add the values and find the sum. Divide the sum by the total number of pixels in the feature. Right? So this is the process of convolution. I will show you this with an example and then I will explain each and every point over here. Right? Okay. Now let's assume that this is the convolutional layer filter that we have applied. Right? This is the filter that is for the diagonal. Okay. Look at this filter. What is this? All the diagonals are 1, rest all the positions are -1. Okay. Now what will happen is that if I apply this filter over here in the first block, don't focus on the block that is highlighted. If I apply this filter over here, can you tell me how many elements are matching between these two? Between these two, the yellow one and the black one. 2, right? Exactly. Okay. So two elements are matching. Okay. It is not an exact match, right? Now, similar to that, if I what I'll do is that I'm going to move this filter time and again. I will start from here. Next time I will come to here. Okay, not a match. Next time I will come here, not a match. So on and so forth. I'll keep on moving. As soon as I come here, I see that this is a match. Okay, this is an exact match. Okay, so if you see over here, what will happen in this particular case, each and every position will be a match, and this hence becomes a feature match. So in our example, consider a feature image in 1 pixel, multiply this with the image, and the product will be stored in another buffer uh, feature image, right? So what will happen when it's a match? Okay, 1 second. Now we will be applying this filter on top of each and every what will happen is that we will be applying this filter on each and every data point, right? So now because each and every image is a match, when each and every point will be a match, the final output will be what? That will be 1 because 1 is a match. So 1 multiplied by 1 becomes what? 1. -1 is a match. So -1 multiplied by -1 becomes 1, right? So what happens is that for the feature which is matching, for the part of the image which is matching, the final output will be 1. Okay. Now, for the part wherein this is an exact mismatch, what will be the final output?
Let's have a quick quiz question, guys. And the question is, which of the following can improve the performance of the AI agent? And your options are perceiving, learning, observing, or all of the above. Please mention your answers in the comment section below.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective as it is taught by IIT professors and industry experts.
1 into -1 for the diagonal will be what? This will result to -1, which will be -3. All the remaining -1s will be multiplied by the correct value, so they will become 6. So 6 minus 3 will be what? 3. 3 by 9 will be what? That will be 1 by 3. Okay. So basically, no, that will be 1 by 3, right? Okay, 1 second. Let's go back to this. Let's go back to this, right? So what happens is that whenever it is this is a match, right? You will multiply each and every element by each and every corresponding element in the input image, right? So this one for the feature will be multiplied by this value. Okay. What will that give me? That will give me 1 multiplied by 1 is equal to 1. The second element of this feature matrix will be multiplied by this value. What will that be? -1 into -1, right? What will that become? That will become 1, right? So we have gotten 2 ones. Now, once again, the third value of the feature matrix will be multiplied by the third value over here. This again will become 1, right? So like this, if you see for this entire block, the green block, because all the values are matching from the feature detector, all the values will be giving you a value of 1, right? 1 into 1 is 1 and -1 into -1 is also 1. Okay. So if when you will sum up these values, you will get what? You will get 9. You will do 9 divided by 9 and you will get the final average value as 1. And that is how this does feature mapping. So let's say we have an image which is something like this. Okay. I want the final value that we will get once when we apply the feature matrix on top onto this matrix, right? Okay, so this is the image, let's assume, and this is the feature matrix. Now you have to superimpose the feature matrix onto this one. 1 multiplied by -1 will be -1. Then again, this 1 multiplied by -1. So each and every time you multiply, you will get a value of -1. You sum up, that will become -9, and -9 divided by 9 will be -1, right? So now you can imagine. So see, if you see this particular image was an exact no match for the feature detector, right? It was exact reverse of what your feature had. Your feature detector had ones at the diagonal, but this image had -1s. Your feature detector had -1s on all the places which was not a diagonal, and this one had all ones there, right? So this was a case wherein the feature detector was not matching even 1 pixel value. Okay, so this value came to -1. Okay, now you can imagine that after the convolution step happens, or my input data, my input images will be in the range of -1 to +1 only, right? All the pixel values that will be there will be in the range of -1 to +1 only. Is that correct? The features which are matching will have a value of 1. The features which are not matching will have a value of -1, right? Okay. So now this is what happens in convolution. So what we do is that either way, every matching pixel results in 1. Similarly, any mismatch in a pixel will result in -1. If all pixels in a feature match, then adding them up and dividing by the total number of pixels gives a value of 1. Similarly, if none of the pixels in a feature match, the image match, then the answer is -1. Okay. So this is how you apply convolution. Okay. Now, can you tell me what will happen? So this is a this is what this is a 1 2 3 4 5 6. This is a 9 cross 9 matrix, and we are applying the 3 cross 3 convolution filter onto this matrix. What will be the resultant size of the matrix that will result from the convolution of this step? What will be the resultant matrix? The size of the resultant matrix. Okay, so the question is that when I apply this 3 cross 3 convolutional layer matrix filter on top of this 9 cross 9 input image, the resultant matrix, what will that be of the same size? That is 9 cross 9. I want, if I am multiplying this, right? I am multiplying these two together. Okay. The resultant matrix will be a new matrix. Okay. I want to understand what will be the size of this new matrix that will be resulting. If I apply this filter over here, how many values will I get as a final output? 1, right? So let me denote that one value as a dot over there, right? So this will give us the total number of pixels. Now what will happen in the next step? In the next step, how will my square move ahead? It will move like this, right? in the second direction, it will move like this, right? It will give me one more value from here. Am I correct? That value will be what? Another pixel, right? Now, similarly, this square will keep on moving forward. I will move it over here. This will give me one more pixel. Again, I will move it. How many pixels will I have till the end? First box, first three rows will give you one value. Second three rows will give you two values and so on and so forth. So the final matrix that you will get will be of the size of 8 cross 8. One dimension will be reduced. Abhinay, yes, that's correct. So basically you are reducing the size of the matrix from 9 cross 9 to 8 cross 8, right? So that is what will happen when you are applying a convolutional layer, right? Your size of the matrix will also go down. First block, let me apply that over here and show it to you. First block will result in how many values? 1, right? I will show this maybe once so that you understand. Now, let's say I go to the second block with the red one. This block will give you how many values? 1, right? This is coming from the red block. Then I once again go, I take the green box, let's say. This box will give you how many values? This will give you 3 values. Okay. Then let's say we come to the fourth block. Fourth block will be from here. Okay. This will give you a fourth set of values. Okay. Then let's say we draw a purple one, which will start from here. Okay. This will give you how many values? 5. Okay. Yeah, I think. Okay, now let's change this to pink. We will have 2 more values. And Puneet is right? If you see, guys. How many are there? 6. And then finally we'll have 7. Because the stride is of 1, we will have how many values? We will have 7 values. Does that make sense? So that's my bad. I was telling 8, but yeah, I think the formula is -2. So you have one lesser value over here. So this will be what? This will be 7 cross 7. Does this make sense? So essentially, after applying the convolution filter, so okay, this will be the last block, right? Orange one. And here your convolution will stop for this row. Now for the next one, what will happen is that your convolution will start from this box, this block. Okay, now this will go in this direction once again. So essentially your 9 cross 9 matrix has been reduced to a 7 cross 7 matrix after doing convolution. Okay, after doing one step of convolution. Okay, the final value obtained from the math that is performed in the last step is placed at the center of the filter image as shown above. Right, so this is what will happen. And here you can see, now move this filter around. This is the same process that I have showed you right now. You are going to move this filter around each and every time, and you will get value corresponding to each and every value wherein the filter was set, right? And now over here you can see that once when we apply this filter on top of this image, this was a 9 cross 9 image if you count 9 pixels, and this, as Puneet said, this will result in 7 cross 7, right? You can see that the image size has reduced to 7 cross 7 and your values have also changed, right? Now can you tell me what are the in the final output, what are the pixels wherein the feature is an exact match? Any pixels wherein the feature is an exact match? Yes, right. So all the pixels which have the value of 1 with them are an exact match. All the features which have a negative value associated, they are actually a mismatch, right? all the features which have a positive value but is not equal to 1 is a slight match, right? So 0.55 is kind of a 50% match only, right? 0.33 is kind of a 30% match only that we have seen over here, right? So to complete the convolution process, repeat this process, lining up the feature with every possible image patch. Take the answer from each convolution and make a new two-dimensional array from it based on where in the image each patch is located. This map of matches is also filtered version of the original image. It's a map showing where in the image the feature can be found. Okay, values close to 1 show strong matches, values close to -1 show strong mismatches for the photographic negative of our feature, and values near to 0 show no match of any sort. Okay, so this is what convolution does actually. Now what you are seeing over here, right, this is just one filter. Now in your convolution step, you will first define the size of the convolution matrix, that is 1. You will also be defining the number of filters that you will be requiring, right? So you can imagine that each and every time your input image will be multiplied by many such filters and many such outputs will be created. Why are we doing that? Because these are extracting features for us. Okay. Hasmith, we calculated the values, right? Previously, we calculated the values when it was an exact match, when it was a no match, when it will be a slight match. Let's say it comes out to be -3/9. So it will be what? It will become -33.3, -3.3, right? -0.33. So that is why you are getting decimal values as well. So if you see, before we had gone ahead and we had converted this into by using this particular function, right? So categorical function, if you see this example that I gave you, okay. So before using that particular function, in the label value, what we had was that we had the number which was predicted for that particular image, right? So let's say for the first image, the number was 0. For the second image, the number that was there was 1. For the third, it was 2, and so on and so forth, right? Now this categorical function that we are working with, what this will do is, this will convert your data in this format, right? Okay, so now if you see, now we don't have one variable which has three, which has the values in it for 0, 1, and 2. Instead, we have created 3 variables. Each and every variable is a binary variable for a particular value, right? So if you see y label 0 over here will be 1 only when this particular target variable is predicting 0, right? Or the real value of the image is 0. Y label 1 will be 0, Y label 2 will be 0. Now, when your Y label is 1, that is when your image that is there in your data is for the digit 1, then Y label 1 will be 1 and rest both will be 0, right? So, excuse me. So like this, it works. It works like this because we are supposed to give probabilities, right? So when it comes to deep learning models, machine learning models, if you imagine, if I would have had just one variable over here, right? And which had the value 0, 1, 2, whatever. Now, what will your deep learning model give? Your deep learning model can maybe give the probability of this being a 2, right? Instead, what we are doing is that we are giving you for each and every number what is the probability that your deep learning framework is predicting, right? So my deep learning model might not be correct at times as well, right? So at times it might say that, okay, a number which is looking like 0, it might predict that number as 8, right? So then what will happen is that it will predict probabilities. It might predict that, okay, label 0 probability is, let's say, 0.75, label 8 probability is, let's say, somewhere around 0.85, right? So it becomes simple to predict. Yeah, it is like one hot encoding, not like it is one hot encoding actually, right? Okay, so this is what actually categorical function does, and this is how a multi-class classification problem looks like, right? Now, if you compare this to a binary problem, right? In case of a binary problem, because there are only two classes, right? That is 0 or 1. So we will end up with just one variable, right? It might be y label 0, okay? And hence we will not see that, okay, we are creating two or three different columns, right? But when you have multiple classes, right, in those cases, whenever you have multiple classes, you will have to go with a multi-class problem. And for that, your target columns will be the total number of classes that you have to predict. And we will be doing a lot of parameter tuning. We will be selecting selecting different parameter values, and we will see how we can optimize those, right? Learning rate and all, if study, we have not played around with that. And learning rate is a parameter which actually is is a key parameter when it comes to tuning of a deep learning model, right? So we are going to see how playing around with learning rate will give us different loss values and different performance values. Okay, so Hasmit, why float? Because if you see, okay, so the range for X train, right? The X train min and max will be 0. If I, let's say, see the minimum value for X train will be 0, right? The maximum value will be what? It will be 250. Okay, I think this is converted. Is X train converted? I think this is standardized, right? Okay, this has already run. Okay, so I'm going to rerun this in the next notebook. But yeah, so why we are doing this is that your X train will have values in the range of 0 to 255, right? So there will be 256 different unique values that can be there, representing each and every bit. Okay, now to standardize this data, I know that my numbers are in the range of 0 to 255, right? So I will just go ahead and I will divide by 255, because each and every row has values only in the range of 0 to 255, right? And why float? Because let's say that for a particular unit, I have a value of 32. Now 32 by 255 will be what? It will be a decimal value, right? So I want to keep the decimal places as well. So I'm kind of standardizing this data only. So when I'm standardizing, because I know that while dividing by 255, these values will, the final values will be coming as float, right? Hence, we are converting this to float before we divide this by 255. If standardizing should be divided by mean and multiplied by standard deviation, no, it is actually subtracting by mean and dividing by standard deviation, right? But that will happen if, let's say, your variables are in a different range, right? So over here, you can also do that, right? That is not a problem, but that is a complicated way of standardizing, because here, if you see, for each and every row, right? For each and every row, all your values will be in the range of 0 to 255. We usually subtract by mean and divide by standard deviation so that each and every column are coming in the same range of, let's say, 0 to 1. Okay. Now, but if you look at the data over here for each and every column or each and every row, all my values are in the same range, 0 to 255. Now, if I compare this with some kind of a structured data, let's say I compare this with a customer data, wherein in one column we have the customer's age. Now, customer's age might vary from 20 years to 75 years, right? Or to 100 years. Now, for that, if I use the formula of value minus mean divided by standard deviation, all the values for that column will come in the range of 0 to 1. Now, let's say second column is the salary of a customer. Now, the salary of the customer can be from 10,000 to 2 lakhs, 3 lakhs, 4 lakhs, whatever, right? So, in this case, we adopt this formula because we know that the variation of each and every variable is different, right? Over here, when you're dealing with image data, right, you know that for all your columns, all your values are in the same range, 0 to 255, right? So hence you go ahead with a simplified standardization process, because see, the aim of standardization is just to bring all your columns in the same range. right? So now when we divide here by 255, we are getting all the columns directly in the range of 0 to 1. So there is no need of subtracting by mean and dividing by standard deviation. You can do that. It will not make any difference to the model. The model will still work as it is, right? So you can try that as well. But in image data, you usually, because you know that the range of all the rows and columns by default is the same, right? Hence, you can go ahead and you can just divide by whatever the maximum value. Any other questions, guys? I can see that some of you have gone through the notebook, so that's why there are questions, which is good, right? Anyone, if there are any other questions for people who have not gone through or who are still going through, please do that. In today's session, we are going to keep it simple. I'm not going to change the data because this data is something that we have worked with yesterday. But we are going to change the approach through which we are creating the model, right? So basically, last time we have used the sequential framework of Keras. This time we will be using the functional, the functional aspect of it, right? The only difference is the syntax and how we are defining the network. The end result will be same, right? So if once when you have this particular notebook as well, you will be able to see that you can basically populate same outputs from both the approaches, right? Now it is your choice to go ahead with sequential syntax or the functional syntax. In the case of a functional, when we are defining our models using the functional way of things in Keras, the only thing is that for functional models, you can connect any layer to any previous layer, right? So now that is something that actually is required when you are working with much more complicated models. But if you are working with ANNs, CNNs, recurrent neural networks and all, in those cases, it might not be required. But for functional, for the functional part, you can very well go ahead and construct sequential models as well, right? All you have to do is that you have to make connections sequentially. Okay. So both the things using functional, you can achieve both the things. That is, you can create sequential models as well as functional models, but vice versa is not true. Using the sequential framework, you can only create sequential models. Functional models you will not be able to create. By functional, what I mean is that models wherein, let's say, the input layer might be connected to the third layer, right? Because in case of a sequential model, what happens is that the input layer will be connected by the first layer that you have defined right after that. The first layer will be defined by the second layer, will be connected by the second layer, and the second layer will be finally connected by the output layer, right? But in case of a functional model, you can rechange how these layers are connected. You can connect the input layer to the hidden layer number 1 and to the hidden layer number 2 directly. Okay. So if that is required, but for the scope of this course and for the scope of most of machine learning that is being done, that will not be required. But still, we are going to go through that. We are going to see how we define functional models so that if ever you need that, and you will have two tools in your pocket when you are creating deep learning models, right? So you will have two ways through which you can create deep learning models using Keras. I have 4 inputs. Okay. And then I have 2 hidden layers, okay, both containing 5 neurons. Okay, and I have one output layer, one output neuron. Okay, and now these will be connected with each other, right? I am not going to connect each and every one, but if you see, in essence, what happens is that your input layer is connected with your first hidden layer, right? Input layer will be connected with first layer, this layer. Hidden layer 1 will be connected to hidden layer 2, and hidden layer 2 will be connected to the final layer, that is the output layer, right? Okay. Now what happens is that this is your sequential model. Okay. Now what if I want to create a model wherein I'll redefine the same images, sorry, same layers, right? But this time I'll define the layers in a different manner, right? So let's say input, okay. Input has, let's say, once again, 4 neurons, okay? And your hidden layers, I have defined 2 hidden layers, okay? One is over here, 1, 2, 3, 4, 1, 2, 3, 4, 5. And then there is one more hidden layer. Okay, 1 second. Now imagine I'm defining the hidden layer in a horizontal way, right? I'll tell you why I'm doing this. This is hidden layer 1, and let's say this is hidden layer 2. Okay. And then we have the output layer finally. This is the same example that I had given before. Okay. Now what will happen is that over here, when you're working with functional models, you can connect this layer and you can also connect this layer directly. Okay. And then both these layers outputs can be connected to the output layer. Okay. Now this can be a functional model. Over here, you can see that the sequence is not being followed, right? So this is a sequential model. Okay. And this over here is a functional model. Now the thing with functional model is that you can also define sequential models here, right? If you are connecting each and every preceding layer with the succeeding layer, right? So you will be able to create sequential models as well. Okay. So this is the difference. For the scope of what we are learning and for the scope of majority of deep learning, right? I have till date never used any functional model in any of the use cases that I've been working with, and I've been using deep learning for the last 5 years, right? So for the scope of this course, yes, we will be looking at how we define functional models, but I think there are very, very scarce cases, very, very complicated cases wherein you will have to adapt to functional models, right? Deep learning in itself, sequential deep learning models in itself are actually capable of solving much more complicated problems. Okay. Okay, let's say that you are solving a particular problem which Swiggy might face, right? So Swiggy has a delivery person who is supposed to cover a particular area, and now you have to optimize the time and optimize the total number of deliveries that you have to give that particular person, right? So in this particular case, you actually don't solve these problems with a typical deep learning model, right? This is an optimization problem wherein you are trying to optimize the route of the delivery person so that he or she is able to manage maximum deliveries in a minimum amount of time, right? Now, these are the kind of problems which can be solved by graph related networks, right? And these graph networks are created by functional models only, right? But if you are working on slightly less complicated problems, which let's say which let's say is a problem wherein you have to predict the total number of orders that a delivery person is going to take on a given day and all. In those cases, you can go ahead with deep learning with your sequential models. Okay. Callback, if let's say the moment when your model is running and your model is training itself and it is testing itself on test data, right? And you have given, let's say, 100 epochs. But after the 25th epoch, it starts to see that your validation performance has started going down and your training performance is still going up, right? So that is the point wherein the model will stop by its own. It will not continue training because it knows that this is the point, it has achieved the point wherein now the training performance is still increasing, but your testing performance is actually going down. So it means that if you train the model even further, the model is going to fit more to the training data, which will not be a good and stable model, right? So in that way, callback helps us in stopping the model. Okay, so we get started with importing the libraries that we had. So similar libraries, we are using pandas, numpy, tensorflow, keras. From keras.model we import model. From keras.layer we import all the layers. From keras we import optimizer. This is for your gradient descent, right? From tensorflow.keras.utils we import this function that we have used yesterday as well, to categorical, right? Now we will over here, this is the same data as we have read yesterday, but this time we are reading it through a CSV file. So I'm showing you this as well. This data is actually flattened out, and if you will see that it contains 784 features and one target. For each and every pixel corresponding to each and every 784 features, you will have a given value. Okay, so we are able to read, and now if you see, so this is the data that we have. Okay, so the first column is the label. It means it is the actual value of the image that is contained in the in that particular image, which is corresponding to first row, right? And then we have 784 features. That is, we are starting from pixel 0 and we are going till pixel 783. For each and every pixel, there will be some value that will be associated with it. Okay. Now over here, what I do is that I split my data into DF features and DF label. DF features will be what? Index starting from index 1 and going till index 785, right? That will be our DF features, and just the 0th index will be our target label, right? If you see 0th index over here is our target label. If I just run this, this is the slicing and dicing in pandas that you would have seen previously as well. Right? So if you see, if I do this, this will give you only the first column values. Okay, so we do this, and similarly for X test, if you see, we have read two data frames, right? DF train and DF test, right? For X test as well, we do the same thing. We just go ahead and we keep all the variables in X test, right? Now I run this. So if you look at DF test, right? DF test will not have the target label, right? DF test is the test data frame that we have over here. Label column represents the target, Ankit. Whatever is the image, whatever is the number of the image. Okay, DF test, you will see this will not contain any of the label value because this is a separate data frame that is provided to us to test the model on. Okay. Okay, so over here, if you see for DF train, we have gone ahead and we have split that into DF features and DF label. But X test only contains the feature values because we will use this data finally to test the performance of our model, right? So at that point of time, okay. So this is the X test that we are actually keeping aside. Now, if you see, if I show you the shapes of the data, right? So DF features is my train data, and if I see the shape, how many are there? 42,000, right? How many rows are there in the test data? 28,000. Total, how many rows are there? 70,000. We had 60,000 rows in our training data and 10,000 rows in our test data. Okay. So this time what we have done is that we have kept 28,000 rows for testing. We have 42,000 rows for training. Now, this test data that we are keeping, right? We will keep this totally aside. Totally aside as in only when your model is finalized. Only then you are going to expose your model to this data. You are not going to expose your model to this data while you are training the model or while you are tuning the model with the best set of values that might be there, right? So parameter tuning and all, you will not be using this X test data. You will be only using this X test data when you have finalized the model, and that finalized model, you are very sure that this is going to work well on unseen data, and that is the point when you will be exposing your model to this X test data. Okay. Now we are only left with 42,000 rows to work with. Okay. Now out of these 42,000, obviously, in order to test whether our model is stable across different data frames, we will have to split this data into training data and into another test data, right? So this can be considered as a CV data. So validation purposes, we are again splitting this train data into training data, and we are keeping 20% aside to be kept to validate the performance of the models as well. Okay. For that, what we do, we call train test split. Okay. I hope everyone is able to follow the chain of thought here. We had 70,000, 28,000 rows to test the model, right? I told that just now. That is there. We have kept that aside to test the model. Okay. So the chain of thought is that we have 70,000 rows of data in total, out of which we have kept aside 28,000. 42,000 are left, right? So 28,000 we have kept aside. So essentially 40% data we have kept aside to test the final model. And if I talk about actual real world models, right, this is how you actually proceed, because you would want to have a healthy chunk of data in your testing data part, right? Because if let's say you are building your model on 90% of the data and you have less data to test on, you will not be able to test how generalized or how stable your model is actually on unseen data, right? Now, data leakage is a concept that I think you guys should be familiar with. But if you're exposing the distribution of test data while training, your model might be able to adapt, right? Hence, we are keeping this totally aside. So 28,000 rows out of 70,000, 28,000 rows have been totally kept aside for testing your final model. Remaining 42,000 for cross validation, we are again taking a 20% split of that, right? So 40,000, 20% of 42,000, 8,400 rows will be considered for cross validation, and the remaining rows, whatever we have, 33,600, will be used for training the model. Okay. So how do we do that? We do that through train test split. If you see in train test split, I am passing DF features and DF label. DF features are the features for 42,000 rows, and DF label is the target label. Okay, test size I've given as 0.2, random state I've given just some number, and from this I get my X train, XCV, Y train, and YCV. Right? I convert this data into NumPy form. This X train, I've converted this X train dot to NumPy dot to reshape, right? Dot reshape. I've reshaped this data to this data actually will be in the same format in this form only, 33 600 784. But just to be sure, what we do is that we actually go ahead and reshape the data once again. Okay. If you see over here, this X test only contains the labels. Right? I'll show you DF test. X test is being created from what? It is created from DF test, and it does not contain your features. It does not contain your label. It will only contain your features. That is why 0 to 784. I have explicitly talked about that before. Okay. Okay. Right. So okay, so now we have converted all this X-train and X-test and XCV to a NumPy matrix. Okay. Now, if I show you the minimum and maximum, right, why we are standardizing by dividing with 255. If you see, the minimum and maximum values are what? They are in the range of 0 to 255, right? And if I change this for X-test as well, right, same thing will be there. Okay, for X-test as well, 0 to 255 will be there, right? So hence, we can go ahead with a simple normalization, a simple standardization, wherein we can just go ahead and divide the data by 255. So over here, we have first converted a slightly different syntax from yesterday. We have first converted all the matrices to float data type as type float 32. You can give multiple lines, multiple statements in one line if you are ending a line by semicolon as well in Python, right? So this is the example of that. We have converted all three matrices to float 32, and then we have gone ahead and we have divided them by 255. This is again a quick syntax to divide, right? If you are doing xtrain slash equals to, then it will do xtrain equals to xtrain by 255. Okay, so this will standardize your data totally, and then number of digits that we have is 10. This is same as yesterday. We are converting a Y train and Y cross validation by using this particular function. We are doing one hot encoding on this data, right? So if you see now, your Y train, which was previously values for each and every label, zero in the range of 0 to 9. Now we have created one hot encoded variables, right? Which will create 10 binary columns, and the binary column will only be true for that particular number which is there in that particular corresponding image. Okay. Uh, deep neural networks make this as a rule of thumb, that your data should always be standardized, right? For your gradient descent to work in an optimized manner, in a faster manner, all your data that is flowing into any of your neural network deep learning model should be standardized, right? If you remember, we had reshaped that 60,000 cross 28 cross 28. We had reshaped that into 60,000 comma 28 into 28, right? Now similar to that, we need our output to be we need in rows, we need the 33,600 values, and in columns, we need the features, right? So just to be sure that whatever our final matrix has come, right, it is following this format, we go ahead and we just to be sure, we do a dot reshape once again, right? To NumPy thing, see, from data frame, you have to convert this data into a matrix, right? Till now, it was in a data frame format, right? Everything was in a data frame format. So before feeding that to a deep learning model, you'll have to convert it into a NumPy array. Okay. What is XCV? XCV over here, we have just now created XCV. XCV is the cross validation data set, 20% of 42,000, right? I gave you numbers as well, 8,400. Those will be there for cross validation. You have one target variable which has three unique values, 0, 1, 2, 2. I talked about it just now as well before starting the class. You will create three binary variables, and each and for y label 0 is true when y label is 0. Y label 1 is true when y label is 1, right? Y label 2 is true when y label is 2. All the rest will be 0 when the other variable is true, right? But sometimes what happens is that when you are converting your data from data frame to matrix, it might happen that your rows and columns might get jumbled up, right? Hence, just to be sure that our data is following this format only, that is 33,600, that is your rows are the features, your rows are the image data and the columns are the features. We are just to be sure, we are doing this again. Even if you would not have done this, this would have been fine. But I'm saying, when you're working with deep learning models, at each and every step, you should be sure what is the form in which your data is at, right? So just to be sure, we have just gone ahead and we have done that. You are correct that, yeah. Okay, so I think we have run this, right? Or not? Okay, so we have converted our data into our label into categorical values, one hot encoded values. This is there, right? We have normalized our variable. We have normalized our data. We can check for values very quickly. Y train 0 is 2, right? So 2 means that the third uh, binary variable should be true, right? And that is what we are seeing. Y train 3 is actually 7. So the third last should be 1, and that is also here. So you can see that the one hot part that we have done, this is working correctly. The data frame which does not have any label. DF test is the data frame which does not have any label, right? Okay. Okay. So this is our data. Now we are ready, right? We are ready with the prepared data. What have we done? I'll reiterate. We had 70,000 rows. Okay. This time by default, our data was split into 28,000 testing values and 42,000 training values. Now those 42,000 training values, we have again gone ahead and we have split that into training data and validation data, right? Training data is 33,600 because we have taken 80% of 42,000, and your validation data is 20% of 42,000, which is 8,400, right? Now, before we go into the model, we have our training data of 33,600 rows, and we have our validation data of 8,400 rows. Test data is kept aside to test the final model. Okay. After doing this, we have done some transformations in the data. We have converted that data into float. We have standardized that data just to be sure that the shape of the matrix is correct. We have reshaped the matrix once again to whatever shape it is required to have. Okay. Then we have converted our target variables into binary variables, right? By using the function, this particular function, categorical function, right? That is it. Now our data is prepared, and now we can go and experiment with the different deep learning models that we can build, right? So by different models, I mean models with different parameters, same model with different parameters. Okay. Now we will start with our tuning of the parameters, right? So for the first model that we are going to test, what the different parameters that we are going to pass are input layer. Obviously, we have 784 features, so this will be fixed. Hidden layer number 1, I am passing 300 neurons. Okay. Hidden layer number 2, I am passing 100. Hidden layer number 3, again 100. Hidden layer number 4, I am passing 200. So I am defining 4 layers in between over here in this particular network. Hidden layers in total will be 4. And number of digits, which is the final output node, for that, I am giving the number of digits equals to 10. Okay. Now I will run this, and now pay attention to the second part. Okay. So now see, in the case of functional models in Keras, right? First define the model, right? This time we are not going to do that at first, right? We are going to do that as a last step. For functional models, first we will define the layers, the different layers that there are, and how they are connected with each other. Okay. So first layer is what? The layer of a feature, right? Input layer. So we will have to define the input layer. All we need to define over here for input is the shape. Okay. So in equals to input, and I've given the shape equals to 784, right? This is defining that my input is coming and it has 784 features over here. That's it, nothing else, because input layer, there is no other parameter that you can define. Okay. Second layer after that, I name that as X, and that is a dense layer. Number of neurons in this dense layer is n hidden 1, which is 300. Function that I will be using over here is this particular function, ReLU. Name of this hidden layer that I'm giving is hidden layer 1. Once when we will be printing the summary of the model, at that point of time, you will be able to, if you give the proper name, you will be able to see what is layer 1, layer 2, and so on and so forth. Now, this is your first layer, right, that we are defining. And this particular layer will be connected by the input layer, right? So by doing this bracket INP, it tells that input is being connected with X, right? So till now we have defined 2 layers, input layer and the first layer that is going to precede that, right? And we have told that the input layer will be connected to X, right? Now, once again, we transform X, okay? Now what we do is that X becomes, we add another layer, dense, number is n hidden 2, right? So n hidden 2 is what? 100. Function remains the same, ReLU. Name changes to layer 2. And this again is connected by the previous X, right? So X becomes, if you are doing X equals to 2X, right? So it becomes 2 times the value of X, right? So similar to that, you are just, what you're saying is that your second layer will be connected with your preceding layer, which was your preceding X, which in turn was connected with your initial, the first layer, which contains all the features to input. Now, hidden layer 3, once again, same thing. I have given that hidden layer 3 will contain 100 neurons. Activation will be ReLU. Name will be hidden layer 3, and this will be connected with the previous state of X, right? Which was still hidden layer number 2. Once again, I do the same thing for hidden layer number 4. It is again connected with X. And then finally, output, I define the output layer. It is a dense layer. Number of digits, that is number of neurons, will be 10 for my final layer. Activation becomes softmax because I want to predict probabilities for each and every class. Name becomes output layer, and this in turn gets connected with your X, which is connected with hidden layer number 3, 2, 1, and then finally your features as input. Okay. So this is how you define a functional framework, right? Till now, we have only defined the layers, right? We have still not fed the data into the model. Okay. Here we are making the connections in a sequence. But if I wanted to, let's say, if I wanted to create a different network, I'm just giving you an example. I will not be running this one. Ankit will do that at a later stage. ReLU does not, yeah, ReLU is not used for probability. Yes, Pushpinder. Prasanya, the diagram is the same as of a sequential model, right? If you see over here, uh, what is happening? Input is connected with your X, which in turn is again connected with your X, which is the new X. X, this was of X layer 1. Okay. Now this again is connected with X layer 2. This again is connected with X layer 3. Okay. And so on and so forth. X layer 4. And finally, this is connected with your output layer. Okay. So this is a sequential model only. Shapes, why are we using after that? Where input shape we'll have to define, right? We are not reshaping, Bhavya. We are just saying this is just a parameter which is saying that input shape will be 784, right? Yes, this is sequential only, Prasanna, but we are doing this through the functional way of things, right? So till now we have only defined the layers. Okay, we have not defined the model. Now when we have defined the layers, after that you can go ahead. Okay, so this I was trying to give an example. Let's say I had done this, x equals to this, and let's say this was y. Let's say this was z, then this will become y, this will become z, and this was, let's say, zz, and this was zz, right? If let's say I would have named the layers in this way, input is x is connected to input, y is connected to x, z is connected to y, and so on and so forth. Now over here with functional, I get one important feature is I can connect my z, right, directly to any preceding layer. Instead of connecting this to y, I can directly connect this with input, right? I can do that, and this will become a non-sequential model over here. ZZ, instead of connecting with Z, I can directly connect with Y as well. Okay, so this will become your non-sequential model. But don't worry about this. This is not in the scope of our course. As I told you, these are very highly complicated deep learning models. I also have not worked with these models, right? So there is no need. In your normal sequential models, there is lots that you can cover, that you will have to cover, and we will be focusing on that only. Okay. Okay, so we run this. Okay. And then all I need to do is I need to our model, I need to pass model and input, which is your input, and output, right? We pass your output. Now output, you know that output will be a function of all your preceding layers only, because we have defined that in such a way. Okay. Now if I do a model.summary, this will give me the entire model structure, right? Over here you can see that the parameters that need tuning, right? 300. Okay, so till now we have only defined the model, learning rate, nothing is gone. Now we have defined the model, input output layer is defined. Now we will be defining some other parameters in order to compile the model, right? Learning rate we define as 0.1. This time we are playing around with the learning rate as well. Okay, training epochs, let's give us 20, batch size, let's give us 100. SGD, your gradient descent, we will go ahead in this particular case with stochastic gradient descent, right? So from tf.keras.optimizers.sgd, we call this LR equals to learning rate. We define this particular object. We run this. These are the parameters that we have to pass. Okay. Now I do a model.compile, same as yesterday, right? From now, from this part on, your syntax will remain the same as yesterday, right? Model.compile loss, we have given this loss, cross entropy, categorical cross entropy, because we have categorical variables that we have created. Optimizer is stochastic gradient descent, and metrics is your performance metrics, which is accuracy, right? I will compile the model, and then finally I run the model. While running the model, I assign the values to history 1 because we'll be creating multiple models, history 1, 2, 3, 4. I do a model.fit. I pass my X train and Y train, right? I give the batch size as the defined batch size of 100, epochs equals to 20, verbose is 2, validation data is XCB and YCB. Okay, I will run this and we will see how the model performance is increasing or decreasing. Okay, this will take some time. So Adam is the default one. Ameya, if you see optimizer, the default that we have is Adam. And if you want to change that, you will have to pass that particular value. Added the dropout layer. So there were no parameters that need to be trained when you are adding a dropout layer. So the params became 0, right? So hence non-trainable parameters are 0. So there are some cases wherein you have non-trainable parameters. You apply a certain transformation to the data which is fixed, right? For which the weight value will never change. So then this value comes populates. But right now, since there are no parameters that are non-trainable, we are getting 0. So see, we are plotting multiple things: loss, accuracy, validation loss, validation accuracy, right? Now this loss and accuracy is corresponding to the training data. Validation loss and validation accuracy is corresponding to the validation data. So you can see the model performance for both the data sets that you have passed, right? Now with time, you can see that the loss is decreasing significantly on the training data. It is, right, 0.0012. But on the validation data, its decrease is not that significant. But still, you can see that the accuracy for your training data has achieved 100%. Okay, and on your testing data, it is somewhere around 97%. Okay, so we can see that this model is decent. This is giving me a validation accuracy of 0.97, 97%. Validation loss somewhere around 0.1025. Okay, we had come to a validation loss of somewhere around 0.0577. That was also because we were using 60,000 rows. This time we are using lesser rows. So this model will take more tuning, right? So that's why now we will change some of the parameters and we will see how we can tune this even further. Okay, this is the first batch of model that we have run. This is a model using stochastic gradient descent and a learning rate of 1. Okay. Now, in the second case, right? In the second case, let us go ahead and let us use Adam, right? And learning rate that we will keep will be default learning rate. We are not going to specify any learning rate. Okay. Same thing. If you see my input and output, this code remains the same that was defined previously. Model 2 becomes model input and output, and I compile the model. Loss remains the same. Optimizer changes from stochastic gradient descent to this one, Adam, and accuracy remains as the metric. Okay. Now I run this model as well, and we'll see whether Adam is working better as compared to stochastic gradient descent, right? The traditional Adam model that we have. You can't know that, Ankit. There are 3.5 lakh values. You can know that, you can download the pickle final all, but what will you do with that? Because you don't know what is happening inside a deep learning, right? So a deep learning model is a very, very complicated model. If you want to know, you can export the model as a pickle file, view that as a notepad or something, and you will be able to see the values, but you won't be able to make any sense out of this, right? Okay, so Adam, right? So I wanted to tell you guys about Adam. What is Adam? I'll very quickly tell you. See, normal gradient descent, what it does is that it takes the learning rate and it proceeds in the direction in which your error is minimizing, right? That is what your normal gradient descent does. Now, Adam is a variation of stochastic of gradient descent, wherein it takes momentum into account as well, right? What do we mean by momentum? Is that, let's say that for the past 5 iterations, you have moved in a particular direction, right? Let's say that you are on the top of a mountain and you are blindfolded, and for the past iterations, by checking the level of the, let's say, level of the floor on which you are at, you are proceeding in a particular direction, right? Let's say that for the last 5 times you have proceeded downwards slightly, but now in the sixth time you are seeing that you are actually supposed to go slightly flat. Okay, so what Adam will do is that Adam will take momentum of the past 5 iterations as well. It will see that, okay, on an average for the last 5 times you have been going down. This time this is asking you to go maybe towards the right or towards the left. So what I will do is that I will combine all the previous cases, and then on that basis I will get a particular direction in which I will move, right? So Adam, as compared to stochastic gradient descent, takes into consideration your historical losses as well and in which direction they have been, right? So this usually helps us in taking, like, it helps us to converge in a faster manner, because essentially if you are moving down, there might be some cases wherein there might be a slight detour or something that your error curve might take, but in general you are capturing the essence that yes, in general you are heading in the downwards direction, right? And that is what Adam actually does in a very simplified way.
Let's have a quick quiz question, guys. And the question is, what does the Bayesian network provide? And your options are partial description of the domain, complete description of the problem, complete description of the domain, or none of the above. Please mention your answers in the comment section below.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Okay. Okay. So this is the second model. Over here we have used Adam. Just Adam, we have not given any other criterion of parameter or something. And you can see that the accuracy has remained almost same, but the loss has actually gone down. But accuracy on your training, if you can see over here, is also slightly lesser. Okay. So now we will see if Adam can work if we tune the learning rate, right? So we now this time what we'll do, this is a third model that we are creating, right? And in this model, we are going to modify the learning rate to 0.01. Okay, all the rest of the things remain same. If you see, all the remaining things actually remain same. Okay, I will run this. And then I will run this. Okay, so this time, let's see how well it is performing. And see, this is how you actually train or tune a neural network model, right? Now, this time you can see that the validation loss has increased even further, because our learning rate has actually gone up from the last time. The last time when we called Adam, the default learning rate that it takes is 0.001. And this time we have given it the learning rate of 0.01, right? Sorry, zero point 0.1. 0.01, right? So because of that, this, if you can see that the validation loss has actually increased, and you can see how learning rate actually impacts your model. You can see through this only directly how learning rate will impact your model, right? This is not required. Okay. Now, one more example I will give you. If let's say I keep the learning rate as 0.5, I increase it even further. What do I mean if I keep the learning rate as 0.5? I mean that the steps that I will be taking are going to be of a bigger magnitude as compared to zero point 0.1 or 0.01. That means that my error curve, I might skip the minimum of the curve at times, right? Now, let's see if I run it with 0.5, what happens. Okay. Now you will see, just look at the variation that we'll have in the model performance. Okay. Accuracy 9%, 1%. Validation loss, you can see 2.3, 2.4. Okay. And both for validation and your training data as well. So you can see what impact learning rate actually has on your entire model, right? Learning rate 0.5, and the model has not converged. The same model which was giving us a performance of 98%, 97% is now giving us a performance accuracy of 10%, right? Okay. So now what we will do, let's try the final variation for now. Okay, we are adding one more layer, right? Let's add one more layer over here. If you see, now we have added 5 layers in between. We define the same layer framework. We define the model, and now you will see that the total parameters, trainable parameters have gone up, right? 308K. Now we will again, for gradient descent, we are going to use Adam only with learning rate of 0.01. Okay. And we can run this. Okay, we'll check only, right? This is 1, right? If you see, 1 is giving you all the losses. I think 2 is something similar, only slight changes. Okay, so it is not giving you the batch output. It is not giving you the arrows for the batch processing, right? It's a more cleaner output. Okay. Then I hope this is clear. So 1 or 2, I think both are fine. If you will give 0, it will not print anything. Okay. Okay, so this is the same. Now you can see something funny. What has happened is the performance has actually gone down even further by running the same model. Why has that happened? I will tell you why this is happening. So we have rerun the same model thrice, right? If you see, I have rerun the same cell 3 or 4 times. What will happen is that the same model object that was run last time with 200 epochs, 20 epochs, 100 batches, on top of that, the model will start training, right? So now this cell, when I run it for 4 times, it will have gone through 80 epochs, right? And increasing the number of epochs, you will see that the performance will with time go down. Okay. Hence, if you are rerunning any cell, don't rerun just that cell. You will have to rerun the entire notebook if you want to generate similar results, right? But now I will change the model again. Let's say I bring this back to the original set of layers that we had, because we saw over there that the loss was slightly higher. Okay. Now we will add some dropout. Okay. We have gone back to the original 4 layers that we have defined. Now between the layers, we are also defining a dropout. See, so in this particular, for functional Keras, this is how you can do that. Same thing that we were doing last time, right? But we have just added a dropout layer in between as well, and we have connected that with the 2 x's that we have. Okay, so you can see x equals to dropout 0.3x, 0.3, 0.3. Okay, so this is what we have added. Okay, so now we have added a dropout. I'm just giving you combinations with which you can play around. So this is the structure now. Okay, I call Adam once again, the previous Adam object only with LR equals to 0.01, and I will run this. Okay, right? So it doesn't mean that dropout will help you every time, right? If the neurons that you have defined are actually helping in predicting, if uh, overfitting is not happening in the data, then in those cases there is no need for a dropout, right? So maybe if we reduce this, let's say I reduce this to zero point 0.1 and I rerun this, maybe I get slightly better results, right? Maybe I totally get rid of this, right? Now, this is something that I want you guys to explore, okay? I will not be telling you this, right? So this is nothing, right? So for me as well, I will also have to run 10 different iterations of this model, and I will have to see which model is working best. Now, dropout, I wanted to show you that it is not that dropout will always work, will do wonders for you, right? In this particular case, dropout was something that was actually not helping us. So a dropout of zero point 0.3 didn't help us. So let's go ahead and see a dropout of 0.1. Okay. And so on and so forth. So now like this, I want you guys to experiment, right? Data frame, image ID +1, it is taking from index. So we are just doing a +1 to make sure that if it is the 0th row, we are pointing that to the first image. Yes. We have to create a model with a choice and save the out. So this is the code to do that, right? This is the code to basically whatever model you have finalized. You can finalize whatever model from here, right? If let's say I would have gone ahead with model 3, I will change this to model 3. Okay, and I will run this. This will give me the outputs. Okay, and using that, you have to save the CSV, and then I will let you know how you can submit that CSV. Okay. What about continuous numerical data? Numerical data, same thing, right? Here you had 784 features. You can have whatever numerical features you have, right? The same process will be followed. Nothing will be changed. Over here, we have used the image data as numerical data only. For image data, it is more complicated because you have to get that image data from an image format to a numerical format. For structured data, it is much more convenient. You already have your data in a numerical format. Okay, so same code, same processes will be followed. If you are able to go on to Keras, download some data sets and try working on a structured data problem, the same code should be, you will be able to work on with the same code with slight modifications. Okay, so what I was saying was that I don't know till what point you guys got, but okay, so the filters that we use on social media, right? The filters that we are using on social media, let's say you're using a filter which is outlining the figure, whatever is present on the camera, right? There can be multiple filters. There can be a filter which is, let's say, converting your normal colored photographs into, let's say, red colored photographs, green colored photographs, and so on and so forth, right? Now, there can be some, and if you go on your phone, if you go on all these apps, there are options to customize the image as well, right? You can change the contrast, you can make the image more sharp, right? All these things. So all these things are nothing but we are applying some kind of feature transformation to the image data, right? Now, let's take the example of a filter wherein what we are doing is that we are outlining the boundary of an image, right? Let's say that we have uploaded the image of a dog, right? Now, our aim over here is to using this filter, our aim is to outline the image of whatever is present in the, outline the uh, outline the, let's say, whatever is present in that particular image. If it's a dog, so we want to outline the shape of the dog, right? If it's a cat, we want to outline the shape of the cat, right? Now, what is the goal behind this? Again, because we want to extract differentiating features of a dog as compared to a cat, right? Now, for this purpose, we apply multiple such filters, right? There will be hundreds of filters that you will be applying on the image, right? So the overall aim is to, let's say that I apply 100 filters, right? And these filters which I'm applying will be going through this particular process that we are seeing on the screen, right? So convolutional layer is the layer wherein you are applying multiple filters on the images, right? Now you can imagine that only one filter, through only one convolutional filter, you might not be able to extract all the features that might be useful for you, right? So that is why we apply multiple filters on any image that is going into our model. Now, let's assume that we applied 100 filters, and out of those 100 filters, one was a filter which will outline the boundary of the shape. Whatever is present in the image, it is going to outline that, right? Now, that filter very clearly tells us that whatever input image is coming us, it has a tail, or this is the shape that it has, right? It won't know that it's a tail or something, but it will know that, okay, this is the shape that it has, right? Now, let's assume there is one more filter, which is to make the image more sharp, right? When we do that, then what happens is that the object that is present, that will become much more clearer, right? So like this, we need to apply multiple filters in this particular step, uh, convolutional layer, right? And once when we have applied these filters, after this image data proceeds further uh, to for us to do the rest of the transformations on this data, right? Now, I want you to understand over here the objective of why we are applying this convolutional layer, right? So if you see what we have been doing here, right? First of all, let's revise the concept, right? Right. I hope you are clear on why we were doing this. So this over here on the left hand side is the filter that we are applying, right? This is the filter, right? And I'll show you this in the hands-on, that how these filters actually act as simple filters that you are using on your phone as well, right? So now once when we are done with this CNN part, right, you can actually go and create filters of your own, right? How you can apply that on your mobile is something that I'm not sure of, but yes, if you can upload the image on your computer, then you can upload the image on a notebook. You can try applying multiple filters, and whatever filter you see that, okay, this is something that looks new, you can go ahead and maybe you can try to publish that as well, right, on Instagram, Facebook, right? So I'll show you how that happens. But over here, if you see on the left hand side, this is the filter that we are applying, right? Now this filter, in this particular filter, diagonal positions are marked as 1, and all the positions which are not present in over here are considered as -1, right? So diagonal will be 1, and points that are not on the diagonal are -1, right? Now this thing goes onto our image, right? Now what I'll do is that I will be applying this exact box onto my image time and again. Over here, so this becomes a 1, this is matching this, becomes a 1, this is matching this, becomes a 1, this is matching this, becomes a 1, this and this are matching, again 1, this and this are matching, again 1, this and this are matching, 1, this and this are matching, 1, right? So we have how many ones? We have 8 ones, right? And this one is not matching, so this will be -1, right? So that is why. So we count the number of points that match, right? 8 points are matching, 1 is not matching, and the value of the one which is not matching is -1, exactly. So hence this will become 7 by 9, right? So that's clear. Now that we know how to calculate this, you should extract out of this what are these filters actually telling us, right? If I come down here now, okay, let me go back to the part wherein we were. So yeah, okay. So if you see over this one, right? So this is if we apply this entire filter on this entire image on the left hand side, this is the output that we will get, right? And we had talked about this, that if the input image is of the shape of, let's say, x cross x, the output image will be of the shape of x minus 2 cross x minus 2 if your filter size is 3 cross 3 and your stride is 1, right? Okay, now let's assume that instead of instead of a 3x3 filter, I apply a 4x4 filter. Okay. In that case, can you tell me what will be the resultant output? So let's say we apply a filter which has 4 columns and 4 rows, something like this, right? 6. Okay. So how 6? Because, so if you see, input was what? I had a matrix of size 9, right? My matrix, my image was of the size 9x9. I had applied a filter of 4x4, and my output became what? It became 6x6, right? So can we derive a formula? When input is 9x9, right? Filter was 3x3. Output was what? Output was 7x7, right? Now my input remains 9x9. Filter becomes 4x4. Output will become what? 6x6, right? So basically the formula that we have is, if you have, let's say, whatever is the size of the matrix, input is, let's say, n cross n, filter is, let's say, m cross m, then your output will be what? Input minus filter plus 1. Exact. So your output matrix will be n minus m plus 1 into same size, n minus n plus, sorry, n minus m plus 1, right? So this is how you will calculate the size of the, you don't need to calculate this. I'm just telling you that this is how this will work, right? Now let's look at the output, right? So we have applied a 3x3 filter over here, and let's study the output now. Can someone tell me what is the output representing over here? Try to visualize this output and see. I want you to tell me what are these values actually representing for each and every block that we have. What is the intuition behind this output, right? How can you maybe read this? How can you tell me this, that after applying this filter, what has happened now? Probability values? No, these are not probability values, right? Try to see how these values, how we have created these values. Looks like a heat map. Yes, so that is somewhat correct, right? So if you see now this output that we are seeing, right? This is because we have applied this particular filter on this data, right? If my filter would have changed, right? As soon as I change my filter, as soon as I give some other values to this filter, this output values will also change, right? So this one, the one output that you're seeing over here is only coming because you have an input, you have applied a filter of this value, and then you have gotten this result, right? All this is telling you is, it is basically all the values which are 1 are those pixels which were matching your filter, right? So these were actually, this is the combination of those pixels which are exactly matching your filter, right? Now if you focus on 0.77, now this is a filter which was matching with the filter, but not all the cells matched, right? So there were just 8 cells which matched. One cell that was there, it did not match, right? Now looking at this image, you can very clearly say what were the pixels that were matching and what were the pixels that were not matching, right? So in a way, what will happen is that when we are applying this filter, right? Now this filter, if let's say the object or the aim of this filter was to sharpen the outlines of the image, right? If that was the aim of the filter, at the end of the day, that is what will happen over here. Only on those blocks wherein the filter shape and size were matching in the input image will you see a value of 1, right? In all the rest of the cases, you will see a smaller value or a less, or a value which is closer to -1, right? Now, all the cases wherein, let's say, the output is 1 or greater than 0.5, 0.8, those are the pixels wherein the input image is matching your filter data. And those will become the parts which the filter was exactly trying to do. If the filter was trying to outline the image, right, then the pixels with a value of 1 will be the outline of the image, right? And the rest of the pixels which were not matching, they are actually not the outline of the image. The part which is matching and the values which are not matching. Now, this is the center. This will also become the center of your output data, right? So now it will match each and every value one by one. This one will be matched with this one, -1 with this -1, and so on and so forth. And then you will get this value. What will be the value that you will be getting over here? It will be 7 minus 2, right? 7 points are matching, 2 are not matching, and 7 minus 2 will become 5 by 9, right? And that is what 0.55 will be. See, these are complicated things. Even if you're not understanding this fully, it's fine. But you should just get what we are trying. What is the main objective of applying these filters behind this, right? At the end of the day, you don't have to do this. You have to call a model which will do this. But why exactly? What is the reason that we are applying these convolutional filters, right? This is something that you need to understand to a certain extent. Okay. Again, I would not say that you are required to understand that how is the maths going, how are the different filters being defined, and all that is something that you can skip. But you should understand what is the objective of applying the convolutional layer. Okay. So now, like this, you can imagine, let's say I have a colored image, right? So what will happen is that this particular colored image, okay, no, it's okay. So now let's say that we have applied 3 filters on our data, right? So basis the 3 filters, you will be getting 3 outputs each. Am I correct? So first filter, let's say first filter that we apply, whatever it is, on the basis of that, we will be getting this output, right? Second filter, for whom the values might be changing, we are getting these values. And third filter, we are getting these values. Okay. Okay. So now we will be moving on to the next layer. I hope convolution is clear to everyone. So now we will be moving forward to the next layer, ReLU layer, right? ReLU is a function that we have studied in the past, right? If you remember, it was a function that we had applied in our deep neural networks as well, right? So ReLU function we are also applying over here. Why are we applying it over here? What is the reason behind that? That is something that we'll be seeing now. Okay. Now, rectified linear units is the full form for this function, ReLU. ReLU is a function, as we have discussed previously, right? This function activates a node only if the input is above a certain quantity. If you remember, this was the function, right? If x is less than 0, then output of this function ReLU will be 0. If x is greater than 0, then output of this function will be x only, right? So when the input is below 0, the output is 0. But when the input rises above a certain threshold, it has a linear relationship with the dependent variable. Okay. Now, if you see over here, if we feed -2 to this function, output will be 0. If we feed -6, output will be 0. If we feed 2, it will be 2. If we feed 6, output will be 6, right? So over here, we have considered a simple function with values as mentioned above. So the function only performs an operation if that value is obtained by the dependent variable. Okay. This is what ReLU did. Now, how are we applying ReLU over here in convolutional neural networks? So ReLU layer, a small but very key player in CNNs, is this particular layer, right? So its math is also very simple, as we have seen. Wherever a negative number occurs, swap it out for a 0, right? I'll tell you why we are doing this. Now, this helps the CNN stay mathematically healthy by keeping learned values from getting stuck near 0 or blowing them up towards the infinity, right? So there are 2 objectives. I'll tell you that why we are doing this in the next part, right? Okay. Now, if you look at this, what will happen? When we are applying this layer to the output of the convolutional layer, right? ReLU layer will be applied to the output of the convolutional layer. Now, the output of the previous convolutional layer was this, right? We had seen this example, center was 0.55, corner was 0.77. Okay. Now, what this will be doing, this will be actually converting all the negative values to zero, right? What if I try to understand what is happening with this convolutional layer out? All the negative values becoming zero. So what are we getting rid of from, like, what things are we getting rid of in the image? Which are not matched, yes. So those aspects of the image which were not matching this filter, right? Basically, now these points which are not matching the filter that we have provided are acting as noise in the image, right? Because I want to outline my image. I have applied a filter which will outline the image, right? But there are certain pixels in the image that are actually not helping me to outline the image. And my overall aim with this filter is to outline the image. It's not that these pixels will not be used in future. Only for this filter, because these, whatever these combinations of pixels are, they are actually not matching with the feature that I have provided. So what I will do is that I will get rid of these so that my image after this layer, right, becomes much more clearer, right? If the objective of convolutional filter was to outline the object that is present in the image, my convolutional filter, it does what? It indicates to me what are the areas in the image which are matching with this filter and what are the places which are not matching, right? ReLU layer, once when we have gone through the first layer, ReLU layer, what it will do is that it will then get rid of those areas or those places in your image which are not matching with your input feature. It will not get rid of that. It will just convert it to a zero, right? So now over here, this becomes a zero, right? Now, similar to this, what will happen is that for every, if you see now, for each and every case, what will happen is all the values which are negative will be becoming zero. Of all other features, the output of ReLU layer is of the same size as whatever it is put into, with just all negative values removed, right? So if you see, negative values will be removed to zero. Okay. So this is what the output of the ReLU layer looks like. Zero, no, zero doesn't mean nothing, right? Zero means that if you see an image, in an image, the pixels will be varying from 0 till 255, right? Now, when we have applied the when we had applied the convolution filter, then your, what happens is your 0 to 255 are changed in the range of -1 to 1, right? That's what we'll see, that that's what the image, that's what the transformation that is, that you will see, right? So 0 to 255 getting changed from -1 to 1, right? Now 0 means that the, over here, 0 means that whatever filter you have applied, right, there are almost half features which are matching, right? Zero value will come when let's say you have applied a filter of 7 3 cross 3, right? And out of the 9 cells that are there in that, 5 are matching and 4 are not matching, right? Or let's say 5 are not matching and 4 are matching. So in that case, what will happen is that the output value will be coming as negative, right? If the output value is negative, then it means that most of your features are not matching with the filter. When most of your features are not matching with the filter, then we impute that by zero. When we impute that by zero, what are we saying? We are implying that all, like, almost, so this, whatever this area is there, it is matching with your filter on a half basis, right? Zero means what? Only half the values are matching and half the values are not matching, right? But the aim over here is to get rid of all those areas wherein the mismatch is greater as compared to the match, right? If out of the 9 pixels, let's say 6 are not matching and only 3 are matching, I will convert all those values to zero, right? Because I don't need them as of now. I only need to highlight those pixels or those points in the image wherein my filter match is greater than zero. Okay. because then whatever image I'll be left with, what will happen in that case is that that particular image will be much more clearer in terms of the filter that we have applied. If we are applying a filter which will make the image sharp, then the output will be much more sharper. If you are applying a filter which will make the image as blurred, right, then the output will be blurred, right? So that is how this happens. So over here, this should have been 0, right? All the values that you are seeing from negative to positive, right, they should have been 0. So if you see, guys, what Hasmit is saying is that, let's say I focus on this is minus 0.11 and this is becoming 0.11, right? So this will not happen. What will happen is this will become 0. Okay, it's not visible, but all the values will be converted to 0. So don't worry about that. This is incorrect. I'll ask the Intellipaat team to update the deck, but this is incorrect. But this new image, in this new image, only those pixels which are matching with the input filter will be highlighted, right? And there will be some kind of a reduction in size as well, right? So if you saw, originally we inputted 9 cross 9, an image size of 9 cross 9. Output was 7 cross 7, right? So essentially we have only gotten rid of 2 pixels each for each and every row and column, right? But at the end of the day, so we are getting 2 things. One is that we are reducing the size of the image, and 2 is that we are highlighting only those pixel values which are applied on that filter, right? If the filter was, let's say, a filter which will make your entire image red, right, then that filter will have the pixel values in the range of the color red, right? Then this color will be, what will happen is that this color will be applied to all the cells, and on that basis the output image that you will have majority of red highlighted. All the rest of the colors that were there in the image would be converted to a slight red color or something, right? Yes, Amit. But again, so the point is that we will lose these features only for this filter, right? Then again, when we apply a new convolution layer, the same will be applied to the same image that we have used while training, right? So your input image remains the same. On that input image, you are applying multiple convolutional filters, right? So for convolutional filter number 1, you might be losing some features because your aim over there is to lose those features, because these features are not matching with your convolutional filter, right? But in the second case, let's say in the second filter that we are applying, those features which we had lost in the previous case, they are actually matching with the filter, right? So in that case, they will be used. Let's say in the third case, there are some other set of pixels that are used, right? So this is how we are actually trying to extract the relevant features through each and every convolution step that we have, right? So think of this image, this one, right? So each and every filter will be giving you each and every new output. Okay, so now till now what we have covered convolution, we have covered convolution, we have covered the functional layer wherein we are applying the, if you are applying a 3 cross 3 filter, the size is being reduced by 2 pixels each in your columns and rows, right? But after that, what it is doing is that it is, your image is still intact, but your image is intact from the point of view of the filter that you have applied. If the filter is a okay, so let me show you something. Okay, so if you take a look at this, right, take a look at this image. So if you see now over here, this filter that we have applied, what are we doing? We are just multiplying whatever pixel value is there by 1 by 9. That's correct. And you can see that the image, this was the image that went into the filter, and the output is a blurred output. Okay. Why is it blurred? Because we have actually, all we have done is that we have divided those pixel values by 1 by 9, right? Now what will happen over here is, you will be calculating the sum of all the 9 pixels, right? Sum of all the 9 pixels will be what? Let's say it is 9 times x. Okay, dividing it by 9, you are just left with x. So it's essentially over here, all you are doing is that you are combining pixels. 9 pixels have become 1, hence your image has become blurred. Okay. Now if you go over here, now this is a filter wherein you are making your image look sharper, right? So all for all your iPhones and for your filters that you are using on Instagram and Facebook, nothing is happening. Only this filter is being applied onto your input image, right? If you see, this was the image. After applying this filter, you are getting this image out, right? The size will be reduced, okay, and you will not be able to visualize it clearly, but this is what you will get. Now if you apply these two filters simultaneously, right, on the image, this is the image that you will be getting, the outline of the dog. Okay, so this is how filters actually work, right? These are filters in action, but this is a good example, and this is how usually you can imagine these filters working. Okay, I hope now convolution makes a little more sense. While in all these layers, right, your convolutional layer, the functional layer, and the max pooling layer, you will be applying this function only, ReLU only. But when we are connecting the deep neural network, at that point of time, you can change the function like we have done previously. You can play around with the function. But for the image transformation part, ReLU will be fixed, because all the rest of the functions will actually make your image useless, right? So if you have, let's say, non-linear functions such as a sigmoid function and all, right? So it will actually change the pixel values a lot. ReLU, what it is doing is that it is only getting rid of negative values for us, right? So that's why ReLU acts the best over here. Okay, I hope this is clear now. You can search with this SAMA, SAAMA, and different kinds of convolutional filters, and you should be able to get this link. I'm not able to. Okay, now we have done what? We have applied convolution and we have applied the functional layer on the output of the convolution, right? So value has been applied on the output of convolution. And now we are left with the third and the final part, right? Which is pooling. What is pooling? Pooling is, okay, so it is yet another very useful tool that CNNs use. It is called pooling. Pooling is a way to take in large images and shrink them down while preserving the most important information in them. It consists of stepping a small window across an image and taking the maximum value from the window at each step. In practice, a window 2x2 or 3x3 and a step of 2 works well, right? Okay, so I'll tell you what pooling does. Pooling is nothing, right? Pooling is only selecting the top features from a predefined frame. Okay, now first let me explain this. Now if you see, let's say I apply a max pooling filter of size 2x2, right? All I need to define over here is the size, that it is 2x2. Okay, as soon as I do that, what will happen is that let's say that the size is 2x2. Okay, now this filter will be applied, and let's say I give a stride of 2, right? So when I give a stride of 2, first of all, what will happen is that this max pooling filter will be applied on this. When I'm saying max pooling, what will happen is that out of the 4 pixel values, it will only take the maximum value, right? So if you see, it has taken the value of 1 over here. Now, when I take a stride of 2, what happens is that this box moves 2 cells, two pixels to the right? Now, next time I will take these 4 values, okay? And from this, what will be the value that we'll get over here? If you apply max pooling on the selected filter, 0.33, right? Yes. So you will be getting 0.33 from here, right? Now, if you see, what happens is, now the third time, this will be moving, this will be applied over here. For the fourth time, there are only 2 pixels, doesn't matter, it will apply like this, right? So it will take the value which is the highest 0.33. Okay, so that doesn't matter to pooling, but this is how max pooling will work, right? It depends upon the stride that you are giving. If you're giving the stride, so in max pooling, it doesn't make sense to apply the filter on the part for which the filter has been applied before, right? If you have applied it here and then you apply it here once again, Doesn't make sense, right? So that is why we give a stride, which is, let's say I give a stride of 2. So when we give a stride of 2, first time my pooling layer, my box started with 0.77. Next time it will jump 2 pixels ahead. From 0.77, it will skip minus 0.11 and it will start from 0.11, right? Because it doesn't make sense reconsidering the pixels which have been considered before. Now, one thing, can you guys tell me how will the output image, if let's say I take a 2x2 filter, by how many pixels, or what is the amount of pixels, percentage of pixels by which the size of the output image should reduce using max pooling? Let's say I have a 10x10 matrix, right? Yeah, and I apply a 2x2 max pooling filter. So size will become what? 1/4 directly. Right? 1/4, right, Siva? Because we are selecting only one pixel out of 4. 1/4, right? So first advantage of pooling is what? That you are reducing your image size significantly, right? 25% is only being left, right? That is the first significant advantage of pooling, that you are actually reducing the input size. Okay. Now, the second advantage, or the second advantage can be that it is again getting rid of those features which are not dominant in that particular area, right? So when I am selecting this box, I am selecting only the value 1, right? So what I am selecting is, I am selecting only that feature which is dominant over here, right? Now let's say I would have gone ahead and I would have put my pooling layer over here. I know that this entire area is actually not significant for my image, right? All these features are not matching, right? So why not I just go ahead and I just use one, right? So see, when you are looking at images, don't imagine them as images of the size of 8x8 or 10x10, right? These images will be of the size of thousands cross thousand pixels, right? When you are actually working with huge amounts of, so if I go back to that example, if I go back to this example, right? Now, if you see, when we have applied this filter 1/9, 1/9, you are still able to recognize the image. You are, yes. If we apply this filter, right, you are still able to recognize the image, right? So your input image size will be so huge that even after you have gotten rid of like 3/4 of the pixels, still, at least, if not a human, a computer will be able to differentiate, right? So don't imagine all these cases as cases wherein you are supposed to visualize. This is a computer trying to extract features, right? So it might be possible that for us, for humans, we might not be we might not be able to interpret how the image is looking like now. But for the deep learning model, which is trying to work on features, it actually doesn't make sense keeping 4 features which are of the same value, right? So what it will do is that it will just keep one feature from there, right? And it will get rid of the rest of the features. Yes, Samaya. So again, so that's a good question. Now, if I give you the if I give you the max pooling layer size of 3x3, what will happen? The first of all, if I give the max pooling layer size 3x3 and I give the stride equals to 3, right? Then in that case, my image size will be reduced by what? 1/9, right? To 1/9, right? So 8/9th part of the image will be lost for us. Now, if I change the stride to even further, right? Let's say I am ignoring, or let's say if I reduce the stride, I reduce the stride to 2, and my matrix, what my max pooling matrix is of the size 3x3. In that case, probably my image size will be reduced to a lesser amount as compared to 1/9, right? So that is something that you can visualize. Depending upon the stride and the size of the matrix, your input image will, your output image will change on the basis of that, right? One is we are reducing the size, which is obviously our aim, right? So if you remember why we came to CNNs, we came to CNNs because ANN, using ANN also, if you remember, we had done the digit problem wherein we had classified whether an image is belonging to digit 1, 2, 3, 4 till 9, right? But the limitation over there was what? That your image sizes will not be 32 cross 32. They will not be 64 cross 64, right? They will actually be much more bigger than that, right? So that is why our aim of going ahead with a complicated technique was that we wanted to obviously reduce the image size, but we wanted to keep the important features intact, right? We only want to use the important features and get rid of the features which are not useful. So you can say consider this stage as kind of a feature selection stage. Okay. Okay, so this is what will happen, right? If you see now, this is a 7 cross 7 matrix. We have applied a pooling layer of size 2 cross 2 and stride 2, and the output that you have gotten is 4 cross 4, right? Now, if you look at it, this is doing exactly the same thing that we were talking about, right? The output from this will be what? Will be 1. That is what we can see on the right hand side. Now the output from this will be what? This will be 0.33. That is what we can see on the right hand side. Then once again, this output will be what? 0.55. Over here we have 0.55. Then this output will be 0.33. And over here we have 0.33. Right? So this is what pooling will do. Ankit, again, you are moving ahead. Let's stick to what we're doing. So again, these are just different methods, right? So max pooling 2D is your image when you are dealing with image data, right? So that will be a 2D data. Average pooling 1D is whatever, if you are giving a 2D image, right? It will take the average of each and every dimension. What it will take is, if I give average pooling of 1D over here, it will take this, it will take the mean of these values and give 1 pixel as output. Then it will take the second row like this, and it will give 1 output as an example, right? So your 7 cross 7 matrix will be converted into just a 1 cross 7 matrix. And your global max pooling 3D is again for your video related data. When your data will be 3D. 3D will be when your image is 2D and when you have multiple images present in the training data. That means that you are working with a with any video related data, right? Then that means that you will be applying. So there are different variations of max pooling, right? So there is max pooling, there is mean pooling, wherein you take the mean of all the whatever values are there, right? So there are some variations. We will have a look at some, but all the rest that you have mentioned are actually much more advanced. They are required for when you are dealing with videos or when you are dealing with very huge amounts of images and you are not much concerned about preserving the shape of the image. You are just doing some classification exercise over there. I hope you are able to come to this output from the ReLU layer output that is on the left. Okay, so this will what happen. This is how your output will look like. We need to do it for all the other filters, right? So now this is key. We have to do this for all the other filters, right? For every filter, for every convolution filter, all these steps will be followed, right? Let's say we have a convolution filter 1. Image, whatever your image is, your convolution filter 1 will be applied to that image. That is step 1, right? ReLU function will be applied to the output of the convolution filter 1, right? That is step 2. Your max pooling layer or your pooling layer, whatever you're choosing, will be applied to the output of your previous function, ReLU function, right? This is for convolution filter 1. Now, similarly, if I have convolution filter 2, same 3 steps will happen and you will get the output of convolution filter 2 after pooling, right? So you can imagine that at the end of the day, we are actually ending up with more pixels than we are starting with. Because if let's say we had 10 cross 10, okay, or let's say we had 20 cross 20 as the image size, okay. So let me give you and kind of a question, right? I want you guys to answer. My input images of the size 20 cross 20, right? And I'm applying 5 convolution filters to it, and I'm applying a max pooling layer of 2 cross 2, right? What will be the output of each and every max pooling layer? We have 5 filters, right? So how will the output change, right? Okay, let's not take 20, 20. Let's take 22, or let's take 32 cross 32, right? Your input image is 32 cross 32. You are applying a convolution filter of size 3 cross 3, right? You are applying 5 convolution filters. Okay, let me write this down. Input image is 32 cross 32. Con filter is 3 cross 3, and ReLU will not change the size. Max pooling is 2 cross 2. Okay, now output, and I have 5 convolution filters. How will your output look like? I want the dimensions of the data. 32 cross 32 after the first convolution layer. What will you get? What will be the output? 8 cross 8. 30 cross 30, right? Yes. So the output from convolution layer will be 30 cross 30. Correct. Now this 30 cross 30 going into max pooling, what will be the output from there? I am giving a size of 2 cross 2, 8 cross 8, right? So Hasmit, correct, you're correct there. So the final output will be what? Will be 8 cross 8 only, right? Now this 8 cross 8 will be the output from one convolution filter, is it? Now similar to this 8 cross 8, there will be 4 other outputs as well. Okay. So effectively, if you see, your input image was of the size 32 cross 32, but your output image is of the size 8 cross 8 multiplied by 5, right? Right. So at the end of the day, what is happening is that depending, after applying multiple convolution filters, even after you are getting the size down of the max pooling by doing the max pooling and all, even after that, you are ending up with more pixels than you started with. Okay. Okay, so again, let's combine all these layers together. I think now we have covered quite a bit, right? So see, we can combine all these layers together. Input image was like this. We applied convolution, ReLU, and pooling, right? And we got these outputs, right? Now what happens in reality is that we apply these layers multiple times, right? So input image, you will apply convolution, ReLU, pooling, right? So you can play around with these layers that you have, right? There is no defined sequence. Convolution and these two should work together, right? So the function that you are applying and these two will be working in pair. ReLU and convolution will always be working in a pair, right? If you see, convolution, ReLU are together. Pooling is something that you can keep on applying, or you can, maybe if you want, you can skip pooling as well, right? So that is something. But again, these are parameters of your CNN model, right? These are not, there is no defined logic that, okay, you have to apply a convolution 2 times, ReLU 2 times, max pooling 2 times, and you will have the answer, right? You will have to play around. You will have to see that after doing all this, are you able to classify whatever you are trying to classify correctly or not, right? So this is what happens. Okay. Okay, so now what we have done is that we have seen everything which was new. We have covered that convolution, ReLU, max pooling layer, and all we have covered, right? Now all we have to do is that we have to tie everything together, right? So we have to join this with the uh, neural network, the simple neural network that we had studied, right? But before that, we have to bring this data in the format which can be consumed by a simple neural network, right? So right now, if you see, the output is still in a matrix format, right? After applying like you would have applied multiple convolutional layers, ReLU layers, max pooling layers. After that, still whatever you will be getting will be in the form of a matrix, right? Nowhere did we see that the output was in the form of rows. It was a matrix output only, right? Now this output, we need to convert it into a form which can be consumed by a simple neural network directly, right? Now then we have one more step, which is to flatten our data, right? Fully connected layer, it is the final layer where the classification actually happens. Fully connected layers take the high level filtered images and translate them into words. Here we take our filtered and shrunk images and put them into one single list as shown in the figure. Instead of treating inputs as two-dimensional array, they are treated as a single list and all are treated in a similar manner. Every value gets its own vote on whether the current image is an X or a no. Right now, if you see over here, so there is one more step that we have in between, which is known as flatten, right? So flattening step is this one. All we are doing over here is we are flattening our data. If you see this 2x2 matrix that we had actually became so this 2x2 matrix in red actually became this 1x4, 4x1 matrix, right? Now, similar to that, this one again, this one became this, right? And your last one will be again, this will become the last four, okay? So this is how your, now if you see, now our data is in a form which can be consumed by a simple neural network, right? If you remember, in case of simple neural network, we had this, right, which was going into the first layer. These were what? These were features. If you remember when we were studying about simple neural networks, your input layer will be in the form of a column only, right? And that all the values in the input layer are considered what? They are considered as features only, right? So now this is the final transformation that we do. Okay. Now till this point, right? Humans, as a human, you will not be able to recognize the image, right? Uh, Post this point, or even before this point as well, right? When you're transforming your image and all, now as humans, we might not be able to recognize the image, but your deep learning model, because it is not actually viewing the image like we do, it is trying to extract patterns, right? It is trying to apply a mathematical model on top of it and see that what features are actually. So now you see all the features that we have applied in convolution, ReLU and all, right? All the significant features. Now you would be able to see why we were doing ReLU and all, right? Because I wanted to get rid of all the features which are actually not making sense. Then why did I do max pooling? Because let's say if in a matrix of 4x4, there are features of 0, 0.5, zero point 0.5 and 1, then I only want to keep the feature which is important for me. So I kept 1, right? So all those steps that we did, convolution, ReLU and max pooling, they were in some sort of way kind of a feature selection that we were doing, right? Now that we have selected the features, we will be feeding these features as an input to the simple neural network that we will be creating, okay? And this will be connected to an artificial or simple neural network, and the connection will be exactly similar to how we actually do, right? So now this over here, after this, what you can imagine is that you can start defining your hidden layers, right? So let's say you have, from here you define hidden layer number 1. You say that this will have 5 layers. Then you once again define hidden layer number 2. You say this will also have, 5 neurons. And then on the basis of this, you can go ahead and you can define the output. Now let's say that this was a problem wherein we were classifying whether the image is of a dog or a cat, right? Now the dense connection that we had talked about before, right? Now all these will be connected, right? All these points will be connected to this neuron, right? All these points will be connected to this. All these points will be connected to this, right? So this is how your neural network will be set up, right? This is in, if you see, this is how actually your convolutional neural networks work. They are nothing but a combination of some transformations that we have applied in the form of convolution, ReLU and max pooling this, and then we are applying the simple neural network on top of this, right? So now again, same thing. Let's say you have two classes X and O, right? Similarly, we will feed an image of O where we will have certain values which are higher than others. Some values are much better than the others at knowing when the image is an X, and some are particularly good at knowing when the image is an O. These get larger votes than the others. These votes are expressed as weights or connection strengths between each value and each category, right? So now your fully connected layer. So now it becomes simple, right? All these are features. These are features. These will be connected with a neural network. Your neural network will go ahead and train itself similar to as we had learned before, right? What will happen is that it will go through the process of gradient descent. It will try to assign the best weights. It will try to find out the best weights for each and every point that you have in the feature space, and then on that basis it will tune itself. So the entire process will go on as we have seen before, right? So consider getting a new input where we have a 12 element vector obtained after passing through all the layers that we had. We make predictions based on the output data by comparing the obtained values with the list of x's and o's, right? So over here, let's say while training the model, these were the features which we had found, and by once when we trained the model at that point of time, we had gone ahead, connected a neural network to these features, and then on the basis of that we got that okay, these were the best sets of weights, right? Now for your vector for x, whatever input image is coming, what will happen is that you will be multiplying the features by the same weights that you have defined while training the model now, and whatever final value is coming will come in forms in the form of a probability value, wherein you will give the probability that this image can be the image of a dog or a cat, right? So this is how this will work for any case wherein the features are not matching. Now what this will do is that this will give you predictions for both cat and dog. It will give you the probability that yes, probability of this image being a cat, probability of this image being a dog, right? So it will give you that for both, and this is how your final convolutional neural network will look like, right? So your fully connected layer over here is your simple neural network that we have. So your input image has been transformed multiple times using convolution, ReLU pooling, convolution, ReLU pooling. Then there is a fully connected layer that is added. That fully connected layer is finally giving you the probability, right? Okay. So on this basis, we go ahead and we actually tune our CNN model, right? Now, if you remember, in ANNs, we had studied of a concept which was a function which will image data generator function, right? A function which will actually, what it will do is it will transform your images, right? It is going to rotate your image. It is going to make your image blurred and so on and so forth, right? So all those things are something, all of these are features which we actually use in CNN, because now what you want is, let's say you are given image data of dogs and cats, right? And now what you want to do is that you want to train a CNN model on top of this. Now, assuming that these photos are clicked by someone and these are proper photos, right? You have your high, just one second. Yeah. So these photos are photos which are, let's say, proper photos. The image is proper. It is not cut. It is not blurred and so on and so forth, right? But now what you want is that you want your model to be so good that when you are training the model at that point of time, it is trained on every kind of image, dirty image, clean image, everything, right? So hence we do some kinds of image transformations, right? We will be applying functions which will be taking our input image, and as an output it will give multiple images of the same image but with some feature varying, right? So one image can be a blurred image, one image can be an image wherein the cat is zoomed in or zoomed out, or the uh, cat is, let's say, uh, rotated, right? So all these cases, what you will do is that you will try to increase the sample size by doing all such transformations onto your input image, right? Once when you have done that, after that you will be sure that you are passing each and every kind of image. Now if I talk about Facebook, right, if I talk about how Facebook works, even when you are, let's say that you tagged a photo of yourself, okay, wherein you were the main part of the photo and your face and all was very clear. But now, even if you go ahead and someone tags a college photograph of yours, wherein there are 50, 60 more people in the photo, still Facebook is able to suggest that this person is you. How? Because it is seeing a pixelated version of you wherein your face might not be that big, right? But still it is going ahead, it is running that CNN model, and it is able to predict with some confidence that, okay, this might be you. And as soon as the photo comes on Facebook, you might get a suggestion, or the person who has basically put that photo on Facebook will get a suggestion that this person might be XYZ, right? So all those are some transformations that we'll be looking at once when we move on to the hands-on part, right? But from a theoretical part, I think we are covered. So this is what the theory was. But if you just if you're not sure what all layers you have to use, then you can go ahead and do a keras.layers.import star, right? Importing star will, what will happen is that you will be importing all the layers that are in Keras. Final probability that you are getting, right? So if there will be classes, right? Let's say that there are two or three classes. Okay. Now let's say if there were two classes, so each and every input image, for each and every input image, you will be giving the probability of what it might be. Probability of this being a cat is, let's say, 90%. Of this being a dog is, let's say, 20%. Right? This is how your final output will always be in case of CNN models. Okay, so when I talk about CNN models, right, because this will always be categorical, right? This cannot be a continuous. So first of all, in CNN, can you predict a continuous value? Yes. So this will be softmax. Why? Because we want probabilities over. So the in your output layer, the function that you will be defining will always be softmax. And what will be the how will you calculate the performance of the model? In cases of regression, we had root mean square error and all. Over here, what can you take? We had created a categorical neural network model, right? So you remember what was the performance criterion that we had taken? Accuracy was there, but to evaluate the model, it was what? It was something known as categorical cross entropy, right? So this is what you will be doing to, this is what the neural network will be doing to make sure that the model is doing well. So categorical cross entropy will be the loss that you are trying to maximize, right? You're trying to minimize over here. Regression problems, you are trying to minimize the, let's say, root mean squared error or mean squared error and so on and so forth. Right. So if you remember in ANNs, what we are doing is that each and every time we are trying to minimize the loss, right? So when we are trying to minimize the loss in case of a regression problem, what is happening is that you might take, let's say, a root mean squared error, mean squared error or something. But for categorical variables, for CNNs, because you are classifying images, right? So in this particular case, you will be the loss function that you will be using will be categorical cross entropy, right? This is the function that you will be using. We'll have a look at this tomorrow, what this actually does. This actually just calculates your actual and predicted probabilities and takes the log of it, and so that you have a value which you can minimize on, right? So, but the loss function that you will be using here will be categorical cross entropy. The case of convolutional neural network, just imagine, right? So in CNNs, you will always be feeding images, right? You will always be feeding images. Now, how can you give a continuous value to each and every image? Even if, let's say, you try doing that, at the end of the day, they will be considered as categories only, right? Now, image, you can classify it as anything. A dog image, you can classify as one. Cat image, you can classify as two. Horse image, you can classify as three, and so on and so forth, right? But at the end of the day, these will always be treated as categories, right? So if you want to do any continuous variable prediction, your simple neural networks will work the best for you. CNN is a special modification of your simple neural network that is only to deal with unstructured data, your image related data, right? Any image or video related data per se, right? The data that we have over here is CIFAR data. This contains 60,000 uh, uh, data points, right? So by data points, what do I mean? That it contains 60,000 photos, okay? Images, and each image is of the size 32 cross 32, right? And these are colored images. So essentially, if you look at the data, it will be, if you look at the number of pixels, how many pixels will be there? 60,000 into 32 cross 32 multiplied by 3. 3 for the three colors that you have, red, green, and blue, right? Now, the 10 different classes that we have in this data set is airplanes, cars, birds, cats, deer, dogs, frogs, horses, ships, and trucks, right? So you can see that it's not that we will just be classifying similar looking classes, right? Or things that are very similar to each other. There can be multiple types of things. There can be multiple types of living beings, humans, or whatever they are in the data. And the neural network should not have a problem in classifying those correctly, right? So over here, you can see we have different types of uh, points that we will be classifying, objects that we'll be classifying, right? Now, for each class, we have 6,000 images, right? So out of the 60,000, for each class, we have given 6,000 images. So 6,000 into 10 becomes 60,000. And this data will be splitting into train and test. This will be by default split into train and test. We'll see how. Understanding the labels, obviously now these labels that we can see airplanes, cars, and birds, this will not be true for the data, right? In the data, there will be labels that will be for each and every class that we have, right? So over here you can see airplane will be 0, your cars or whatever things like that will be 1, bird is 2, cat is 3, so on and so forth, truck is 9, right? Now problem statement, image classification using deep CNN, Keras, and also some edge detection operations, right? So that those are the filters that we will be applying. Okay, so now coming to the libraries, what are libraries we will need, right? So we CV2 we probably don't need. First of all, NumPy we will be needing, matplot, lib.pyplot we will be needing. And then from TensorFlow, we will be needing obviously Keras. From TensorFlow.keras, we will be importing data sets, models, layers, and optimizers, right? All these are functions that we will be using while we are defining the model, right? So from TensorFlow.keras.preprocessing.image, we will be importing image data generator. Now this is a function that will generate images. If the performance of the model, if we feel that the performance of the model is not good enough, we can go ahead and we can generate further images. Now there are two new functions, TensorFlow.keras.callbacks, model checkpoint, and this particular function which makes the model stop as soon as the performance stops to decrease, right? So I'll talk about these. What do these two functions actually do when we are running a deep neural network model? And yeah, so these are the ones. This collab.patches, this will not be required, or I think this will be required. This is to show the image data that we have, right? Okay, so we have imported the libraries. Now we will be defining some variables which will remain the same. You can define them here, or you can directly pass them in the function as well, right? So we are just defining it here for now. So batch size we are predefining as 32. Number of classes we are defining as 10. Epochs are 50 and number of predictions are 20. Number of predictions are 20 is used to tell how many predictions we are going to make, like what is the chunk of the size of predictions that we'll be making, right? So when we call the predict model, all the images will not be going at once. So we are just saying, just like batch size, this particular function, this particular variable will come in effect when you're scoring the model. Okay, so now we will load the data. So similar to the previous cases that we have seen, we are directly loading the data from Keras, right? So this data will be coming as X-train and Y-train and X-test and Y-test. This is pre-split into these four variables, and we are just directly reading this into X-train, Y-train, and X-test and Y-test, right? So datasets.cypher10.load data, and this will start loading the data. Okay, so now you can see that the data is loaded. Now we'll have a look at this, and first of all, see how the data looks like, how many rows, how many columns are there, right? So for X-train, let's print all the X-train and X-test. We will be printing all the numbers. So shape of X-train is what? 50,000, 32, 32, 3. So 50,000 samples are there, right? So images that we have in training are 50,000. The size of each and every image is 32 cross 32. But because these are colored, this is colored data. So hence we will be having 3 matrices of red, green, and blue each, right? So that is why we have 32 into 32 cross 3. Now, if this would have been black and white data, right, or grayscale data, you would not have had this 3 over here, right? It would just have been 50,000, 32 and 32. And if you remember, that was the case when we were working with our flower data, I think, right? The simple neural network case study that we had done, in that case, we had not seen 4 dimensions, right? But over here, because this is colored image, we are able to see 4 dimensions, right? So the 4th dimension is the basically color matrices that you will have for red, green, and blue each. Now, if you look at each and every data point, right? So you can just have a view that if, let's say, I select one image, right? Let's say I selected the 12th image, or if I select the 0 image, for each and every image, obviously the shape will be 32 cross 32 cross 3, right? Now let's try to visualize these images and see what are the different classes and how clear these photos are actually. Because since these are 32 cross 32, obviously they will not be very clear photos, but still, let's have a look at it, right? So shape of Y train is again 50,000 comma 1, right? So that's good. We have, if you see Y train, if I try to visualize Y train, what is it? It will give me something like this, right? Y train 0 is array of 6 value. And if I want to extract, okay, let's see that, right? So now what we will do is that we will, okay. So first of all, Y train 0, 6 is label, right? So 6 is label, and 6 is what? 6 is basically a frog, right? So what it is saying is that the 0th image that you have in your data is the image of a frog, right? Now, if I move it to the first image, this is what? This is 9. And 9 is what? 9 is a truck. So the second image that you have in the data is the image of a truck, right? So this is what it is saying. Now, in order to visualize our data, in order to just keep a mapping of the target labels with respect to what, so this is a list of lists, right? Target variables are not 10, right? Like the total targets that we'll be having are 50,000, but the values that they will be having will be one of these 10 values, either 10, right? Now this over here, if you can see, this is not a list. This is a list of a list. If I define a equals to 1, 2, 3, right? And I print a of 0, it will give me 1 directly, right? But if I define a equals to this one and this one and this, right? And then if I give a of 0, it will give me array only, right? Now, if I want to extract the value of this one, then I'll have to give a00. This will give me the value directly, right? So that's what it's happening here. The Y label that we have is a list of lists. If you see Y train is a list of lists, and that is why the shape is coming as to be now. Okay, 1 second. Okay, now here if you take the shape of A is a list, right? Right, and now if I check here, okay, this is an array. We'll have to convert this into a data frame first to check the shape. But if you see here, okay, len will be same. Let's not convert this into data frame, but yeah, if you look at this over here, right? Now here the shape is coming out to be 50,000, 1. Now if this would not have been a list of lists, the shape would have been something like this. 50,000, nothing, right? This would have been the shape in that case. But over here, because this is a list of lists, that is why it is giving you a shape of this, right? And now if you want to extract each and every label, you will have to refer to that one, right? Yeah. Okay, so now what we have to do is that we over here, just for our just to make it simple for us, what do each and every class represent? We will be creating a dictionary which will keep a mapping of the target label with respect to what the target actually is, right? So 0 is an airplane, right? 1 is this, 2 is this, 3 cat, 4 deer, right? So this is a label dict that we have created. This will help us to just when we are, let's say, visualizing the image, we don't want to print that, okay, this is the image of first label or second label. You want to see what actually that particular label is representing, and is that correct or not, right? So just for our understanding, we are in this. Okay, now let's visualize the data. I think it will make more sense then, right? So over here to visualize the data, what I'll do is that I will keep a variable. Let's say I equals to 1. I will keep on changing this. I will tell you how. Now image will be what? To display the image, all I have to do is xtrain I, right? So if I select, let's say xtrain 1, what will be the dimensions that will be coming from xtrain? 32, 32, 3, exactly, right? Now this is the image that we'll have to plot. Label will be what? Y train I, whatever this is, and 0, because I have to extract the list of lists. I have to extract the exact value, and then I'm printing. When I'm printing, I'm just printing the label dict label, right? So label dict, whatever is coming from here, let's say 6 comes from here. So 6 in the dictionary is referred to as frog, right? So hence we are just printing label dict label, just to see what exactly we are getting, right? Now if you see over here, this label ID is 9, name is truck, and you can see that this is a truck, right? Now over here, obviously this is an image which is of 32 cross 32 size, right? And hence it is not very clear, but again, just to, I'll show you, see, if you see, the model will take some time to run, right? So the complexity of CNNs is such that if you would have gone ahead with a slightly bigger image data, right, it would have taken 2-3 hours to train the model, maybe more. So that's why we are going ahead with only simple data. Now you can keep on changing the image and you will keep on seeing. So this looks like something of a shape, right? So any value, you can just print any value, and you can see this looks like a frog. But this is again a very pixelated photo. These are pixelated photos, and hence we might not be able to visualize this. This again is a frog. But to the deep learning model, because we are feeding our labels that, okay, this is a frog and all, it will be able to, we'll see how well it does actually. Okay. So this is again a frog, right? So you can see this is how we can visualize the images that we have.
Let's have a quick quiz question, guys. And the question is, a hybrid Bayesian network consists of, and your options are discrete variable, continuous variables, both A and B, or none of the above. Please mention your answers in the comment section below.
If you want to make a career in data science,
then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective as it is taught by IIT professors and industry experts.
Okay, so then let's start with the model building part, right? See, this is all the data that we have. In cases of CNN, the good part is that there is no data pre-processing that you require, right? So everything is image data, right? And all the pre-processing that will happen, it will happen inside your convolutional layer network model only, right? So unlike your structured data problems, right, like the ones that we had seen with other approaches, right, wherein you might be worried that your data is not clean, your variables, whatever value is coming is not correct. Unlike that, over here, in cases of CNNs, once you are able to read the data, read the image, after that, you can directly take it to the CNN model, right? All you have to do is there is only one thing that if it is a multi-class problem, you will have to one hot code the target variable, right? So that is something that is required. There are multiple ways in doing this for doing the same thing, right? So over here, if you see, to convert the labels to one hot vectors, we are using a different function, right? Okay. What is encoding, Ankit? I have shared an Excel some days back. I have given you multiple examples there. For the target variable, if it is a multi-class target variable, how do we change into a mathematical form? That is encoding. Okay, so over here we are using from sklearn.preprocessing, we are using this particular function. This particular function, binarizer, right? Label binarizer. This will do the same job as your get dummies, as your all the rest of the functions that we have used. I'll show you some of those functions as well, that it works in a similar way, right? But right now, if you see, before I take this, what was the shape of my white train? It was 50,000 comma 1, right? Now, after taking my white train through this function, first of all, from sklearn.preprocessing, we import the required function, label binarizer. Then all we do is that encode equals to label binarizer. This is a variable that we have created of this type object. And now we are doing is that we are calling the fit transform to binarize this data, right? So encode this data, binarize this data, dummy variable, all the things are same. Right now, if you see over here, same thing will happen, is that you will be creating multiple values. Now, if you remember, the first value was what? First value was the value of a truck. Truck was what? Truck was the 9th value. So you can see that all the rest of the positions are 0. Only the 9th position has a value of 1, right? Then I think we checked 11. 11 was what? 11 was maybe, I think, a car or ship or something. 111 was a frog, I think. So yeah, so whatever class this would have been, it is representing that, right? Now, if you see, two categorical, one hot encoder, get dummies, all will be doing the same thing, right? All of the functions will be doing the same thing, which is which over here this particular function is doing, label binarizer. So that is up to you. You can go ahead and you can use whatever function you want to use. Okay, now over here, if you see, if we do the same thing, right? Now, y equals to 0, 1, 2, 3, I call get dummies by, right? This will do the same thing. I can also call the one hot encoder. The only thing is that one hot encoder will need your output to be input to be in a list of list format, right? Now, if you see over here, this is also doing the same thing. So all these functions, label binarizer, one hot encoder, get dummies, all these functions are actually doing the same thing, right? So it is up to you what function you want to use. You can select one function of your choice and keep using that. So that should not be a problem. Okay, so now we have done all the data transformation that was required, right? So as I said, for convolutional neural network models for image data and all, obviously there is nothing. All you can probably see is that the images that you have don't have noise. The images that you have are not blurred, right? That is the only data quality check that you can do, right? Other than that, once when the images are fed to the model, after that there is no specific transformation like missing value imputation and treatment of outliers and all. This is all these are things which are not required in case of a CNN model. Okay, so that is the good part. All you have to do is that you have to just transform your target variable if it is a multi-class problem, and then you're good to go, right? And then we can start working with our framework of the neural network of the CNN model. It will read all the images, so there is an option which can be defined wherein all the images will be read as a single number that you have prescribed, right? Let's say that you want to read each and every image as 1024 into 1024, right? So it will do that in that particular case. Even if the images are different, right? That is not a problem because your different images having different features, they will go as multiple features, right? So one image which has, let's say, multiple features, for that what will happen is that multiple features can go, right? But yes, that is something that usually you should keep in mind, that the size of the image should usually be in a given range. It should not be that the sizes are varying quite by much, right? If let's say there are one image which is 1024 into 1024, and then there are some images which are, let's say, uh, super high, like the pixels are very very high in those images, right? So that is something that will cause a problem. But if other than that, if the images are in the same range, right, then it should not be a problem. But as a precaution, you should always keep photos, images, or whatever data you have which are of a similar size. Okay, so now we come to creating the model part, right? Now, while creating the model, again, all we have to do is that we have to test out with different layers. We have to keep adding different layers, and then we need to see how the model is responding. Data scientists, from wherever you are getting the data, you will have to tell them the specification that this is what I'm looking for, right? I want to have photos in a given range only, images in a given range only, and that is something that you should get. If you're working on a project on your own, in that case you should make sure that the image, whatever images you are having, are of the same shape, right? If not, if let's say that there is slight variation, then there can be some parameters that while reading the image data, you can maybe define those. But other than that, there is nothing much that you can do over here, right? So from as a data scientist, you will have to ensure that the images that are showing in are of similar shape and size. Okay, right. So now creating the model, right? We come to creating the model, we will be defining multiple layers, right? So over here, this is the first testing that we are doing, right? So I'll be starting with a model which is giving us a decent performance, and then I'll be showing you some variation if I keep on changing the different parameters that are there, right? So we will first see how we can get the best performance out of this model. This might not be the best performance, but this will be a decent performance. Then we will see if by changing each and every function, activation functions and all, how the model performance will keep on changing. Okay. Now, what we are defining over here is that first step, we are defining a convolutional layer of 32 feature maps with a size of 5 cross 5, right? So if you remember the filters that we were talking about, over here we are giving 32 filters, and each has a size of 5 cross 5, right? The function that we will be using will be the rectifier function, ReLU, right? This will be followed by batch normalization layer. We have gone through batch normalization when we were talking about simple neural networks, right? So we are applying the batch normalization layer as well over there. Others, okay, so see, batch normalization is nothing. It's just that between each and every layer, you are adding a normalization layer which will normalize your inputs so that they are coming in a given range, right? So otherwise, what happens is that it might happen that because there are so many layers that we are having convolution layer, max pooling, and all those, because of which what will have happen is that sometimes some values might be tending to such a small value that gradient descent might not be able to tune them, or sometimes some values will be in such a high range that gradient descent might not be able to tune them, right? Hence, just to be sure, just to be safe, what we do is that before feeding the output of a previous layer to the next layer, we standardize the data, we normalize the data. And that is what the batch normalization layer does. Exactly. Yes, right. So that's what batch normalization does, and we'll be testing that over here. Then again, we are adding a convolutional layer of 32 feature maps, same size 5 cross 5. Then we are adding a max pool layer, right? Then we will be adding a dropout layer at 25%. Okay, so let's do one thing. First, let's start with this only, right? We will not be adding any more layers. Okay, let's add just one layer and see the model performance to avoid overfitting this. So dropout is nothing but you will be randomly deactivating some of the nodes, right? You will be randomly deactivating some of the neurons and then see. So this is because see, in cases of a convolutional neural network, we are defining multiple neurons. It might be the case that you don't require each and every neuron. Each and every feature that is coming from the image might not be required, right? So it is kind of a feature selection technique as well over here. So that is why we are applying dropout as well. Okay, so now first let's start with a network which is as small as this, right? All we have done is that we have applied only uh, one convolution layer. So let's apply at least two convolution layers, right? So we have applied two convolution layers. Now, if you see batch size over here, right now we are giving as none. Model becomes your sequential model, same as your simple neural network, right? On top of the image. So there will be 32 such filters which will be applied, right? Now this again is a parameter which you have to tune, right? So you can start with whatever, you can start with 64, but you usually start with a lesser number of filters and see if the model is doing good. If let's say it is not performing well, then you go ahead and change the number. You maybe add some more filters, right? So that's how the process is. Okay, so first what we are doing, we have defined the models at models.sequential. This is the same thing, right? That we have done previously as well. Nothing changes here. Now in model.add layers, now these are some new syntaxes that we are seeing, right? Previously we have not seen this. But if you see, the syntax remains the same like dense one. Model.add. Last time we had done layers.dense. This time we are doing layers.convolution 2D, right? Now, obviously, we know that in a convolutional neural network, we usually start with convolution. So convolution 2D. I am giving 32 filters and the size of each filter is 5, 5, 5, right? Padding equals to same. I'm coming to that. Activation is ReLU, right? So the function that we are using over here is ReLU and that will always remain the same. Input shape is xtrain dot shape, right? What will this be? This value will be what? This one, right? 32 comma 32 comma 3, right? So that is the input shape that we will be getting, right? So that is the shape that we are getting over here. Now what is padding equals to same, right? Now what happens is that when you're doing max pooling, or when sorry, when you are applying the convolution filters and all, what happens is, let's say I take this example and let's say I have a 5 cross 5 matrix, right? Okay. Now, if I'm doing this and when I apply convolution, what happens is that, so when I'm applying convolution, what will happen is that this particular pixel will be at the center, right? If you see, this particular pixel will be at the center. This one will be at the center, right? When we are applying a convolution filter of this value. Okay. Now, because of this, what happens is that, see, each and every time when you move the convolution filter, every time what will happen is only the inner pixels will be at the center of this, right? Only these pixels will come at the center of the convolution filter. The other, these ones will not come over here, right? So if you see these, all these values that are these values will never come at the center of the convolution filter that you are applying, right? So we want that. Why? Because see, we are trying to match the patterns. It might happen that if we just put our convolution filter somewhere like this, right? It might happen that this part would match the filter, right? So in order to not skip that, what we do is that we give an option which is to pad the data, right? By padding, what we mean is we add one row, two rows and two columns each, right? So if you see, we create an additional this thing over here, and now what happens is, so for each and every one, you can imagine that this will increase, right? This will become something like this, and doing just for this one, and these will be populated with zero values, right? No values will be, these will be populated with zero values. But now what you can do is that now you can apply your convolution filter with your center pixel in with your cornermost pixel in the center as well, right? Now if you see, this will also be coming in the center of the convolution filter that you have defined, right? So this is padding that we usually do, right? So in this case, our data was very small, 32 cross 32. So we went ahead with padding. Now let's assume you have a huge size data, right? 1024 into 1024. In those cases, probably you're not that worried about extreme pixels as well, because you will know that whatever object that you are trying to detect, it might be placed at the center of the, or even if it is not at the center, the probability of important pixels being towards the end of the image might be less, right? But over here, the size of our image is very small, 32 cross 32. So we obviously don't want to drop out any of the pixels that are there, right? Now, if in a 32 cross 32 image, we are dropping out the corner pixels, then we are dropping off, I think, at least how many, 16, 17 pixels in total, right? So that will result in loss of data. So hence we do padding, right? So that is the concept of padding, which we are doing over here. So this is a safe option. You can always, whenever you are working with convolutional layer networks, you can go with this option, padding. And when you're doing padding equals to same, it will, the outer rows and columns that it is creating, it will give zero values to them. So now, if you see, first layer that we added was what? Convolutional 2D. We have passed all the parameters. Second layer that we are passing is the batch, is the standardization layer, right? So we are calling this particular function normalization, batch normalization. This will normalize your output. Okay, so batch normalization. Then we are calling a max pooling layer of 2, 2, right? Now, if you see this 2, 2, again, you know how this will work. Then we are adding a dropout of 0.2, and then we are adding one more convolutional layer. This time we are increasing the filter to 264, comma, then size remains 5, 5. No, Ankit, in all cases, it will be two rows each, right? Whatever is the size of your matrix, how can you pad that data? Just try to visualize this, right? Be it 3 cross 3, be it 5 cross 5, be it 1000, 1000. Every time you will have to create two additional rows, one on top, one on bottom, and 2 additional columns, one on right, one on left. Okay, so you will be needing only 2 rows and 2 columns. You won't be needing that. All you have to do is that once you define padding and all, it will be done for you. Okay. Now over here again, if you see, we are defining a convolution layer. Filters are 64, size is 5x5, padding is same, activation is ReLU. Over here we have not given the input shade because this will be taking the output from the previous layer. Okay, then we will move on to the dense layer that we have, right? So this is the simple neural network that we had we talked about previously, right? So first of all, the output we will be using flatten, layers.flatten. Okay, so model.add layers.flatten. This will again flatten your data. Then this becomes a simple neural network model for me. I am adding one dense layer of 256 neurons. Activation becomes ReLU. Model.add, this becomes 0.5, and my, let's say I change my activation to sigmoid, right? I'm not using softmax for now. Let's see what will happen if I give an incorrect activation over here, right? So let's see if the network runs or if it gives some error, what is happening. So we'll just check that. Okay. So we run this and we see the summary, right? So if you see, these are the number of parameters that this particular neural network model, CNN model, will require to train, right? For convolutional layer, it will have 2432 parameters, right? Batch normalization, it will have 128 parameters. For the second convolution layer, it will have these many parameters. Batch normalization again, and then for the dense layer, it will have these many parameters. And the output again, it will have these many parameters. So these are the parameters. Now over here, I have defined how to calculate these parameters. You can go ahead and you can read that. This is the same thing that we have done before, right? If you remember how we had calculated the number of parameters for each and every layer, right? So this is the same thing. So just go ahead and read this. Now these are the different layers that we have added: convolution to deactivation, max pooling, dropout, dense. These are the explanations of that, right? And now we will be moving on to the compiling of the model part. Okay, so now we will be moving on to the compilation part. We have defined the different layers in the model, right? Model.add is done. And now we will be moving on to the compilation part. So Hasmith, usually what will happen is that you will be applying multiple convolution layers, right? There will be multiple convolution layers that you will be applying in your data. So that is why we usually, what we do is that we apply, because see, these filters are acting as features, right? Now first convolution layer, maybe that will extract some features. Now second convolution layer will also extract a combination of the previous features. It will create some features might join together and act as one, right? So hence we are applying multiple convolution features, and then we will be so you try to add as many convolution layers as you can, right? As you are required to do so. Hence it is not always that you just need one convolution layer, right? Batch size you can define as well. We will do that, but even if you're not defining, in cases of CNN, it will continuously keep on calculating the performance, right? Okay, now optimizer, right? It is the part wherein we will be compiling the model. Adam we are using, right? In optimizer, we will be, for gradient descent, we will be using this Adam. Learning rate we are defining as 0.001. Okay, this is a very critical parameter. And this beta 1, beta 2, and this epsilon, right? What are these? These are the weights of the previous iterations. Because if you remember this particular gradient descent technique, what it does is that it gives weightage to your previous momentum, right? It will take previous momentum into account. Okay, so for this particular iteration, if the learning rate is 0.001, right, then it will also keep in mind what has happened in the last 3 iterations. So let's say that in the last iteration, the gradient descent moved in a specific direction, right? So it will give a weightage of 0.9 to that one. Okay, now the iteration which was last to last, it will give a weightage of 0.99. And the iteration which was third last, it will give a weightage of this much. Right? So these are the parameters that you have with Adam. And these are the weights that you will define to the previous iterations that will be considered for the next iteration. Okay. Now for model.compile, we are passing these three values. Loss will be this one, categorical cross entropy, because we have categorical variables over here. Optimizer becomes opt, which we have defined over here, and metrics become accuracy. Okay. Yes. So optimizer, if you see, we have defined the learning rate as 0.001. Now, Adam, if you remember, Adam is a technique which also gives weightage to previous. So this is adaptive gradient descent with momentum, right? So what this will be doing is that this will also be, so let's say that you are at the fourth step, right? And you have to proceed in a particular direction. Now, what Adam will do is that Adam will also keep in mind the previous three steps. What have you done in the previous three steps? Have you gone down? Have you gone upwards? Have you gone left? Have you gone right? Right. So, in order to capture that value, we are defining these parameters, which will tell Adam that for the for the last iteration, whatever you had done, let's say that you had moved in a certain in a particular direction, right? So give that direction 0.9 weightage and include that in this times direction. Beta 2, the last to last one, you give that 0.99 weightage and include that in this one. You will always have previous iterations, right? It cannot be that you will not have previous. For the first iteration, you will not have previous. In those cases, these parameters will not be used. What happens is that a certain part will be the direction that is coming from the current state, but a certain part will also be coming from the direction of previous states. If you only want to use a gradient descent technique, which is only focusing on the current state, you can go ahead with your typical gradient descents that you have, your stochastic, your batch and all, right? But Adam actually works well because keeping previous iterations in mind, it actually has worked well in the past, and it converges in a faster way, right? So that's why Adam is a preferred gradient descent technique over here. But yes, so Adam, it will give weightage to the current iteration as well as previous iterations as well. So in those cases, Ameya, it will take the default parameters, right? If you look at this, this will have to open in tab, I think. Yeah, if you see this, all these values will be taken by default if you're not passing anything, right? So that's not a problem. Even if you're not passing, it will take default values. Okay, so now this is the compilation part. Over here, if you see, we have parsed the loss function, optimizer, and the metrics. Okay, now let's go ahead and see the summary once again. So summary almost remains the same, what we had seen previously. Obviously, it will remain the same. Till now, we have only compiled the model. We had just given the compilation metrics, right? Till now, we have not parsed any data. These are parameters, right? You can play around with this. So there is no logic. Logic is that, yes, if you want to give previous iterations a higher weight, you can give those values. If you want to give an equal weight, you can give those values as well, right? So these are parameters which need to be tuned, so these are standard values that are given, because usually when you're working, usually what you see is that last 3-4 iterations, whatever direction it is having, right? So these are problems in multi-dimensional plane. These are not single dimension problems, right? So it might not be the case that each and every time you are stepping down, right? We are trying to visualize it that, okay, I'm trying to descend a hill, but you try to visualize it in a way wherein you are trying to descend a hill in a multi-dimensional plane. Now the previous iteration might be in the x dimension, right? The previous to previous iteration might have been in, let's say, the Z dimension, and the third last iteration might have been in the, let's say, Y dimension. Now, if you are only focusing on the current dimension, then again you are losing track of the previous dimensions. Hence, we are giving a higher weight to previous dimensions as well, because for a multi-dimensional problem, just try to imagine. I think you would have seen movies like Matrix and all, right? So when you are in a multi-dimensional plane, right? So it is not three dimensional like we are seeing, right? It will be multi. Any error loss, your error loss can happen in any dimension, right? So for that, we are trying to give a higher weightage to previous dimensions as well, because the final result will be a combination of all these dimensions. Okay. So now we come to the, so see, till now we have not passed any data to the model. That's correct, right? So no data has been passed. So now we will prepare the data. If you see, we had not we had not standardized the data, right? So over here, we will standardize by following the same operation that we had done before. Xtrain and Xtest, we will convert to float and divide by 255, right? Why are we doing this by 255? Because this is again image data, pixel data, and all the values will be in the range of 0 to 255 only, right? Okay, great. So now we come to the two new functions, this stopping and the model checkpoint, right? Uh, okay, now see, we are using two new functions from tensorflow.keras.callbacks. We are using model checkpoint, and we are using this one, uh, the early stopping function, right? Now, these two functions, what are they doing? How they help us, right? First, coming to this function, right? Uh, so this particular function, right? What this will do is that if we add this particular function, stopping callback to the fit function is going to stop the training. If the val loss is not going to change even after 0.001 for more than 10 continuous epochs, right? So if you see what are the parameters we have passed, I will tell you on the basis of parameters. The stopping function that we are seeing over here, it will, so let's say that you have given 50 epochs to the model, right? But what happens is that by applying this function, the model will be keeping a tab on the model performance. Now, let's say that after 25th epoch, right, your model loss is not decreasing. Your uh, validation loss. So if you see monitor, what this particular function will monitor is your validation loss. Minimum delta is 0.001. So I am saying that if my validation loss stops decreasing, right, by any value greater than 0.001, and this happens for continuously 10 times, patience equals to 10, right, then you stop the model then and there. Then it means that I have given an epochs which are high in number, right, and I probably did not require the model to run for 50 epochs, because in 25 epochs only I was able to come to a validation loss value which is not changing now, right? And so this patience that is there, so this, what this will do is that this will wait for 10 epochs. From 25th epoch it will wait till 35th epoch, and if it sees that still the validation loss is not decreasing by a minimum of 0.001, then it will stop the model then and there, right? So this is a very useful function, because when you are tuning CNNs and all, you don't know what is the correct parameter. So this will actually assist you in coming up with a good value of the number of epochs, right? Now, similar to this, model checkpoint is what? Model checkpoint is going to save the weights whenever val loss achieves a new low value, right? Now, if you see, each and every time the my neural network is running, my performance actually fluctuates each and every time, right? So it might happen that in the 25th epoch, I'm getting the best sets of, I'm getting the best set of weights, and the validation loss is minimum for that, right? So what this model checkpoint will do is that this will save the weights for the best epoch thus far, right? So whichever weights in your model are achieving the lowest validation loss, right? So those weights should be saved. Usually this should be the last epoch only, but there are some cases. So let's assume that you have given, that you have run the model for a high number of epochs, right? Now what will happen is that beyond a given point, your validation loss, which was decreasing till now, will start going up, right? If your validation loss starts going up, what do we call that particular phenomena? Overfitting, right? Now that is the point wherein you know that your model is actually fitting your training data more. So this particular model check weight function, this will save the weights for the lowest validation loss directly, right? So even if your model is, let's say you have run it for a huge number of iterations, your epochs are high, right? Overfitting, even if it is happening, it will still save the best weights for you. Okay, so these are the two functions that we're using. Okay, model checkpoint and this stopping function, and this over here we have defined the objects for these two functions. Now we just reshape our data just to check, but we know that the data is in this shape only, so no worries, but still we have reshaped the data, and then finally we go ahead and fit our model, right? Model.fit, I am passing x train, y train, batch size I have given 0 as of now. I can increase that as well, right? Epochs equals to epochs, the number of epochs that we had defined previously. Validation data is x test and y test. Shuffle equals to true, each and every time data will be shuffled. Verbose equals to 1, print. And in callbacks, if you see, I have added these two functions, right? So callbacks are those functions which will stop the model uh, before as compared to what parameters you have defined. But this will stop the model only if a certain criterion is met, right? So these are the callbacks, and then we are plotting the history. I will run this now. This will take some time to run, and once it completes, I think then we can see multiple iterations, right? So this model, again, because we have used a sigmoid function, maybe we will not be able to get a good accuracy over here, right? We will see how well this is doing, but again, that is something. This is run, right? And you can see that the accuracy that we are getting is decent, right? But some overfitting is happening. If you see, your blue line is this is your loss for train, and the second line, the haphazard line, is the loss for your test data, right? Now, test data loss will usually fluctuate like this only, but effectively it should be going down. Right now, you can see that somewhere around 20th epoch, the test data validation loss has started going up again. Right now, this is again something that we will have to look at. But your overall loss was going down, hence the model was actually going down. Right, and your test loss was also changing. That is why it was the model was not stopped. Right, so model was not stuck in a minima, right? Hence, it kept on running. But over here, you can see that the validation accuracy that we have gotten is somewhere around 74%, and train accuracy is around 84%, right? Okay, so now what we will do is that we will try to tune this model even further, right? Now we will change the sigmoid to okay, so let's change the sigmoid back to softmax and see what happens now. Okay, we will keep the layers as constant. Okay, whatever layers we had defined, we will keep them the same, and then we will see what happens if we just change the sigmoid to softmax. Okay, so I will run all these once again. Right, your optimizer remains the same, your cross entropy remains the same. So this I will not be doing again because this will again divide by 255. So standardization is not required again. This data is in the same shape only, so no worries. Now we will run this again and we will see what's happening now. Okay. Okay. Now to the questions. Model checkpoint, right? So model checkpoint is nothing but yes. So model checkpoint will see every time what happens is that your neural network keeps on updating the weights, right? Now the weights will keep on changing. Now, what if you got the best model in an epoch which was somewhere in the middle? Because if let's say you have given a high number of epochs, your model will start fitting to your training data more, right? Now, on the basis of that, see what we are doing over here is that we are monitoring validation loss wherever the validation loss is minimum till now, right? So let's say that till the 10th epoch, validation loss was minimum for the ninth epoch. So it will save the weights for the ninth epoch. Now let's say at 20th epoch, I get the best validation loss till now, right? As soon as I am getting the best validation loss on 20th epoch, whatever weights the model had, whatever weights and biases that we were defining that the model had for the 20th epoch will be saved in the model checkpoint, right? This is the file wherein this will be saved. Okay. So this is what validation loss, this is what model checkpoint will do. It will monitor validation loss and it will see wherever the validation loss is coming to be a minimum, it will save those model weights. Now, by saving those model weights, what I mean is that it will save that particular model to be scored for future times, right? So that will be the final model. Now, let's assume after the 20th epoch, there is no epoch wherein the validation loss has gone beyond what you saw in the 20th epoch, right? Then it means that the model checkpoint will save the model object as the weights that were coming from 20th epoch, right? So even if your model, let's say, starts to fit more on training data and starts to give a decreased performance on validation loss, still the best model will be saved for you, right? So that is the purpose of model checkpoint. Okay, and padding, right? Padding. So let me give you an image. It will be better. Right? Now, if you see, if you look at this image, so this is what padding does, right? If you see, the main data that you have is which one is this one, the one which is inside, right? What padding will do is that padding will add these rows as extra, okay? And these columns as well as extra, right? Now your data is actually cocooned by two rows and two columns, right? Now, every time you apply any filter, let's say I apply a convolution filter over here, right? Right. So you can see that what will happen is, let's say I apply a 3x3 filter. What will happen is each of your pixel value will be coming in the center of the convolution filter each and every time. Previously, they were getting skipped. And why is that happening? Because we have added these extra rows and columns on top. Okay, so that is what is meant by padding. Okay, now this 0 to D is nothing but two decimal places. So this will, okay, so the name of the model file that will be saved will be this, right? H5 is what? So the deep learning models are saved as dot H5, right? So that is the extension that you will have. Now this is the name of the file that I'm giving, Cypher CNN checkpoint. Epoch 0 to D, that is your epoch. Whatever your epoch is, let's say this is 25th epoch, 50th epoch, whatever, this will be till two decimal places. Underscore validation loss, right? So this will be till four decimal places, right? So you are creating a file name which is defining the epoch and what was the validation loss that you got in this particular file, and this particular file will be saved. Okay, so now you can see that once again, over here, your performance is slightly better, right? As compared to your, when we were using the sigmoid function. But you can see that there is not a very huge change, right? Why? Because see, sigmoid is again a function which goes in the range of 0 to 1 only. Now, instead of sigmoid, if let's say I would have gone ahead and I would have used a step function, right? That would actually have decreased the model performance very, uh, like that would have decreased the model performance. Why? Because now my probability will either would have been 0 or 1, right? So that's why sigmoid was able to still give us predictions which were good. Softmax is giving us the best predictions. It is the correct function that we can use, right? But if let's say I would have used some other function which was a unit function or a step function, in that case, we would not have gotten a very good output. So you guys can go ahead and try that, right? Now, what if I add all the layers back? Okay. Okay, one second. So we have seen this in our train data, this model performance, right? Now let's look at this in the test data as well. Okay. So now if you see, this was the previous model performance using the sigmoid function. Okay. Using sigmoid. And this is the model performance using your softmax function. Accuracy is better, right? It is 3% better almost. In case of sigmoid, it was 74%. In case of softmax, it is 77%, right? Okay, so that is the performance over here. Now let's go ahead and let's run the complete model. Okay, we will uncomment everything which we have done, and now we will run the model once again. Everything remains the same. Optimizer is same. Model.compile is same. We will not standardize. This will remain same. This will remain same, and we will run our data. Okay, now this is the full-fledged model that we are running now, and we will see how this one performs. Okay, and then we will see the performance comparison in this. So every time you need to get a probability number, you will have to use softmax only. Sigmoid, you are not using directly sigmoid because see, softmax function takes the weights of the final neurons and converts those into probabilities. And sigmoid function, it just gives you a value in the range of 0 to 1. So you saw here that even sigmoid will not be very far off in terms of performance, but that is not the correct way to do things, right? Sigmoid in output layer is very very it is not frequently used, right? So if you know that anything that you're predicting, any value, tangible value, not a probability, is in the range of 0 to 1, you can go ahead with sigmoid, right? Otherwise, you can go with any of the normal functions that are there, right? So for regression, if your value is in the range of 0 to 1, you can go ahead with the sigmoid. this model's performance is 0.773, 77.3. This model's performance is 77.2%. This one is 74%, right? But at the end of the day, this is a much more stable model. Why? Because your training and test loss both are actually in the same range, right? Now, do you guys feel that increasing the epochs, we could have reduced the performance even more? We could have reduced the loss even more. Now, all these things I want you to test out, right? If you see over here, this curve is still going down. We stopped at 40 epochs, right? But what if I would have given 60 epochs? What will happen then, right? So all these are questions that you should be asking, right? Now over here, your validation loss and your train and test loss are somewhere around zero point 0.7, right? But it is still going down. It is stabilizing, but it might still go down. So what if I go ahead and I check with FOX equals to 60, right? So all these things you will have to, as a data scientist, you will have to do, right? So your deep learning models are not models which you can just create and you're set, right? You will have to tune them. Tuning all these models takes lots of time. But once when you get a tuned model, a stable model, you can obviously use that model for calculate for complex predictions, like such as this one. Now over here, if you see, the image data that we have is actually not very clean data, right? It's clean data, but it's a very pixelated form. Even then, your model is able to classify. Even then, your model is able to give you an accuracy of around 77%, right?
Let's have a quick quiz question, guys. And the question is, the bidirectional feedback loop helps link the computer modeling with, and your options are cognitive science, human intelligence, heuristic processing, or artificial intelligence. Please mention your answers in the comment section below.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Now, I was expecting questions like, why is the accuracy not greater than 77%, right? Because why are we fine with 77%? Now, the reason for that is that obviously in your data, you have a pixelated version, so all your features are not very clear, right? So this is the best that your CNN can do. Might be that you would be able to get this accuracy up to 80% by increasing epochs, by tuning the parameters and all. But the remaining 20% that you will never be able to achieve with this set of data, because your pixels, your image quality is not that good. Now, if you have the same images in a higher quality, wherein more features are clearer, right? Now, in those cases, you will see that your performance can actually be increased till 90, 95%, 99% as well, right? So that is something, these are questions that you will have to ask, and these are questions that you will have to see at how to answer them, right? So this means that your model is not able to reduce the loss beyond a certain point, right? Beyond zero point 0.6, it is not able to reduce the loss, right? So it can be two things. Either you have not given the correct parameters, either you have not given the best set of epochs, or it can be that your data, whatever data you have given, it can give you an accuracy till this point only. You cannot go beyond that. But that is something that you will have to test. And once when you are able to see that after changing all the parameters, your loss is not going down further, then it means that yes, this is the maximum that you can do. And now this is a limitation of the data that you have, because of which you are not able to get a better performance. See, 38, 39, 40 validation loss was going up, but then it came down again, right? So this happens because again, your weights are constantly changing, right? Your data is being shuffled because of that. But if you see, the trend is actually going down, right? From that point of view, if you would have seen over here, right at zero point 0.5 to 10, right? You will see that the loss is going up, but eventually it is coming down only, right? So you will have to look at the bigger picture in order to see it can be anything. It might be that this is the best loss that you are getting, But all these are things which you will have to test. You cannot say that this is the best loss you are getting without testing with data, right? If you want yourself to be a data scientist, you will have to validate everything by data only. You cannot assume that, okay, this will not go further, because till 40, I can think that it is the maximum that it has gone. You will have to validate that with data, right? If you run with 60 epochs, maybe you will see that after 40th epoch, the validation loss starts going up, right? Then you will be assured. So nothing that a data scientist will do will be a guess, right? You will have to extract these insights on the basis of whatever data you have. Baseline for module 3 assignment. Okay, let me check that. You're talking about this one. So what do you mean by baseline? Oh, yeah. Okay, I'll wait for your answer. Ankit is saying in MNIST data, we have to make it as a label data, sequential or functional. Okay, 1 second. So see, module 3 assignment is what? Consider yourself to be Matt, who is a deep learning engineer at a prestigious firm. You are asked to look into wine fraud. You'll need to you have all this. We will use the wine data set from the UCI machine learning repository. It has various chemical features of different wines, all grown in the same region in Italy. But the data is labeled by different possible cultivars. Okay. Task to be done, you will need to import the data set, split your data into training and testing. You can do that. To scale your data, you can do that. Train your model using scikit-learn's objects, estimator object, by defining the fit the training model. Use predict methods to get generations. Right? Extract the MLB weights and biases after training them. Okay. So this will be a sequential model only, right? You can go ahead and you can basically you can take this as a sequential model only. There is no need for a functional model over here. So we have to make it as a labeled data. This is labeled data only, I think. What do you want to predict? You want to predict to look into wine fraud that has occurred recently. See, if you see this variable, I think the column A, this will be a binary variable, should be 1 or 0, right? So once when you do this step A, you will know you need to get your data set. You need to basically explore your data then, right? So once when you explore your data, you will understand that this will be the binary variable that you have to predict, right? So again, this becomes a problem wherein you have to predict the classes, a classification problem, right? Okay, so in MNIST data, you have used xtrain, ytrain, xtest, ytest. While explaining this line, you mentioned the shape of this data set. This data set should contain around 60,000. How many rows were there in this data? Can you remind me? 70,000, right? Yeah. So this data should contain around those many rows in total, right? But now, if you will go ahead and if you will use this particular syntax, it should split your data by default. So the function which is load data, in this function, if you are passing 4 data frames, it is going to return the splitted data. Else, I'm assuming if you're just passing this one data set, all the data would be returned at one, right? So all these things, Ankit, you can explore, right? You should not wait for me to do this. You can explore and then you can let me know that this is something that is happening. You could have done this, right? You can check the shape and all. I have given you all the functions regarding that to pull out of range. So it has returned only two data sets, but you are not sure what they are, right? This is a tuple. This is array one. If you take the, let's see if we can take the shape of this. Let's see the len. Len is 2, right? So there are two. Okay, so this will be your train and test, but this will be in tuple, right? So let's look at the definition of this. Okay, this is the function that you're calling. This is the path. See, this is supposed to return x train, y train, and x test and y test, right? Now, if you're not passing if you're not passing 4 data frames, what will happen is that all these 4 values will be returned to one data that you are pointing it to at, right? And now that is what is happening over here. If you see this data set that you have, right? This is a tuple. Now, when you're doing data set 0, it contains your X train and Y train, right? When you are doing your data set 1, it is containing your X test and Y test. So if you want to do it like this will be a more complicated way of extracting your data, right? So I'd suggest go ahead and do this only, which was shared in the notebook. If you want to explore more, go and take a look at the function. What is the function returning, right? If the function is returning 4 separate uh, features, right? See, if you see over here, the function returns 4 separate data frame. That means that if you give the same as input over here, that's what we have given, right? Then you should be able to get all these values correctly. Okay, so see, your ANN is for your structured data, right? ANNs will not be used for image detection and all. Majorly, if you look at, yes, so you guys are correct. Your text data, handwriting prediction and all, ANNs can do that. But if you remember, CNNs will be able to do that in a better way, right? So in that cases, we are usually limited to, when we are talking about ANNs, you would majorly want to uh, be dealing with structured data, right? When you are working with ANNs, because it's not that it cannot work with your image data and all, as we have seen previously, but again, as we saw last time, that in cases of ANNs, because if you are passing an image of 1024 into 1024 size, it will have close to 1 million features, right? And that becomes a problem when you are running such a complicated model, right? So ANNs typically you can use for your structured data problems, right? Any problem which is, let's say, classification or regression kind of problems, right? So there you can use your ANNs. Okay. Now coming to CNNs, how can you use a CNN now if we are using an ANN for this? Again, CNN as what we have seen, your image detection, yeah, right? Your medical diagnosis, right? Your let's say you have all your different, if you talk about some other data types, you can also, majorly CNNs will be used for any image or video related data, right? So you can also use for video classification, right? So these are some of the domains wherein you can use the CNN. Okay. Yes. Now coming to recurrent neural networks, right? Recurrent neural networks, when we'll be studying about them, so you will see that recurrent neural networks are actually your, let's say, your uh, Google Assistant, right? That you're seeing, or Siri, right? Or your language translation. Now, if you see all these cases, these are actually complicated cases. Why? Because if, let's say, if I look at translation of language from one language to another, right? So let's say from French to Spanish. If I want to say my name is so and so, right? Now in French, I might say something, and in Spanish, the sequence of words might be something else, right? So whatever model you are using, it should have a memory, or it should be connected with the previous models. It should know that, okay, if someone is saying my name is, then it should be followed by the name of that particular whoever is saying that, right? Now let's say if I'm saying today the temperature is going to be, right? Now all these words are basically connected to each another, right? Each other. So what will happen is that your recurrent neural networks hence will be what they will be a connection of multiple ANNs that you have, right? Multiple ANNs will be sequentially connected. One ANN will be predicting something. Now this prediction will be going to the second ANN, and so on and so forth. All the values will be going forward. So you can imagine how much complicated it would be tuning a recurrent neural network model, right? But all the things, so if you see right now, if you go on to YouTube and all, right, so there are ways through which you can generate the subtitles, right? Now previously, if you remember, I think 10 to 15 years back, at that point of time, there used to be text files for subtitles which you had to pass to a particular video file in order for you to see that particular uh, subtitle on the screen, right? But nowadays, if you go onto YouTube, Netflix, and all these, for some cases, these subtitles will be generated. But even if the subtitles are not generated, right, these complicated deep learning models, they are actually able to do that. But this happens using recurrent neural networks. And recurrent neural networks, again, see, if you want to create subtitles from voice, right, it is not that you can only listen to one word and convert that, right? You will have to listen to each and every word. So you will have to make sure that till the sentence ends, you have each and everything. So all your predictions should match in that case, right? So there you can go ahead and you can use these techniques, recurrent neural networks and all. Now, autoencoders and also this is for your deep learning models. This is kind of a feature reduction technique, right? You can call it as feature extraction, or you can also use it for image compression, right? So these are some of the cases wherein you can use this technique. I have used artificial neural network models. I have deployed artificial neural network models only couple of times, right? CNN model, in my previous company, I have deployed 3 CNN models. Recurrent neural network models, I have never used in my entire life, because those are the kind of problem statements which the I have never worked with, right? So it actually depends upon the kind of companies that you're going in, the kind of problems that you're working with, right? But you should have the knowledge about all of these. That is fine. But see, at the moment, there are self-driving cars which are being built on a CNN model. That doesn't mean that we will be building a self-driving car over here. What I can help you with is understanding the basics, right? Once when you have understood the basics, now let's say that you get selected for for a company, right? Now that company might be into, let's say, retail analytics. Okay. Now retail analytics, you can very well be assured that, okay, you can go ahead and you can use your traditional machine learning and your deep learning models. Okay. Most of the consulting companies that are out there, right, 90% of the companies that are in data science are uh, uh, consulting companies. Consulting companies will majorly have structured data clients, right? They can be clients from telecom, from finance, from retail. right? And these are the entry level data science jobs that you will almost always get, right? For moving into much more complicated roles, which are properly into deep learning, right? You need to have some basic experience on your traditional data science roles, right? Or else you would have to have a resume wherein you would have built multiple projects on image detection and video classification and so on and so forth. Even then the chances become slim because companies prefer people who have some experience. So my aim over here is to make you understand what are, let's say, the 90% of the most common techniques that are used out there, right? And using those you can do what you have planned next in your life. And then gradually all these complicated topics, they probably are separate courses of 20-30 hours, right? But again, my suggestion is if you are able to do this 90%, there is nothing stopping you from covering that 10% because all that 10% is coming from this 90% only. Your typical CNNs, your ANNs, what you are doing over here, this is not easy stuff, right? Uh, Going beyond this, there will be n different things that will be there. But whatever you are covering till now as well, right? I can give you multiple data scientists who I have worked with, I am currently working with, who will not know how to run a convolutional neural network model or recurrent neural network model, right? That does not mean that they are not good data scientists, right? That means that the majority of problem statements out there, right? They actually do not require that. And for some niche problem statements wherein it is required, it is not that you will not be able to pick that up, right? I'm not saying that you will never work for a company wherein you are working with video data and all that. You will be doing that, right? If you want to do that, you will be doing that. There are multiple companies who do that. But then it will never be a problem for you if, let's say, you go ahead right now and you are trying to see how CNN model will work for video data and all, and you don't actually understand how a typical CNN works, right? How gradient descent works. So you will not be able to tune the parameters. As I said, it is not magic. It is not that you just get a bit of a piece of code and you just have to run that each and every time. Okay. So if you see, if you plot your train loss and test loss, right? So every time what will happen is, right? So let's say that this is the x, this is the x and y axis, right? Or whatever. Now, what will happen is your train loss will go something like this always, right? You keep on training and this will keep on going down. But your test loss will actually, it might be something like this, right? It might go down. It might not be such smooth, but then it will keep on going up, right? So what do you want from your model? You want to stop at a point which is something like this, right? Somewhere over here, right? You will stop somewhere over here because over here you can see that both your test loss and your train loss are minimum, right? So this is, let's say, your test loss and this is your train loss. Okay. So header, you can, in the read CSV part, right? So you can give the option which is add header as true. If you go to, okay, right? While you are reading that data, you can give the, one second. Okay, so this is header equals to 0. There will be no header, no columns will be there. Or what you can do is that you can give header equals to one option. It is int. You can give a list of int, none, or default. Right. So what are they asking you to do over here? This was the assignment, right? Module 3 assignment you're talking about, right? Import the data set and add the header columns with the names function. Where is the names function? Okay, so see, what you have to do is that I think there is a names function or something, or whatever names you have to define, you will have to pass that as a list over here. If you see, so if you just pass the list of the names, that will be considered as the header, right? See, if you use this particular parameter names, array like optional, right? So list of column names to use. If the file contains a header row, then you should explicitly pass header equals to 0 to override the column names, right? So now what will happen is that if you want to give explicit column names, so what you will give for this particular parameter, you will give the value as 0. So it will ensure that whatever headers are coming from the file, they are being dropped. And then in the names part, you will have to give the list of the names that you would want to give to those columns. So if let's say you have 5 columns in the data, so you will have a list of 5 values, 5 names that you will like to give to each and every column, and they should be in the sequence in which your columns are there in the data. Okay. So this is how you can do this. If let's say, so there are two things, right? Now let's say what happens is that you added 3 layers in your model, right? And you saw that the validation performance and your training performance were almost same. Okay. Now let's say you added the 4th layer and your validation performance and your training performance actually increased, but your validation performance increase was not as high as the training performance, right? So that means that by adding the 4th layer, there was some kind of noise in the neurons that was there, right? But hold on. Now let's go ahead and add one more layer, right? Right? Let's say you go ahead and you add the 5th layer. Now, after adding the 5th layer, you see very clearly that the performance for validation is not going up, but for training, it is going up, right? What does that mean? First thing is that you should stick with 4 layers only, right? But in the 4th layer, you are seeing that there, to a certain extent, there is some kind of a difference in the validation and the training performance, right? Then you can go ahead and you can apply a dropout, right? So dropout should be applied when you feel that a layer is required, but from that layer, to a certain extent, there are some neurons or some features which are not helping you predict correctly, right? But it should not be the case that you are adding 10 layers in the model and then you are using a dropout of 50%, 60%, right? At the end of the day, what you are doing is that you are minimizing the neurons in the layer only, right? So these are very critical parameters that you will have to be very sensitive with when you are playing around, right? So dropout should only be considered when you know that, okay, this layer is required, but within this layer, maybe you are passing 512 neurons, and you are seeing that, okay, overfitting is there to a certain extent, right? Then you can go ahead, because you don't know what neurons you have to deactivate. There you can add a dropout layer, right? See, there can be multiple parameters which are the cause over here, right? One reason can be the number of layers that you have defined. Other reason can be the number of neurons that you have defined in each and every layer, right? Other reason can be the kind of functions that you are using in the model, right? So all these things you will have to tune your model. You will have to see. So right. So that's why what we do when we are tuning a neural network model, it's not that we start with, let's say, 4 layers, right? You will start by adding one layer. One by one, you will be adding each and every layer, and you will be continuously monitoring the performance, right? Now, let's assume you go and add one layer and you are saying that the model performance is not good, right? The loss is still very high for both training and testing. What does that tell you? That tells you that you will have to add one more layer, right? Now you add one more layer. You see that, okay, the loss is going down, it is decreasing, but still there is scope for the loss to decrease. You will add one more layer, right? Now, after adding the 3rd layer, you see that the loss which was decreasing, now it has started to increase for your testing data, right? Now, as soon as it happens, you will know that, okay, somewhere around 3 layers is my best structure for this particular neural network, right? Now you will start your parameter tuning. Now you will see that, okay, let's add dropout to each and every layer, right? So all these are parameters that you'll have to play around with. You'll have to see what is working best for that particular model, right? And that is how you'll have to tune that model. See, dropout will not miss any data. First of all, dropout will only drop out the neurons, right? So be clear on this, that dropout will be deactivating the neuron. So this has nothing to do with data, right? Shuffle, yes, when you are doing shuffle, right? So the only thing that will happen is that your rows of your training data, right? Let's say you have 1000 data points, right? Now, these rows will not be passed to the neural network model sequentially. They will be shuffled. But all the rows, all the 1000 rows that you have will eventually be passed into the model, right? So your data, all the data that you have considered for training, it will go through the model. It will never be missed. No rows will be missed there, right? Image quality, if you want to increase, that is something that is that when you're sourcing the data at that point of time, you'll have to ensure, right? For the existing images, which are, let's say, 32 cross 32, you cannot increase the pixel quality, right? But for whenever you are working on a problem, you would want a good size of the image so that it has good features in terms of pixels into that, right? But for an existing smaller image, you cannot increase that. Now we are starting with recurrent neural networks, right? So again, over here, as the name suggests, right, recurrent is what means to reoccur, right? And that is what we see in this type of networks. Recurrent neural network is nothing but a combination of ANNs, right? So if let's say you have ANN1, this will be connected by ANN2, this will be connected by ANN3, and so on and so forth, right? So like this, ANN, right? So this is how you can represent a typical model for RNNs, right? Recurrent neural network. So that is what we, okay. Now, feed-forward network, right? What are some of the issues that we have with the feed-forward network? Not exactly issues, but what are the limitations of a feed-forward network that we can see usually, right? Now, limitations. Now you can see over here. Let's say the input is something like this. Let's say the input is chicken, and the output is chicken pizza, right? Okay. Now outputs are not related with each other, right? If you see, there is not there will not be a, like, you cannot establish a mathematical mechanism probably to predict chicken pizza from chicken, right? Uh, Problem with your, okay, let's not take this example. I'll take uh, another example. The problems with ANNs is that ANNs are actually not able to remember the previous outputs, right? Now, an ANN is only created, or an ANN can only help you in predicting a single unit, right? A single unit can be, let's say, the whether a person will buy a credit card or not, right? Or let's say what will be the price of a particular property on sale, right? Now all these are singular units which are not dependent upon each other, right? Now what if I wanted to predict the name of a, or let's say, what if I wanted to predict the job profile of a person, and after predicting the job profile from the same model itself, I wanted to predict the salary of that person, right? Now in this particular case, what needs to happen is that you actually want two different kinds of predictions, right? But one prediction is might be in some way correlated to the next prediction, right? Now depending upon the designation of the person, you may be able to predict the salary, right? Now that is where your typical your simple neural networks are actually not able to help us, right? Because as you know, in case of a simple neural networks, output layer will just be one, right? My output layer can be defined as only one output layer. Now that output layer can either be, let's say, you are predicting a variable which is divided into classes, right? Let's say whether a person will buy a card or not, right? Or you are predicting a variable which is a variable such as, let's say, the price of a particular product, right? Or the sales that you will see on a particular product, right? So regression and classification, they can be achieved through ANN separately, but you cannot combine that, right? You cannot combine multiple classifications in a sequence in case of a typical neural network, right? Now we will see where exactly we will be needing recurrent neural networks, right? Now, if you see, would this feed forward network be able to predict the next word, right? Now, let's say my input over here is this, right? Input is something like this, and I am expecting my neural network to basically fill in the blank, right? Now, recurrent neural, and which is followed by blank. Now, in order to predict the next word network, the ANN or the model that we have should have the capability to take in previous values that are there, right? So your output will change. Now, if let's say, if I would have gone ahead with a typical ANN here, what will happen is that you would expect the ANN to give this output, right? Now this output, again, this will be your final layer only, output layer. Now the neural network that you are trying to build will have no idea what these values are. Okay. But what if I have a mechanism which is able to predict all these three things, right? When, let's say, the probability that it takes of predicting this word, right? Then it says, let's say that the probability of this word is recurrent, which is your, let's say my ANN1 predicts this word. Okay. And let's say that the probability is 0.90. Okay. Now, similarly, my second ANN, let's say this one is ANN2. And over here, the probability if my previous word is this one, right? If my previous word is this one, then the probability of the next word being neural becomes, let's say, 0.85. Okay. And now my third neural network, right, will predict that, okay, if your first two predictions are these two words, right, then the probability of your third word being network will be, let's say, 0.80, right? So over here, if you see, we have combined three neural network models, and then on the basis of the predictions that we are getting from each and every model, some kind of knowledge is flowing forward, right? From ANN1, there will be some key values that will be flowing to ANN2. Now from ANN2, there will be some key values that will be flowing to ANN3, because of which we should be able to predict that the third word for the sequence will be network, right? But now this is something that you won't be able to do in a typical ANN model, right? In a typical model wherein you have only one, wherein you are defining only one neural network with one layer in the last, right? So your output layer will be only just one layer, right? And that output layer is not again connected to any other neural network model. In those cases, you will not be able to predict things in a sequence, right? And that is where recurrent neural networks actually come into picture, right? So in order to make complicated predictions, wherein each and every prediction that you have in a sequence is correlated or is dependent upon the previous prediction, right? We will have to make use of recurrent neural networks. Okay. Now this a typical network would not be able to predict the next word because it cannot memorize the previous inputs, right? So because there is no recollection of the previous inputs that were there in case of a typical ANN model, it won't be able to predict over here. But a recurrent neural network will be able to do that, right? Now, let's say if I look at the solution with our new kind of models, right? So let's say that we have this kind of a data. I only cook these three items and in the same sequence, right? So day one, let's say chicken, day two, let's say pizza, and day three, let's say spaghetti. Okay. Now what will happen is that your uh, the model that we'll be defining over here, right? Now it knows, So let's assume that these are three different ANNs. Okay, so this will be your ANN1, okay, ANN2, ANN3, right? If you see, all these are connected with each other, and this combined will, this structure combined will become your recurrent neural network, right? This will be your RNN. Okay, now over here, this is how your network will look like. Now you will feed some features in day one. Okay, now on the basis of the features that are being fed in day one, what happens is that you are getting this prediction that on day one the cook is going to cook let's say chicken, right? Now this output that is coming over here will be fed into the second network along with some new features for day two, right? On the basis of this particular network will learn that, okay, whenever the cook is cooking chicken and the features are in this range, right? Then on the second day, the cook is going to cook, let's say, a pizza, right? Now, once again, there will be some key values which will be flowing from this ANN2 to ANN3, and there will be some new features which will be flowing in on day three once again. And on the basis of this, the network will be able to predict that yes, on the third day you are going to cook this particular dish, spaghetti, right? Now over here, if you see, outputs are dependent on each other, can work with sequential data, can remember previous what were the previous values, right? Now in order to know that, okay, the second day will be pizza, you need to know that the first day will be chicken, right? So all that knowledge that is required will be fed forward to this particular network, right? Now in order to know that on the third day this will be cooked, the network should know that on the previous 2 days, your chicken and pizza were cooked, right? It's not just that what was there on the previous day, you should know what has happened in all the previous cases, right? Now, this is something that you can achieve with a typical recurrent neural network. Okay, I'll make this more clear. These examples may look a little vague, but okay. Let me give you another example, right? Now, let's say I have an image, right? Let's say I have an image of right? Now, let's say I have this image as an input into the model. Okay. Now, this can be classified as one-to-many, like this problem can be classified as a one-to-many recurrent neural network problem, right? Now, over here, what will happen is first of all, why one-to-many? Because your over here, if you see input image is only one, right? In the output, what we expect is, so this is a problem wherein we are taking in an image and we are giving the description of the image as the final value, right? Now, one one to many, you have one uh, photo that is flowing into the model, and the output that you will be expecting will be something like this: the big black and white dog jumps over the barricade, right? Now, let's say this is what you are expecting. Okay. Now, with a typical CNN model or a typical neural network, what can you predict? All you can predict from this image is just one thing, right? What is that? You can just predict that, okay, whether it is a dog or a cat, right? And depending upon the classes that you have passed, maybe you can predict whether it's a dog jumping or a dog sitting and all those things. But obviously, you cannot caption this particular image, right? But with your, if you look at your RNNs, right? With your RNNs, you will be able to do this. Why? Because let's say your first network, right, your ANN1 predicts dog. Okay, it predicts that, okay, there is a dog. ANN2 predicts jumping, right? Now all these outputs will be linked to each other. ANN1 will feed whatever it is giving as the output to ANN2, right? Now ANN3 predicts barricade. Okay, ANN4, let's say, combines all these predictions and says there is a dog which is jumping over a fence over here, barricade, right? Now this is what happens when you're working with recurrent neural networks. So you will be having complicated, your in short, what happens is that your predictions have become much more complicated now, right? It is not a singular prediction of whether it's a cat or a dog, right? Now your predictions have become much more complicated, hence your neural network are also supposed to become much more complicated. Okay, does this make sense? Okay, so let's have a look at a typical network over here, and this is just a structure of that, right? So uh, recurrent neural networks are called recurrent because they perform the same task for every element of a sequence, with the output being dependent on the previous layers as well, right? Computations. Another way to think about recurrent neural networks is that they have a memory which captures information about what has been calculated so far. Okay, now as I said, same thing. Recurrent neural networks, you can just assume that these are multiple neural networks which are connected together. But by connected, what we mean is that at each and every stage, now if you see for ANN1, right, there are two things that you are getting from ANN1, right? One is the output that you are getting, obviously, right? And then there is some amount of information which is being passed from the ANN1 to ANN2. Right, now this information will be the final value that you are getting from this one, and then there might be some other things, some other features which you might require from ANN1 to help in the prediction of ANN2, right? That will also be so. All the required knowledge that needs to flow in from ANN1 to ANN2, right? That will be put over here, right? So if you see now, all those features and all those things that you require from ANN1 till ANN2, they are being shipped from here to here, right? Now, again, if you come to ANN2, in case of ANN2, there are a new set of input features, right, which are flowing in from here. And then there are these features which are flowing in from here. Combined, this is once again going ahead and giving you an output at T, right? Now, all these values are getting combined, right? So whatever is flowing from here, whatever is flowing from ANN1 to ANN2, ANN2, and ANN3, all those can be considered as the predictions that we are getting from the previous networks, as well as some of the important features which might be required for future predictions, right? And then finally, when you come to the last network, there you combine all these things together and you give the final output. Okay, and this is how a typical recurrent neural network will look like. Okay, and this is the structure. So understanding recurrent neural networks, this is a slightly complicated image. Now, if you see, first of all, recurrent neural networks are defined in such a way, right? If you want to define a recurrent neural network through a diagram, right? Through a concise diagram, you can look at this, right? So if you see over here, this particular part, this particular loop that we are creating, wherein the network, we are saying that there will be multiple networks that will be present on top, right? Now X is going in and X is going into the network, which is S, right? Now S is giving you two things. One is O that you are getting over here, which will be the output basically that you're getting from this one, and then there will be some features which will be once again fed to the next S, that is the next neural network, right? Then again some features will be flowing in X, and then again a prediction will be made, right? So this is a concise image, but if you basically uh, go ahead and expand this, right, this will result into something like this only. Right? If you expand this recurrent neural network on the left hand side, this should look something like this, right? Now, what is happening? What is xt minus 1? Xt minus 1 are the inputs that are going, right? xt minus 1 will be your inputs. So this layer will be focusing on all your features, right? There xt minus 1, xt and xt plus 1 all are considered as your features. Okay. Now st minus 1, st and st plus 1, they will be what? They will be your neural networks that you are defining, right? So all these will be your network layers. And over here, if you see this will be your outputs that are coming. Okay. And all these outputs will be related to each other because this data is being passed from NN1 to NN2, NN2 and NN3, so on and so forth, till you get the final output, right? So this is again a similar image that we had seen previously, but slightly complicated. Okay, so all these are weights, right? If you see this U, V, W, all these are weights. So we'll now, if you talk about your typical neural networks, there were one sets of weights, right? That you had. Biases and weights were fixed, right? Now over here, if you see from XT to ST, the weights that you are defining are U. Okay, from ST to this one, that is OT minus 1, the weights that are defined are as V, right? But from ST minus 1 to ST as well, what outputs need to flow forward, you will have a weight for that as well, right? Now, because see, in case of a neural network, obviously you will be having all the data that is present. Now, from all the data, output features and all, what are the relevant outputs that you have to feed forward to the next neural network, right? That once again will be defined by weights. So over here, whenever I'm saying that that a neural network will be able to remember, will be able to memorize from the previous layers what is happening. All that I'm doing is that I'm establishing a connection of ANN1 with ANN2 with all the features that ANN1 has and the predictions that ANN1 has made. But I am depending it upon a weight matrix, right? Now that weight matrix will define what are the necessary features from ANN1, what are the necessary predictions from ANN1 that need to move forward, right? And similar to that, so essentially you can consider a recurrent neural network as a huge network combining of multiple simple neural networks, but obviously all these neural networks will be connected by weights values, right? So different weights will be there which we need to initialize, right? So you can imagine that how dense uh, this kind of a neural network will look like, right? Because you can see that there are weights at each and every place. Everywhere, every connection you are making, every connection of one ANN to the second ANN, every flowing of data, right? Wherever your data is being flowing from one ANN to the second ANN, all these will be defined by different sets of weights only. Okay, so these are weights. Okay, now XT is the set of features at time step t. ST is the hidden state at time step t. It is the uh, uh, basically uh, memory of the network. Memory of the network, as in what it is getting from the previous states and what it is getting from the current state. ST is calculated based on the previous layer, on the previous state and the input at the current state. Right. The function f is usually a non-linear function such as tan h or ReLU. OT is the output at the step softmax, right? So if you see this hidden state ST minus 1, ST and ST plus 1, this is what? This is nothing but a combination of your current state, which will be your features that are flowing in the form of XT minus 1. And this will also be your previous state, whatever is required from your previous neural network. That will be defined in ST minus 1.
Let's have a quick quiz question, guys. And the question is, the following function in Lisp would return bracket min USP bracket minus 20 4881 bracket. Now, your options are F, T, minus 20 or nil. Please mention your answers in the comment section below.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective as it is taught by IIT professors and industry experts.
Now, first of all, we are clear what is xt, right? Xt is what? Xt is input at each and every state, right? Let's say t minus 1 is time step t minus 1, t is time step t plus 1 is time step t plus 1. Okay. Now, what happens is that you will be defining your hidden state. Hidden state as in hidden, we are just saying because just correlate hidden with the layers that we were defining in case of a neural network, right? So all this data will not be visible to the end user, right? Hidden layer from ANN has been changed to hidden state over here, right? So all your ST minus 1 and ST and ST plus 1 will be considered as your hidden state, which will be comprising of your hidden layers, right? Now, XT minus 1, XT and XT plus 1 are nothing but your input features coming at in different stages. Okay, this is one. Now, what happens is you are defining your your ST minus 1, ST and ST plus 1, which are your layers which are defined in between. Hidden layers, they will be a combination of what? They will be a combination of your previous state, right? So what is coming from your previous neural network, one, and what is coming into this state as a new set of features, right? So that will be your hidden state will be defined by your previous state and your state, which is your current set of features, right? So hence, if you see, ST is calculated based on the previous state and the features of the of this particular step that you have. So ST is a function of what? It is UXT, okay, which are your features, and it is WST minus 1. So U and W are what? They are a set of weights, okay, for your current state and for your previous state. The function F is usually a non-linear function only, such as tan H or ReLU, right? So the function again, what function you have to use over here? This again is a parameter. It is usually a function which is non-linear, right? So we can go ahead with a sigmoid, we can go ahead with a tan H ReLU, leaky ReLU, whatever, right? So we look at this, right? But like this, if you see, each and every hidden state is connected to the time step of the next state, and hidden states for each and every step are defined by nothing else but the input features coming from that particular time step and the previous steps features that are considered necessary to move forward. Okay, right? It will keep on refeeding those input features to the recurrent neural network, because what it knows is that using only these sets of features, I have to go ahead and I have to predict. Now, if I go back to my example, which was this image, right? Where is it? This image, right? Now, this input image, if you see, only this input image can be used as a set of features for multiple values, right? So output number 1 from neural network 1 can be what? That it is a dog, right? Now, using the same image, feeding it to a second neural network, you can also give an output that, okay, there are trees around, right? Now, using the same image, giving it to a new network, you can also say that whatever object is there, it is in air. So probably it is jumping, right? You can also say that there is some kind of a fence there, right? So using the same set of input features, you can extract different outputs, right? So that is how what will happen is that your same set of inputs can be fed to multiple neural networks, but your end objective will be different, right? Your prediction, what you are predicting from there, will be different. XT minus 1, yes. So if you see, what will happen is that if you come to this picture once again, right? Now, when my neural network is predicting a dog, right, it will only focus on the part which has a dog in it, right? So only the features will be extracted from that part, right? When my neural network is focusing on that there are trees present, then it will be extracting features or using features that are associated to the tree, right? But at the end of the day, we are feeding in all the features to the neural network through its weights values, right? Which we have defined through U, right? Through the weight values that we have defined, it will be able to find out that what are the relevant features that are required for me to go ahead and make this prediction. And obviously, there will be some previous outputs that will be coming in from the previous layers, right? Now, let's say that, okay, let's take our example only. And let's say that this neural network, this recurrent neural network in your output step OT-1 had predicted dog. Okay. Now let's say that over here, then what happens that your dog and all the data that is coming from dog is flowing in from your ST-1 to your ST, right? Now, on the basis of this, from XT, this particular neural network, let's say it derives jump, okay? So what will happen is that your output will become something like this, right? Dog jumps, okay? Output T, which is a combination of previous output and the set of features that we are getting from here, right? Now, similar to that, output 3, what will happen now? Dog jumps will be flowing forward from ST to ST+1. Now, your let's say output T+1 is black and white now. So black and white dog jumps, right? Like this entire structure will be created. Your different words that you are getting as predictions from the different neural networks, they will be created, right? And finally, in your final output, you will get the whole sentence that you are expecting, that black and white dog jumps over a fence, right? So this is all. But if you see, for all these neural networks, same image can be fed, right? Because the image only consists of all these values that we are actually getting. The dog is in the image, the fence is in the image, jumping part is in the image, right? Trees are in the image. Okay. Okay. Now coming to back propagation, right? So if you see over here, see, assume this, all this, right? The complicated network as a neural network only that we have studied, and assume that all the weights and biases, right, coming from hidden state 0 to hidden state n, all these have to be tuned, right? Just like we have done gradient descent on our simple networks, right? Just like that, all the tuning will happen over here as well, right? It's not that they are separate neural networks which are not connected to each other. Since these neural networks, ANNs, are connected to each other, what happens is that you will have to obviously optimize the weights, right? Now, if you remember, in case of a simple neural network, when we had to optimize the weights, how we had to backpropagate, right? The backpropagation was what we, from the output node, we compared the difference of your real value and your value that you get from the network, right? Predicted value and real value. And on the basis of that, because we have to minimize this difference, we actually backpropagated through time, right? We calculated the differential of the error with respect to the different weights that you had, right? So differential of error with respect to, let's say, weight 1, differential of error with respect to, let's say, weight 2, and so on and so forth, in order to get actual contribution of each and every weight, the contribution that each and every weight is giving, in order to get us this particular predicted value, right? On the basis of that, we went ahead and we readjusted the weights, okay? And then once again we moved forward, and we calculated the predicted value, we had the real value, and then once again we calculated the difference, and this process went on and on, right? Now over here, imagine the same process. It's just that there are multiple networks that are connected, right? Now, if you see over here, this is a recurrent neural network that we have defined. And this neural network has 5 separate simple neural networks at play over here, right? Which are connected to each other, right? Now, hidden state S0 to S4 will be considered your, you can consider these as 5 separate simple neural networks. Okay. Now, whatever output we are getting at S4, right? Now, imagine the first step. Imagine the first time this particular recurrent neural network runs, right? With the first batch of values, whatever we are passing. Now, all the outputs that it will be comparing will probably be wrong. Okay. Now, from S0 to S4 it goes, then it compares the actual value with the predicted value, right? Now it starts coming back. When it compares the actual value with the predicted value, it starts coming back, and it starts to readjust the weights. Okay. Now the readjusted weights for S4 will be simple because they are linked to the final value, right? whatever we are getting as the final value, and we have the real value as well, we'll make the comparison and we'll get the delta, and we will be able to adjust the weights, right? Now, on the basis of the adjustment of those weights, once again you will come from hidden state S4 back to hidden state S3, right? So you can imagine that what will happen is that whatever differentiation we were calculating in just one particular simple neural network, now that is going to happen in sequence for all the networks that are present, right? And that is exactly what happens in backpropagation when we are talking about this kind of a network, right? So backpropagation through time, PPTT, is used to update the weights in the neural network, right? So the same thing that we have done previously. Recurrent neural networks typically predicts one output per each time step. Conceptually, backpropagation through time works by unrolling the network to get each of these in singular time steps, right? And it calculates the error across each time step and adds up all the individual errors to get the final error, following which the network is rolled back up and weights are updated, right? Same thing which I have told you. The same thing is mentioned over here. That backpropagation through time over here as well is the same process which we have seen. It's just that it is a much more complicated process because the number of backpropagation steps have increased, right? Now, depending upon the number of layers that you are defining, right? The number of neural networks that you are defining within this particular network, obviously your backpropagation, the complexity of your backpropagation will increase. But the basic funda, right? The basic process of backpropagation, which we have talked about 2 weeks back, remains the same, right? You will be calculating the gradient with respect to different weights, and then you will be going ahead and you will be making you will be changing those weights as per the gradient that you are getting, right? Same process is going to happen over here as well. Okay. DS1, DS2, this is not DS, this is differentiation, right, Ankit? Same thing which I, right? But theoretically as well, it is very, very complicated to visualize what exactly a recurrent neural network will do, right? But intuition point of view, try getting the intuition, right? What is happening over here? At the end of the day, just like we have coded CNNs and your simple networks, we will be able to code for these as well. Recurrent neural networks as well. At the end of the day, you should be able to know what are the parameters that you need to tune. But to a certain extent, if you are able to understand what is the functioning of this kind of networks, then it will help you. Okay. But again, the more you go through the theory, the more you try to understand, you try to break down, the more you will be able to understand, right? So don't worry, even if you're able to get 40-50%, that's still okay. Okay, now coming to the types of RNNs, recurrent neural networks, right? Now, we have seen the functioning to a certain extent, but on what are some of the cases wherein recurrent neural networks are actually used, right? Now, recurrent neural networks can also be used for your single classification problems for which we had used the CNN models, right? Or let's say a categorical ask, right? Wherever you are trying to predict something categorical. Regression as well, you can do that, right? Regression as well, you can do that using your these networks. But again, recurrent neural networks are a requirement only when you are predicting something complicated, right? So for one-to-one asks, you have many other networks, right? So what are the different networks that you can use when you have a one-to-one prediction? What are the different options that you have for making one-to-one? When I'm saying one-to-one, it can be as simple as whether a customer will buy a loan or not, whether a person will buy this product or not. ANNs, your CNNs, your typical models which come under the wing of machine learning. Exactly, right? So for one-to-one type of problem statements, recurrent neural networks might be, it might be that you are picking up a very complicated tool to solve a simpler problem. So you should not go ahead and use these types of models there, unless you feel that, okay, your ANNs and CNNs are not able to do a good job there, right? So that is one-to-one. So one-to-one again, recurrent neural networks, I would say They are not that much used in one-to-one kind of problem statements because your ANN CNNs are simpler models which are able to converge faster, which are able to give you an equal performance in a lesser amount. Okay. You remember if we had to calculate the weight of W1 with respect to the error, how did we do that? Differentiation of error with respect to W1. And now from W1, there will be multiple weights which will be there, right? W1, W2, W3, W4, W5. How did that happen? In case of back propagation, what did we do? We did delta of error with respect to the output from the previous layer, right? Multiplied by delta of the output from the previous layer with respect to what features are going into that previous layer. Now, this will go on and on and on till you reach that point wherein your W1 is defined. I have spent a good amount of time in explaining this process. If you remember, that same process is going to apply over here. Okay. Now coming to one-to-many. Okay. Now one-to-many is what? One-to-many. Okay. Can someone give me an example of one-to-many problem statement that we can have with which we can solve through recurrent neural networks? One-to-many as in your input will be one, but your output will be many. No, that is what do you mean by father and son? Dog is jumping, exactly. So the example that we have taken in this particular case, which is image, right? So from one image, so this will be considered as one-to-many. No, Hasmit, don't take this example. Predicting if a sentence makes sense through the words may be correct. No, Amit, this will not be one-to-many. I'll tell you, this will be many-to-one, right? One-to-many will be what Puneet is saying and the example that I took, right? Over here, if you see this example, this is what one image, right? From one input image, you are making many predictions. How? One image is giving you the prediction that a big black and white dog jumps over a white fence, right? So this will be considered as a one-to-many neural network, wherein only one input image is fed to the model and many outputs. So if you see over here, from this one image only, right? From this singular image only, you are able to create a network which is predicting you multiple values, right? So this will be an example of one-to-many. See, chatbot again will be many-to-many because what is happening is that as an input, you are giving many words, right? That I want help with this product, right? Now the chatbot will reply, okay, this product is has been shipped from a particular location and will be reaching your pin code at this time, right? Now this output it has derived, but that's a good example. So what you are saying, Amit, that is the example of a chatbot, and that is a many-to-many neural network, right? So I'll come to that as well. Okay. Now many-to-one. Any example? What can be many-to-one? So many-to-one can be what? It can be a sentiment classification, right? Now you have deep learning models which are giving you a summary of an entire book, right? From one image, many details are made, right? Is one-to-many. Your single input is giving you many outputs, right? That will be one-to-many. Many-to-one will be vice versa, right? Many-to-one will be my neural network. Let's say I have created a neural network model or a recurrent neural network model, which will take as an input let's say an entire book's content, right? Let's say you have created a deep learning model which will predict the genre of the book, right? Whether the book that is being fed into the model is fiction, reality, child, adult, whatever, right? Okay. So you want to predict the genre of a book. And for that, what will happen is that this will be an example of many-to-one. Why? Because there will be multiple words that you're feeding into the neural network. And at the end, you want to get whether what is the kind of book that it is, right? Whether it is a children's book, whether it is a fictional book, whether it is a mystery book, and so on and so forth, right? So that can be an example of many-to-one. But it's not that all the features are interrelated to each other, right? All the features are basically free of each other. But in case of a novel, in case when we are predicting the genre of a book, right? What will happen is that all your words are actually connected, right? To extract the genre of the book, you'll have to probably go through the entire book, and to then only you will be able to extract the genre. Netflix recommendation, no. This is also not many to one, right? This is uh, your inputs. Again, as I said, it's not that your inputs are correlated with each other. In order to make a recommendation of one movie, it's not relevant. Okay, so try to distinguish it in such a way, right? What if some of the okay, what if I take away some of the text from a book? Will my model be able to predict the genre of the book correctly? What if I take away some of the pages of the book? My model will not be able to predict. Why? Because there is a dependency of all these pages. I will have to go through all mm, the contents of the entire book in order to make one prediction, right? But when we are talking about a recommendation engine, let's say you have 10 different movies. Even if I take 5 movies away, using the remaining 5, you can still go ahead and make a prediction, right? Because the 5 might not be interconnected with the remaining 5 that are there, right? Job role and salary prediction, no. So these are, again, I mean, see, these are classical categorical models that you are talking about, right? When you're talking about recurrent neural networks, you think of complicated problem statements such as, okay, your many to one prediction can be what? A very simple example of many to one prediction will be you interacting with Siri, you interacting with Google Talk Assistant, right? What will happen in that particular case? What are you doing? You are saying, "Hey Siri, can you tell me what is the time?" Okay, the output is what? Siri gives you time, right? Or, "Hey Siri, can you set an alarm for 6 a.m.?" Right? Alarm will be set. So many words are being fed, but the action is one, right? So that will be considered as many to one, right? Even if, let's say, there are 5 sons and you have gotten rid of 4 sons, still you should be able to predict for 1 son, right? This is not interrelated. Google Map predictions of best route. This is an optimization problem, but if you see, this can be considered as many to one. Yes, to a certain extent, Amit, yes, this can be considered as a many to one, because there are many options that you are feeding and all these are interrelated with each other. No, Hasmit. See, these are, again, you'll have to classify the problems in a complicated manner, right? Now, classification of a mail, whether it is spam, private, promotional, social bot, this is one target variable, right? But is this target variable dependent on multiple features at multiple time steps? No, right? See, all those features that you are getting, it's fine. You are taking multiple features. I think you guys are confusing the multiple features that are there, but taking in the multiple features using only one model, a singular model, you will be able to predict, right, whether a mail is spam or not spam, right? Now, but if I take the example of let's say Siri, right? Now you have 10 different words that are there, but each and every word is interrelated, right? It's not that I can treat these words separately. If I am saying, "Hey Siri, what is the time?" Right? So if Siri is able to only take, "Hey Siri, what is," right? What is the? Will it be able to give me a final value of what the time is? No, because it is missing a key feature, because all these features put together will only make sense to Siri, right? Hence, this will be a recurrent neural network, because see, at the end of the day, what is happening is that you are using all these features which are interrelated together, creating multiple models which are making sense of this entire text, and then you are giving one particular item for Siri to do. That is okay. If your prediction is something like this, you go ahead and you tell the time. Okay. So yeah, that is many to one. And many to many can be what? It can be, let's say, subtitle generation on YouTube, right? Or subtitle generation on any of the apps that you are seeing, right? Because in this particular case, there are many words that are there. And see now, or many to many example, a classic example of many to many will be what? It will be the language translators that we are seeing, right? Let's say Hindi to English, English to Hindi. Can I okay, let's say I give a word that is run in English, okay, and I want the model to convert this into some other language, right? So let's say run is converted, and you get the output as bhago, okay. Now, if I give the output, let's say uh, Tom has gone out for a run, right? Now, what will be the output that we'll be expecting? Uh, Tom भागने गया है, right? I'm sorry if there are people in US, but I'm just giving the example, right? Now, Tom has gone for a run in English is totally different as compared to what we are saying it in our local language, right? Hindi. Tom भागने गया है, right? Now, what is happening is Tom has gone for a run will become a very small sentence, right? But to get the context of this entire thing, you will have to feed in each and every word separately, right? So this becomes a many to many model, because first of all, you will say Tom. You will feed Tom into the model. Output will be Tom, because Tom will be same in both the things, right? Be it English, Hindi, Spanish, whatever, Tom will remain the same. Now, Tom has gone, okay? Has gone, when you come down to the second language, the output will still remain Tom. Why? Because you know that in our particular case, the past and present, the present, past, future, all that will be incorporated in a particular word, right? भागने गया है, right? गया है और गया था, right? Now, for English, Tom has gone for a run. Has gone has occurred before run. For our language, what has happened is भागने गया है. It has happened after gaya, right? After bhagne. Now, this is an output which the recurrent neural network will save. Okay, that okay. Till now, I don't have to translate this because I still don't have the context of the entire thing, right? Then it moves forward. Tom has gone for a run, right? Now, when it sees run, it converts that into bhagne. Now, then it realizes that okay, when Tom bhagne, then it means that gone for a run, gone for a will become gaya hai, right? So you understand here that it's not that it is a one-to-one prediction. That okay, Tom hai, to wo Tom ho gaya, right? Has gone for a run will change into something else. It's not that you will be changing has to Hindi, gone to Hindi. You are taking the entire context, right? So hence this becomes a many-to-many problem. Now see, RNNs, right? So we have some issues that we actually face with RNNs. And because of that, we have a slightly more advanced technique, which are known as long short-term networks, right? So first of all, we will see what are the limitations of your typical RNNs, recurrent neural networks, and then we will see how we can basically bypass these limitations and come up with a model which is more robust, right? Now, if you see, in case of a recurrent neural network, right? Now, let's say that the input is this, right? These two words, and we want to predict the third word, right? Now, RNN model is supposed to give the output as network, right? Over here, the input is these two words, right? And the output is this word, which is network, right? Here, the recurrent neural network does not need any further context. It can very simply predict that the last word would be network, right? Now, this looks like a simplified input, wherein it is not that something from a very previously defined state is required, right? But I what if I gave as an input that let's say um, an input is, let's say Smita has go to has got to go to work at 8 a.m. in the morning. She slept at 10 p.m. the previous day because of the same reason, right? Now, in the first sentence, what I'm saying is that Smita has to get up in the morning at 6 a.m., right? But in the second sentence, when I come to she has to, okay, she went to bed at 10 p.m. because of the same reason. Now, in order to get the context of who that she is that Smita or is that someone else? The recurrent neural network will have to go back to the start of the sentence in order to see that whether this she is being referred to Smita or not. right? Now, this is a problem where like this becomes a complicated aspect when you are talking about your recurrent neural networks in a normal way. Why is it complicated? I'll talk about it, right? So if the context is longer, right? So if you see over here, now let's say I want to, using this sentence, I've been staying in Spain for the last 10 years. I can speak fluent, right? What should be, what should I fill in this blanks over here? As per you guys, what should be the output here? Spanish, right? Why Spanish? Because you knew that the context was that that you have been staying in Spain. Now this Spain is critical over here to predict this output, that you can speak fluent Spanish, right? Because the context is that yes, you can speak fluent, you can be fluent in a particular language only if, let's say, you have lived there on, or let's say your family belongs to that country or so on and so forth. Over here, you have mentioned that I've been staying in Spain for the last 10 years, right? Now, the context needs to come from this particular word to give the output in the final word, right? Now, your typical recurrent neural networks have difficulty in learning long range dependencies, right? So if you see, this is a very long range dependency. Now, if you imagine, these will be multiple ANN models that will be created, right? So now this model, which is your sixth ANN model, the output from this model will have to go as a major input to this last model, the 15th model, or maybe something like that, right? Now, your typical recurrent neural networks, they basically go through a very huge problem, right? When they are trying to solve these kinds of problem statements, right? Now, what is the problem statement? What is the problem? I'll talk about that. What is the exact problem, right? Now, first of all, how do you guys think that the recurrent neural network is able to do this, right? The main, if you come to the basics, deep down, a recurrent neural network is nothing but a set of weights and biases which are given to multiple networks, right? That is it. Okay. Now, in order for the recurrent neural network to predict correctly that this is Spanish, it should predict this correctly, and whatever knowledge is coming from this should flow on to the last words seamlessly, right? So that means that the weights and biases that you are defining, right, they should be defined correctly, right? There will be a very minimum scope of error in the weights and biases, right? Because what will happen if, let's say, the weights that I have defined for this neural network, right, let's say they are off by 60% initially, right? Now, if I keep writing this down, focus on this, uh, try to focus on this. This is complicated thing, but I think once this is clear, you should be able to understand what are the limitations of recurrent neural networks, right? Now, what I'm writing here is the error that you will be getting from all the different words, right? So let's say the error from this is 0.6. Okay. The error from bean is, let's say, 0.5, right? The error from staying is, let's say, or let's say, for example, for simplicity's sake, I'll take just 0.1. All the errors I'm taking, I'm saying that all these are very good models, right? And I'm taking the error as 0.1 only, right? Or let's say the weight value as 0.1, okay, in Spain, 0.1, okay. Now, if I multiply all these together, all these values together, what will be the weight that I will be getting for this last word, right? If, let's say, I have how many words? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So 0.1 to the power 14 will be what, guys? 0.1 to the power 14 will be what? Will be 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This much, right? This will be this value. Yes, correct. And now, if, let's say, for Spanish, my weight is this value, 0.1 with 14 zeros, right? 0.1 multiplied by 10 to the power minus 14. What it means is that when you're performing gradient descent on such a smaller weight value, this is a very, very small weight value, right? you will not be able to know the correct direction of the error, because this is such a small value that gradient descent, you will not be able to work around with gradient descent. Gradient descent works on what principle? You are calculating the differentiation. Differentiation is doing what? It is calculating the delta of that particular. So you are taking a very, very small change. Now, a very, very small change of this will be what? Maybe 0.1 with 10 to the power minus 15, right? So whatever, now what will happen is that whatever error you are getting from the last layer, that will be so small that when you back propagate, right, you will not be able to back propagate these weights correctly, right? So your gradient descent will fail when you have such small weights assigned. Now, because of which, when you are back propagating, so till the point that you reach the last word, right, till the point that you reach this word, your weights would have again be not correct, right? So what happens is that this process will go on and on and on, and you will never be able to converge on the correct set of weights. Okay, so this thing that I talked about is known as the vanishing gradient problem, right? This is the vanishing gradient problem. Now, similar to this, there is something also known as exploding gradient problem. And you can imagine what that is. That is when, let's say I had weights assigned as 10, right? Let's say I had 10 on an average for each and every word. So that will become 10 to the power 14, right? And again, for this, what will happen is that your gradient descent, it might become a problem for gradient descent too. When we are redistributing the weights, then the networks that are towards the start of this particular entire complicated network, whatever weights you are redistributing here, it will be a very small fraction. So hence, there will not be any much improvement in the weight that you are defining, right? So this is a problem which your typical recurrent neural networks actually face. So if you see over here, same thing which I told you, right? That this differentiation of error with respect to your first weight will be all the weights, will be the multiplication of all the weights that are in the in the middle of the first weight and the last value, right? And this becomes so small, this value becomes so small that basically performing gradient descent on that becomes a challenge, right? In this case, the network needs the context of Spain to predict the last word. The gap between the word which you want to predict and the relevant information is very large, and this is known as long-term dependency. There arises a long-term dependency while back propagating the error, right? So this becomes very small, and this is what happens in this particular case. Now, if there is a really long dependency, there's a good probability that one of the gradients might approach zero, and this would lead to all the gradients rushing to zero exponentially fast due to multiplication, right? Such states would no longer help the network to learn a thing. This is known as vanishing gradient problem, right? So if you see, if you're, as in when we move forward, my gradient becomes very, very close to zero. When it becomes very much close to zero, what happens is that while redistributing the weights again, because the gradient is tending to zero, your weights might not change that much, right? And hence your network is actually just going backward and forward, and it is not learning anything, right? So that becomes the problem when you are dealing with your vanilla recurrent neural networks that we have. Okay, that when you're saying that I live in France, I speak French, right? When I live in Spain, I speak Spanish, right? When I live in England, I speak English, right? Now all this, yes, the model should be able to capture that for Spain, the language that people speak should be Spanish, right? Obviously, you will have to pass in that much amount of information to the model, right? So similar to our typical models wherein we are passing thousands and millions of rows of data, if you talk about these chatbots and all that you're seeing, there are millions and billions of words that are being fed into this model, right? So yes, the model should be able to make sense that yes, Spain will be converted to Spanish, but not on its own, only because you have fed accurate data or enough amounts of data to that model, right? If you're giving lesser weightage to older words and higher to newer words, right? So Spain will be somewhere in the middle, but speak and can will have a higher weightage. But that is not what we want, right? Now, looking at this, we knew that Spain is a very critical input that should be fed into the output, right? So Spain, so we should actually we should be giving the most weightage to Spain over here. We should be giving the least weightage to can, I, and these kinds of words, right? So speak, yes, we should give a high weightage to speak. Fluent, we should give a high weightage, but after that we should give a high weightage to Spain. So if we go by your logic, then yes. And what if, let's say, I would have started this sentence by saying that Spain is the country that I have lived in for the past 10 years. I can speak fluent. What will you do in that case? You're starting with Spain, right? It will not always be the case that your words are positioned as per your will, right? Your words can be anywhere, but your network should have the capability of picking up the right words and assigning the right weightage to those words. Okay, so does this make sense? This is the vanishing gradient problem, and similar to this, we have the exploding gradient problem as well. The concept remains the same. Exploding gradient problem is just that your gradient becomes so large that your weights values are changed by a very huge margin, and hence you might actually skip the correct weight, right? And vanishing gradient problem, again, your weights become so small that whatever change you are doing in those weights, they are not giving an effect in the final output, right? Okay, so now we will be coming on to LSTMs, right? So LSTMs are also known as long short-term networks, right? So LSTMs are an improvement to the typical recurrent neural network models. Yes, Pushpinder, we are talking about that only. So see, in case of LSTMs, we are actually trying to deal with this with this problem, through which what we are doing is that we are actually so you can okay, so the key to LSTMs is the cell state, right? The cell state is kind of a conveyor belt. It runs straight down the entire change with only some minor changes. It's very easy for information to just flow along it unchanged, right? The LSTM does have the ability to remove or add information to the cell state, carefully regulated by structures called gates. Okay. Now, if you look at this, this is the typical structure of an LSTM model, right? Now, this is okay. Now, if you look at this is your cell state, right? If you look at this arrow on top. Now, in simple words, what LSTM does is that LSTM, just like mentioned over here, just like a conveyor belt, right? So there is a connection that is flowing from the first node, from the first layer of the first network that is defined to the last layer of the last network, which is carrying important weights, right? Which is carrying information about the different important words that are there, right? So if you compare this with a recurrent neural network model, right? If you compare this with a recurrent neural network model, if I go up, now here what happens is that S0 is passed to S1, right? S1 is passed to S2, but some parts of S0 will be lost when you are passing S0 to S1, right? Because at this point, whatever is considered useful will be moved forward from S1 to S2, right? But what instead of this, what LSTMs do is that they actually create a connection over here, right? They create a connection somewhere over here, wherein all your key informations flowing in from S0, from S1, from S2, they are passing directly, right? So it's not that. So what happens is that whatever is key, right? We add that in this particular cell state part, and that will be used for all the future cases, right? So if I come down to LSTM, right? Okay, so I had missed this, right? So if you look at this is the typical example of a typical recurrent neural network model, right? Over here, you can see that there is no cell state that is being defined. The previous interactions from this one, or whatever is coming to the past, are go to the cell state of A, right? Now, from A, we get the output st minus 1, and then from here, whatever we have proceeds to the next network, right? But in case, if you see, in such kinds of networks, have the form of a chain of repeating modules of neural networks. In standard RNNs, this repeating module will have a very simple structure such as a single tangent layer, right? Now, if you see over here, what is happening is that there is no connection that is running across all these networks, which is keeping important knowledge about the previous details that are there, right? Now, if I come to LSTM, in LSTM, what happens is long short-term networks are special kind of RNNs which are explicitly designed to avoid the long-term dependency problem, right? LSTMs also have this chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are four interacting in a very special way, right? Now, if you see, this is a LSTM model. Now, in this particular case, one second. Okay, I had come to this basically. Okay. Yeah. So if you focus on this now, this is your LSTM framework. Okay, let's focus on this particular. So this you can consider as one ANN model, right? Now this will be your second ANN model. So probably this will be a first ANN model, then second, then third ANN model, right? Now what happens is there is one key aspect over here, which is your which is the cell state, right? If you look at this, what is happening here is that information from the previous neuron is following over here, right? Information from the previous neural network is following over here, right? Now what happens is that over here, if you see, there is a gate, which is the plus gate. Now the information, whatever information you are getting from the current neural network, that you add over here, whatever information you feel is required to be kept at a longer range, right? Whatever information you feel that yes, it is required to make long-term predictions, right? So you will be adding those details over here in this layer, right? And then this particular connection will keep on proceeding, right? In the next network, what will happen is that whatever you want to drop, whatever you feel that, okay, these details are not required now because when I came to this particular state, these details actually are not making, they do not seem useful right now, right? So you will, so in this particular cell state, you will be dropping on some of the previous content that you are getting from the previous layer, and you will add in some more data or some more knowledge that you're getting from this particular cell state, right? Now, this is what actually LSTMs do differently as compared to your typical models that we are talking about, like recurrent neural networks, right? I'll explain what each and every function is doing over here, right? So LSTMs also have this chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there will be multiple layers, right? Now, how these layers are working, I'll talk about that now. The key to LSTMs, so first we'll talk about the cell state, right? This particular connection that we have. The key to LSTMs is the cell state. The cell state is kind of like a conveyor belt, as I said. It runs straight down the entire chain with only some minor changes. It's very easy for information to just flow along it unchanged, right? So now if you see, this is a connection which is making it possible for information to flow right from the first network till the last network. If you feel anything is important, anything is required, you can kind of dump it over here, right? At a later stage, you might feel that, okay, Spain was important. So you could have gone back and you could have seen Spain, right? That, okay, Spain is there. But apart from this, the network will go ahead and make its predictions, right? If you see, the prediction part is going to happen over here. This HT is the prediction that you are getting from this particular network. Apart from all those predictions, you are also keeping a cell state intact. Now, this cell state will contain all the information that might be required at a later point of time. Okay, so this is the cell state that we talk about. I will go through each and every functions one by one, and then we can come back to how this, what is like, we will just combine this all together, right? I know there will be doubts, but let me complete this and then we will tie this all together. Okay. Now there are different gates, right? There will be different gates that will be defined when you're talking about an LSTM model. So gates are a way to optionally let information through. They are composed out of a sigmoid neural network layer and a point-wise multiplication application. The sigmoid layer outputs numbers between 0 and 1, describing how much of each component should be let through. A value of 0 means let nothing through, while a value of 1 means let all the data through, right? Now, if you look at this particular arrow, where is this? this sigmoid, this is over here, right? Now, if you see, what is happening is that the information, the xt are the features that we have from this particular state, right? Now, this xt, if you see, these are the set of features which are from this particular state. I am adding this to a gate and I'm adding this connection to the cell state. Now, whatever information from this feature and from the previous layer, this ht minus 1, this ht minus 1 is what? This is the input from the previous state, and xt is the input from this state. Now, this combined, first of all, I'm passing it through this particular gate wherein I'm using a sigmoid function. And the sigmoid function will range from 0 to 1. It will tell for, let's say, for particular features, it gives the value of 0. That means that no, those features should not, you should not add those features to the cell state. For some features, it gives the value as 1. So it means that yes, you should go ahead and you should add these features to the cell state. When we do a multiply over here, all we are doing is that we add in whatever is coming from the cell state, right? Whatever is coming from the previous cell state, you are going to add that over here with the new details that are coming from xt and ht minus 1. Okay, now that is the purpose of this sigmoid function over here. Okay, see, if you see over here, this is the same thing. The first step in our LSTM is to decide what information we are going to throw away from the cell state. This decision is made by a sigmoid layer called the forget gate layer, right? If you see, this is the forget gate layer. This will, what this will do is that whatever information you have to keep or not keep, you will be defining that over here. So first step within an LSTM that we do is that we define what information to keep and what information not to keep for future. Okay, that is the first step. Now the second step. The next step is to decide what new information we are going to store in the cell state. Okay, this has two parts. First, a sigmoid layer called the input gate layer, which decides which values we will update. Next, a TANH layer creates a vector of new candidate values that could be added to the state, right? So now over here in step 2, what we are doing is that we are taking new information once again. We are taking it through all the transformations that are required, right? So the new information we are going to store to the cell state. This is about the new data. Over here, the previous sigmoid function was about the previous data, right? So in the previous data, whatever was flowing through, what is required and what is not required. Now, this sigmoid and TANH combination that we are looking at, this is for the new set of features that we will be getting for this particular neural network. And for this, we will again go through all the transformations. This has two parts. First, a sigmoid layer called the this gate layer decides which values we'll update. Next, a TANH layer creates a vector of new candidate values that could be added to the state, right? So two parts. First is the single sigmoid function, which will only give us that what are the from the previous cell state, what are the things that you need to keep or what are the things that you need to delete, right? That is one. Second is for the current set of features, you will go through with the same set of transformations with sigmoid and TANH, and you will see what is the information that you have to add to the cell state that is flowing from behind. Okay, that will be your second step. Step 3, then we have to update the old cell state. Now, step 3 becomes the refreshing of the cell state, CT minus 1 into the new cell state, which is CT. So we multiply the old cell state CT minus 1 by your current output, right? So you will multiply this cell state by FT, which what this will do is that this will forget the outputs which it is not required to keep. Then we add the current state CT that we are getting. So if you see, when we multiply this CT minus 1 with this sigmoid, it will forget what is all the features which it might not require from now on, right? Then when we move forward, we add on the current state, right? So we multiply old state, then we add the CT. This is the new candidate value scaled by how much we decided to update each state value, right? Now over here, whatever the new features that were coming in from this for this particular neural network, we are going to add those values, right? That is your step 3. So till now, what we have done, we have only gone ahead and we have updated the cell state, right? In 3 steps. First step is using the sigmoid function. We have basically updated the previous cell state. We have decided what features we have to keep now and what we have to drop on account of the new features that are flowing into the network. So that is the first step. Second step is for the new features, we go ahead and do the same transformations, and we see what are the features that we have to add in the cell state. And the third step is that we go ahead and we add both of these functions together to the cell state, right? Now your cell state has been refreshed. From CT-1, you are able to get CT. Okay. Finally, you come to the output part. Finally, we'll run a sigmoid layer which decides what part of the cell state we are going to output. Then we put the cell state through tanh and multiply it by the output of the sigmoid gate so that we only get the outputs parts that we had decided to, right? So till now, if you see, if you focus only till this box, okay, till this box, we have not generated any predictions from this particular neural network. All we have done is that we have updated the cell state by dropping some features from the previous cell state, and we have given new features to the previous cell state, and we have defined the CT. Now we will be generating the output, right? The output is being generated by, again, using a combination of sigmoid and tanh functions. And then the output which is being generated by sigmoid, we have applied a tanh function to see what are the outputs that actually need to be updated to the cell state, right? Now, if you see over here, now this cell state that is going out from here, there are three major steps that have happened on the cell state. One, from the previous layer, the features which were not required, we have dropped that off over here, right? Then second step is we have added the new features that are coming in from this particular cell state, which might be useful at a later point of time. And then the third step is the output that we are getting from this particular network. We are going ahead and we are adding that output as well over here. Now your cell state is complete. Your output, you have gotten the output over here. This is what you can show over here. And then your cell state gets refreshed, right? Now this entire thing, this happens every time and till you reach the end of the network. Okay. And this, yeah. So this is how your LSTMs actually work.
Let's have a quick quiz question, guys. And the question is, dash or modeling is a method using when we program a computer to exhibit human intelligence. And your options are simulation, duplication, cognitization, or none of the above. Please mention your answers in the comment section below.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
So see, if you look at the typical recurrent neural networks, right? So whenever you are talking about the differences between a recurrent neural network and an LSTM, there is one term which is common that you will have to talk about, and that is the gradient problem that you have, right? So in your typical networks, right, in your typical RNNs, what will happen is that if you remember, I explained on Friday that let's say that you have connected multiple neural networks, right? Now the weights from one neural network are going to be a factor in the weights of the second neural network, right? Because at the end of the day, if you see the weight calculation that we are doing, how do we do that? We calculate the delta, right? So first that we do in order to calculate the weight is that we calculate your error. What is this? Original value minus predicted value minus predicted, right? This will be your error. Now let's say this is the error that you are getting in a recurrent neural network, which was created using 5 neural networks, right? And it was a connection of 5 simple neural networks, right? Now what will happen is that weights of NN4 or NN5 will be derived from where? Will be, let's say, differentiation of error by the different weights that you will have, let's say dw1 of NN5, right? Like this, you are going to calculate the weights of NN5. Is it correct? Because if you see, fifth network will be the last one which is connected to the to your predicted values, actual and predicted, right? Now similar to this, weight NN4 will be what? It will be a function of again D error, right, by, now I'm just taking an example here. Let's say dw1 of nn5, this whole term multiplied by, right, this whole term will be multiplied by dw1 of nn5 divided by your dw2 of nn4, let's assume, right? So now if you see, in order to derive nn4, I have to multiply the weight of nn5 to this. Does this make sense? Now this chain of events will go on, right? Now similar to this, weight nn3 will be, I'm just writing it simply over here, multiplication of weights from nn4 and nn5. That's correct, right? Similar to this, weight nn2 will again be this, right? Okay, and similar to this, weight nn1 will again be multiplication of nn2, nn3, nn4, and nn5. Does this make sense, this part? So don't go behind the mathematics over here. The mathematics will remain the same that we have seen in case of a simple neural network, but this will be very complicated maths, which no one is going to ask you. They will just want to ask you the intuition behind why we are actually going ahead and creating long short term frameworks, right? So the intuition will be something like this. Okay. Now, if you see your weight, okay, if let's assume your weight nn5 becomes is, let's say, 0.01. Okay, I'm taking a simple example wherein I'm taking that all the weights are in the range of 0.01. Okay, but the weights values can be lesser as well. Okay, now if I take this so on till nn2, what will my weight nn1 become? All the four weights for my nn5, nn4, nn3, and nn2 are 0.01. So what will the weight of my nn1 become? Generally, if let's say if I just multiply these values together, it will not be the same value. Yes, that's correct. Classmate. So 4 times something like this, right? Now, if you see, this is your nn1 weight, right? Now nn1 is what? nn1 is the weight through which you are going to again start the training of the network. Is that correct? Now this value is so small that what will happen is that now once again when you're going to move forward, right, to train the weights, now this small value, you will again multiply this by all the weights that you are going to get from nn2, nn3, and nn4, and this will keep on becoming smaller, right? And when it is becoming smaller time and again, what happens, that gradient descent that you are applying, wherein you are calculating the delta, that is the difference, that is the differentiation of weights, differentiation of error with respect to the weights, right? Now because the weight value becomes so small, it's that your uh, in these cases your lstm or your models, whatever you are building, right, it will get stuck. It will not be able to give you the best value of the weights because the weights have become so small, right? So this is the problem that you have with your recurrent neural networks, right? Because what happens is vanishing gradient problem. Right now, this is the problem that we have with our typical networks, and because of this, we actually introduce what? We introduce LSTM, right? Solution is LSTM, right? What does an LSTM do differently over here? LSTM includes a cell state right, which carries forward the weight of all previous iterations separately. Okay, so basically this is what an LSTM does. Okay, so an LSTM will help you in solving the gradient problem, wherein your gradient becomes either very small or very large. Right, that is the only, and that is the major difference that you have between a recurrent neural network and an LSTM model. Okay, great. Okay, so let's start with the case study. Again, in this case study, we are going to apply an LSTM model in order to solve a time series problem. Okay, so let's get started. We'll first look at the data, and then we will see how we can apply the model. Okay, uh, even for people who are not able to understand the theory behind LSTM, let's say some part of it is clear, most of the part is not, right? Don't worry. Focus on this. If you are able to understand this, if you are able to run this, and if you are able to create similar LSTM models out of some other data, 90% of your job is done, right? Don't worry about the theoretical aspect. That is something that you can maybe read upon it and all, and you will be able to answer crucial things that there are. But LSTM, as I said, again, it's a very complicated model, right? Most of the people, there might be researchers and people who are actually working on this model who might exactly know that how complicated this model is, and who might be able to list down the maths of it, right? But most of the people who are just using an LSTM model in order to solve any business problem or use case, right? Their major focus is upon how to implement an LSTM, how to tune an LSTM model, and if you're able to do that, that is what will be the main ask from you always whenever you're working as a data scientist, right? Okay. Okay, so we will import the libraries NumPy, matplotlib, pandas, datetime. Datetime we are importing because we have to convert our variable which contains date as a datetime variable. For scaling, we are using min-max scaler. From TensorFlow.keras.models, we are importing sequential, and TensorFlow.keras.layers, we are importing dense, dropout, and LSTM. So you can see that from a code point of view, the changes will not be many. Okay, so only LSTM is there, which we are importing, which is extra as compared to your simple neural networks. And if I compare this to convolutional neural networks had more imports as compared to an LSTM, right? You had convolutional layer, you had max pooling and all, so you had to import those as well. But in this case, you just need to import LSTM, and obviously your dense and dropout and sequential, all this will be there. Okay, so now we will read this data. Once we read this, I will show what this data is to you. Okay, so now we have read this, and this is the data that we have, right? If you see, we have the date and we have the temperature corresponding to each and every date, right? Let's do a describe and see the ranges. Sorry. Okay, so you can see that there are different ranges, but date variable is not here. Why? Because date probably will be an object variable, so we'll have to convert that into a date time. Okay, so this is previously into date time only. Okay, so first look at this data. So what we will be considering in the time series model are only, so if you see, what is the time series? A time series is any data that is spread across time, right? Now, if you look at this over here for the time series model, so our objective is what? Our objective is to look at this, right? We are looking at the date and the temperature. So our objective is to go ahead and predict for future dates what will be the temperature that you might be seeing, right? Now, if I do Florida.date dot max, right? Should be a function. So if you see, you have data till 2013, right? 1/9/2013. Okay, and the minimum is what? Minimum is 1743. Okay. How many rows do we have in total? We have 3239 entries, right? So we have almost 3 decades of data. Yes, Shiva, I'm doing that only. Just wait for a second. Okay. So if you see, we have, okay, so let me first filter the data and then I will show you what is the problem statement. Okay. Now, this is the data. In this data, we are only going to consider 2 variables. Why? Because see, this is a time series problem and I have to predict the average temperature for future dates, right? So if you see, I have my temperature data till 2013. Okay, now what if, so see what happens is that there are use cases in the business wherein, let's say your business is doing some sales, okay, and they have all their sales related data for past 10, 15 years, whatever, right? 5, 10 years. Now, what a time series model does is that a time series model captures the seasonality in the data, captures the trend in the data and all, right? So first of all, seasonality. What is that? Can you guys give me an example of seasonality by the name, right? If you are able to derive what seasonality should mean from the name, just the name part, right? What can you understand could be seasonality in a data? If you take temperature, for example, right? So what should be seasonality? Amir, the question is that given a time series data, so if you are given a term, explain seasonality, right? I know that you guys don't know seasonality, but looking at the definition of seasonality or season, right? What can you infer about the data over a certain period of time? Yes, but okay. So if you see, if I look at temperature, yes, right? How temperature varies over a certain period of time. So is there a seasonality? What do I mean by seasonality? Temperature changes with seasons, exactly, right? Now let's say I give you 5 years of data. Okay, so for each and every year you will see a similar pattern, right? You will see that, okay, if I talk about Delhi, that you will see that starting from January going till April, the temperatures are maybe on the lower side, right? Now from April till, let's say, October, the temperatures are towards the higher side, right? And then once again from October till November, December, your temperatures are once again lower, right? So if I would want to plot this data, let's say if I plot the temperature data for Delhi, okay, for only 1 year, how will that look? I'm just giving you an example, right? So let's say I am starting with let's say I'm starting with January. So your January will be somewhere over here, January till March. Let's say March, April, May, June, July, it is going up, it is peaking, then once again it is coming down, right? This data will be something like this. Okay. Now over here, my year will change, right? My year will change and you will see a similar pattern in the data once again for the second year. Is that correct? Right? Once again, my year will change and you will once again see a similar pattern in the data, right? That's correct, right? So this is what you can refer to as seasonality, because you see the effect of seasons. Because of the effect of seasons, what is happening? Yes, your data is changing between an year, but it is going to repeat each and every year, right? Like this, like the temperature data that we are seeing, there can also be sales related data. Now, can you infer or can you correlate the seasonality to iPhone sales? Or let's say sales we see on Flipkart and all. How can you infer that, right? So let's say sales of electronic gadgets, that what can be the seasonality? So can you guys tell me what can be the important days wherein you might see that okay, the sales are going up or the sales are going down? Just some intuition from your maybe how you shop, right? So there are some specific days on which there are lots of discounts, right? Then there are specific days, festive seasons, exactly, right, Shiva? So see, now what happens is that whenever you will plot any sales related data of any company, depending upon the country that they belong to, depending upon the festive seasons, depending when they are giving an offer or a discount, your sales will either plummet or your sales will go up, right? The sales might plummet as well. How can they plummet? Because see, before a festive season is about to come, the sales are supposed to go down because most of the people will be waiting for the discount season, right? Or let's say if we talk about specific products, right? So when a new phone launches, right? So let's say on the launch of iPhone 14, the sales of other phones might go down, right? So this is something that you will be able to plot through uh, when you plot the data, right? You will have to capture the seasonality and all, right? Now, this is something that a deep learning model will be able to do very well, right? The trend of the data, the seasonality of the data, all these things are something that you associate with time series data. And this is something that we are wanting to capture over here, right? Now, okay, one second. Okay, if you look at this, right? Now let's say this is the training data that is given to you. Okay, let's assume that this is the training data that is given to you for 3 years. Okay, that if someone asks me what will the distribution look like over here, will you be able to do that? Yes, right? So if you see in these time series models, what is happening? The target variable that we are wanting to predict is actually the feature that we are going to consume, right? If you see over here, I am actually plotting my target variable only for the past 3 years. And using that data only, I'm going to go ahead and make predictions for my future news, right? So that is how we actually work with time series problems. Okay. And that is why over here, what we are doing is that we will first of all limit our data to only two variables which are important to us, that is the date and the average temperature. Okay. If you see over here, I have just restricted this data frame to date and temperature. I have gone ahead and I have done a fill in it, right? And I have changed the column names to date and average temperature. Okay. Now, see what happens. If you see over here, bfill is a function which is backward fill, right? Now, what backward fill will do is that for time series data, usually what you will do is that if let's say that there is a missing value, okay? Let's say that the missing value is for 7th of March. What backward fill will do is that it will go ahead and take the average of the last 4 weeks and it will replace the value of 7th of March by the average of days from 6th of February till 6th of March, right? So for time series data, you cannot go ahead and you cannot make predictions. You cannot impute missing values by taking the mean, median, or mode, right? You will have to go back and you will have to take, let's say, an average of a week, 2 weeks, 3 weeks, 4 weeks. And on the basis of that, you will have to make the predictions. You can use the mean, but do you think the mean will be useful? You know that when, let's say, 7th of March, usually 7th of March, temperature should be towards the lower side, right? Now, if let's say you go ahead and you take the mean of the entire data, that value might be slightly off as compared to if you're only focusing on the previous month or the previous week, right? This is something that you can choose. Okay, right? So it makes sense because you are actually imputing the missing value by a value which might be much closer to the actual data. So that's why we are using this. Okay, so now if you see, our data has changed, and this over here, this is the data that we are going to consider totally. Okay. Okay, if you see over here, access none, in place, limit, right? Downcast. So in limit, you can pass the number of days that you would want to have. Okay. Okay. So now comes the important part, right? So when I said that our target variable is only our feature, right? What did I mean by that? Okay. Now let me take an example. First, I will show you what we are trying to do, what is the intuition behind whatever we are doing, and then I will tell you why we are doing this, right? Let's say temperature. Okay. Okay, let's say we have these 10 days, and let's say we have a land between 10 to 30. Okay, so let's say these are the temperatures, right? Now let's say this is the data that you have. Okay, it will look similar to this only. Okay, now look at this, right? Now let's assume that this is our training data. Okay, let's assume that this is our training data, and we have to predict, let's say, for the next day. Okay, and this is our testing data. Okay, this we have to predict, right? Now how will a time series model do the predictions? Okay, now let's say I say that your time step is 3. I will tell you what this time step means, right? Let's say I say that your time step is 3. What will happen is that we will have to transform your data on a certain basis, right? Now, when I give the time step as 3, I will maybe consider only these rows. I will tell you why. Don't worry. Okay. And now this becomes my target variable. Okay. This becomes my target variable. Why? Okay. So what was the temperature on 4th of January? 24 degrees, right? What was the temperature on 5th of January? 30 degrees, right? This is the temperature that we are taking. Now, when we give a time step of 3, that means that we are taking 3 features, right, of the past 3 temperatures, right? Now, over here, feature 1 will be the temperature that we had seen on 1st of January. When we are looking at 4th of January, we are going back 3 time steps. Okay, so we are starting from 1st of January, and we say that, okay, on 1st of January, temperature was 16. On 2nd of January, temperature was 27, and on 3rd of January, temperature was 11. Okay, so if you see 27, 11, and 24, right? Now, like this, you can populate this entire data. You can, right? Now, this will be 11, 24, and 30. Okay, this will be 24, 30, and 14. This will be 30, 14, and 22. This will be 14, 22, and 13. Just make sure that you are able to follow guys, right? And this will be 22, 13, and 16, right? Now this becomes your training data. Okay, and on this you are going to train the LSTM model or whatever time series model you are applying on the data. Now, once you have trained this model, it will give you future predictions. How? Now, as soon as you give the data that, okay, this is your date, right? And you give the data till one day before that date, right? You want the predictions for 11 for this particular date, 11th of January. So you will have the data till 10th of January, right? If you're sitting on 10th of January, that means that you have the data till 10th of January and you want to make predictions for 11th of January, right? Now, what you will give over here, the features for the last 10 days, right? Sorry, the temperature for the last 3 days, right? So this will become your oh, sorry. Okay. Now, does this make sense? 13, 16, 18? Yes, right? And now I have to predict this date. Okay. Now my model will be able to predict this particular date if I'm training it on something like this. Okay. Okay. Then apart from that, we have done nothing. Don't worry. Okay. So after that, I was showing just this data which you had asked for, right? This is the data that we have. And on this, we are going to make the transformation now. Okay. Okay. So see, original data had all these columns, right? Your average temperature, date, year, month, day, right? But we have only limited this to data and temperature. I explained right now that in time series, we are actually focusing on the target variable only. From the target variable only, we are creating features. That is why we have limited this data to date and the temperature part only. Right now, we will be working with only this part of the data and date and temperature. Okay. Okay. So let's get started with the transformation, right? So whatever we have done over here in the Excel, right? That is something that we will be doing over here as well, right? Now, what we are doing is that we are considering a time step of 225, 225 previous steps. What does that mean? That means that I will be looking at the previous 225 observations in order to make prediction for the next month's temperature, right? So in the Excel, I had taken the example of 3 time steps. Okay, time step equals to 3. So like this, you can imagine that I am taking a time step equals to 225. Okay, 225 features, right? Yes, exactly. So that's what we are doing. And now see this again, this 225 that you're seeing again, this is not something which is hard coded, right? You can go ahead and you can play around with this this time step that you are deciding, right? Now let's assume you feel that for your sales data, previous 2 months of sales is critical for us to determine the sale for, let's say, the next week, right? Then in that case, you can go ahead and you can take the time step as, let's say, 60 days, 90 days, whatever, right? So on that basis, you can go ahead and you can calculate the data. Now, if I come back to the Excel, you will see that originally I had what? I had 10 rows in the Excel, right? But after the transformation, we had how many rows? 7, right? So this happened why? Because the first 3 rows actually became features. Okay. Now in this example, if I have, let's say, 1000 rows, then after transformation, how many rows will I have? So we will be having 1000 minus the number of time step rows, right? So this will be your answer, which will be 775. Okay. Not sure why it's not having, right? So this is how your data will actually reduce, and we will see this will actually happen, right? Now coming to this part, how do we do this, right? So we will go through this step by step. 225 are the number of features. right? Yes, Asmat. So now, first of all, let's divide this data into training and testing. Okay, we will divide this data into training and testing, and then we will go ahead and we will convert this data to the required format. Now, another key aspect to time series model. Now, if you remember, for the simple machine learning models, deep learning models, how are we taking the train and test? 225, because we have considered a time step of 225, right? So that means that the first 225 temperatures will actually become the feature for the 226th value, which will become the target variable, right? So this is how it will create the data. Previous 225, right? So if you have over here in the Excel, if you see, I had 10 rows, right? Right. So similar to that, if I take a time step of 225 and let's say I have 1000 rows, I'm assuming I have 1000 rows. So after transformation, we will be left with how many? 775 rows. Okay. Okay. So now the second part that I was talking about. Okay. So my question was that how did we divide our data into training and testing in case of non-time series data? We would take a random sample, right? We were using a train test split function, if you remember, and there we were taking we were giving, let's say, a test ratio of 0.3. Now what that will do is that it will pick up 30% rows randomly, right? Okay, so first of all, when we took random values, right? If let's say I had 10 rows of data, I can take any random values. Let's say I'll take the second value, I'll take the fifth value and seventh value, and that will become my testing data. Okay. But in a time series model, can you do that? Can I take random points from here? Let's say I decide that I need to have my test data. Can I take random points like this one and this one and this one? No, right? I will have to take sequential data only. In case of time series, I can only take sequential data. I can take this maybe as my testing, right? Because else I'm going to break the entire pattern, right? So I don't want to do that. Hence, in case of time series models, you will have to split your data in a sequential way only. You cannot pick up random points. Okay. So initial 7 rows, let's say if I consider as training, I can build my model using this. I can test my model using, let's say, the last 3 rows, and then I can go ahead and I can definitely print it. I can predict the value on any unseen data. Okay. So now let's understand this. Okay. I will split this so that you're able to see, right? If you're taking, let's say, this point as a test data, right? That means that your sequence for your train data will break, and here in the features you will have missing values. So that is why you can only have sequential data. Okay. Okay. So now let's see how we are creating train. If I want to take all the rows but the last 225, how will I do that? I will do this, something like this, right? Colon minus 225 will do what? It will filter my data. It will only keep the data the till the last 225th row, and all the last 225 rows will not be included over here, right? If I show you this data, index is what? 3013, and in this data, which was my whole data, my index was what? 3238. If you subtract 3238 by 3013, you will get 225, right? So essentially we have skipped the last 225 rows and we have only focused on the first 3014 rows. Okay, when we are doing minus 225, right, this is for reverse, you will have to give one more colon and then you will have to give -1. We are not doing that, right? When you give something like this, so this is saying that go till the last, don't include the last 225 rows, go till the end, but don't include the last 225 rows. Okay, okay, right? So now we have our train data. We have kept all the rows but the last 225, and similar to that, we can also get our testing data. How? I am saying that only consider the last 225 values, right? So this is the syntax, and if I do a test.tail, you will see, right? See, this is from 3 till 3238 only. And if I do a test.head, you will see that it will be starting from 3014. Okay, so these are the last. And if I do a test dot, let's say info, you should see 225 non-null values, right? Does this make sense? So see guys, this filtering is something that in NumPy classes, this concept should have been clear to you. If it is not clear as of now, you can go with this, right? But this is nothing. All we are doing is that we are actually limiting the data. And over here we are saying, so over here, if you see what are we saying? We are saying that the starting point is basically minus 225 from the end, right? Over here, we are saying that the ending point is actually minus 225. Okay, anything which is towards the left side of the colon will give you the starting point, and anything which is on the right side of the colon will give you the end point of the filter. Over here, when I'm doing minus 225, I'm saying that the end range for this filter is actually 225 rows before the last row, right? Over here, I'm saying that the starting range is 225 rows before the last row. So go from this row till the last row, right? After this is done, right, take any stock data. You will have 5, 10, 15 years of stock data, right? If you're taking, let's say, any blue chip fund, whatever, take that data, get this data in the similar format, date and the price, and you will be able to make predictions on that. And you will see LS teams are actually able to make quite good predictions there. Okay. Okay. So now I'll move forward. Over here, once again, I'm just converting this to date time. See, when we are doing date time, right? If you see when we use the backfill function as well, right? So your Python, first of all, for time series models, it becomes easy to manipulate data. It becomes easy to split the data into training and testing. And Python knows that this is a time series data, right? So if there are any missing values, right, then if let's say you are doing a backfill, it knows that it has to go on the basis of the date and it has to do the backfill, right? So that's why it's always suggested you convert your date variables to date time variables, right? It becomes easier to implement time series models in that way. Okay. Okay, so now we have, what have we done till now? We have only we had our original data with some features. We restricted that to date and the temperature features. After that, once when we did that, we have split that data into training and testing, right? My training is all the rows but the last 225. My testing is all the last 225 rows. Okay. Okay, so now we will, first of all, we will scale our data and then we will do the transformations that were required. Okay, so we will scale our data using min-max scaler. Neural network models, you remember, we need to scale our data, right? So you see min-max scaler, we have scaled our data and this becomes our scaled data. Okay, now if you see, now we have gotten rid of the date. Okay, we have only done the fit transform on train average temperature. Okay, And just to be sure, I have reshaped this once again just to make sure that I have the values in the correct dimension, right? So if you see over here, my dimensions are correct. It is in the long form only, right? If I look at the length of this data, what should be the length? 3014, right? If you see, this is a single data with like this is a NumPy matrix with 3014 rows. Okay, and now from this we will create our transform data which we were looking at in the Excel, right? Is this part clear? This is just the scale data that we have. Now that we have all our data, it was sorted by date. Now date is something that we don't need right now. We only need the predictions, and then we can we only need the target values because we know that these target values are sequenced in uh, right from the start date till the end date, right? So now I'm at a good place. I can go ahead and I can start doing the data transformations. Okay. Now I set once again my prediction days equals to 225. Okay, this is what I have put over here. And I initialize two empty lists, X train and Y train arrays, right? Now I will do the transformation. What am I doing over here? I'll show you. Okay. Now, how do I get the data? Let's say I have to focus on the last 10 rows. Now, what if, let's say I want to see the first row of this data. Okay. Sorry. Okay. So let's assume that we want to see 0. And 0. Okay. Okay, sorry. Right now Xtrain is empty, right? So we'll have to first run this. I'll run this and then I'll show you what this means, right? I'll explain this code to you. Don't worry about this. Now, if you see Xtrain, okay, what if I want to see the 0th row? Okay, this is 0. Oh, sorry, what am I doing? This should be scale data. Okay, now just take a look at this, right? I will explain this from scratch to you guys. Don't worry about this, right? No, this is fine, Amina, right? So now see, this was a scale data. This was it, right? It is an NumPy array. Okay. Now, if I want to look at the first observation, which was 0.33, I have to do this, right? If I have to look at the second observation, it was 0.56, right? I'll show you the second observation, right? This was 0.56. Okay, the third observation was once again 0.56. Okay, what if I want to see the first 3 observations? I will do 0:2. Okay, 2 will not be included, so I will do 0:3, right? So this is how you can get the first 3 observations, right? Now, similar to this, if I do 0:225, what will I get? I will get the first 225 observations, right? Okay, so this will be my feature set for my first row. But what will be my feature set for the second row? It will be 1 till 226, right? Right? Yes, sir. So 224. So essentially 224 are considered and 225th will be the target variable, which we'll get, right? So that's how we're doing, right? So now if we do 2:227, we will get what? We will get the feature set for the third row, right? Now this is what exactly we are doing over here, right? If you see over here in this code, we are iterating from prediction days till the length of scale data. Prediction days is what? It is 225. So this loop will start with x equals to 225 and go till what? Till the length of scale data, which is what? Which is 3014, right? That is the end of my training data. Okay. Now for x train, which is a blank NumPy matrix, it will append the first row. How? It will append your scale data and it will do this. X minus prediction days. First of all, what is X in the first run? It is 225 and my prediction days are also 225. So this will become 0, 0 till 225, right? So in my X, I will have the first 225th values, right? From 0 till 224. Okay. And in my Y train, I am just appending this X, right? Which is actually the 225th value in this case, right? Now, if you see, when I'm taking in X train, when I'm taking the values from 0 till 225, right? I'm getting the values till 224 only. Okay, so they will become my 225 features. And in ytrain.append, I'm only focusing on the 225th value, right? So my first 225 temperatures become the feature, and the 226th feature, right, becomes the target variable. Okay. Now in the second case, what will happen? Your X will become 226, right? 226 minus prediction days, which is 225, will be 1. So this will go from 1 till 226. Same thing which we have talked about. And over here, it will take the Y value of 226. Okay, so first let me show you the output. Then we will go to this again. Okay. So if you see, this is your X train, which is a kind of a list of lists, right? One second. So now this has become actually complicated data, which is tough to visualize as well, right? But let's see. Okay, so if you see, this is X train, right? Now, if I do X train 0, I will get the set of my first 225 values, right? If I take the len of this should be what? This should be 225. 225, right? And if I take Y train of 0, this should be the 226th value. Okay. Now, one second. If I come back to my scale data, right? In scale data, what was the 224th value? 0.795. Okay. And if I run this, if you see X train 0, your last value should be 0.795. Does this make sense? If you see, the last value is this. And now if I go to the 225th value, this should be my target variable, 0.643. And if you see, this is your Y train value, right? So what this code has done is it has created my data in a similar way, which I was doing in the in the spreadsheet, right? It has kept the first 225 temperatures as features and the 220 and the next one value as the target variable. Exactly, right? Okay, so Hasmit, you want the scale part. So Hasmit, we always scale the data, right? You're talking about what part? The scaled data part or the scaling part that we're doing? Okay. Okay, so first of all, let's come here, right? Over here, we have done the scaling. I hope no questions here, right? Scaling is something that we always do for any neural network model, right? Now, once when we had scaled our data, this is how our data looked like, right? What was this? This was 3014, initial 3014 rows, right? I hope this makes sense. We had just split our data into training and testing. Training contained 3014 rows, testing contained 225 rows. Okay. Now over here, I have defined in the next one, I have defined the prediction days as 225 because I'm taking a time step of 225 days. Okay. And I have initialized two empty lists, X train and Y train. Okay. I'm doing this once again. Now, if you see X train and Y train are empty, right? Now over here in this loop, I'm iterating from what is the value of this scale data has only one column, right? It is an array, first of all, right? But if you see the shape, so explicitly we have given the shape as 3014 comma 1 over here because we wanted to do all these transformations, right? But if you see, it only actually has a single value. Okay. This is your scale data. If you see the length, it is 3014 only. Okay, one second. Let me show you this data directly. What is this? This is this, right? If I just take the temperature column, what is this? This is just a column. This part clear? If I do values, these are just this data converted into an array, right? But if you see the array over here is what? It is in the form of a row. Okay. Now what I do, I reshape this using -1. You have to transform your row into column and you have to add one additional dimension, right? Now, if I would have done this, right, cannot reshape array of size because this is in the same shape, right? I am giving a -1 because I want to transform the row into the column, right? Previous to this, my data was in a row format, was it? Now, when I do -1, what I'm saying is that whatever shape, whatever dimension you have, transpose that to the other dimension, right? Now the second dimension that we have is this one. So we are transposing this from a row to the column. This will work, but I'm not sure. This will not work, right? This will just convert this into an array. When you are doing -1, 1, you are actually transposing this to a different dimension from your x-axis to your y-axis. Same. Okay, right? So see, this is again, take this notebook, play around, and you will be there are some syntaxes which are very specific. If you're not familiar with the syntaxes, you will get confused, right? So reshape -1, 1, this is something that we use because we want to transform from, let's say, transform the data from an x-axis to a y-axis. Over here, I had to transform the data which was in a kind of a row-based format. I wanted that into a long form, a column-based form, right? So for that, we have used this. So I will run this again, okay? And then we will run this. 2789, right? 2789 plus 225 is what? 3014, right? So basically, we have, initially we had 3014 rows. Now 3014 minus 225 will give you what? 2789. Right? And now this is the amount of rows that I have in my training data. Similarly, I will have these many values in my Y train as well, right? It should have 2789 values because all these are corresponding values. right? 2789 and 2789. So now we are again coming to a step which might confuse you, but this is again a requirement of LSTM models. I will explain this to you. Okay, so first of all, now we are converting your X train and Y train into NumPy matrices arrays, right? Because if you remember, LSTMs, first of all, LSTMs will work faster with NumPy data, right? If you are feeding in Pandas data, it will take much more time. All our transformations have been done using NumPy matrices only, and your processing time for LSTMs will be faster. So we mostly for all deep learning models, if you see, we have always converted our data from data frame into a NumPy array, right? And that is what we are doing over here as well, right? Now, if you see the shape of X train, what is the shape of X train right now? This is the shape, right? 2789 and 225. Does this make sense? Why? Because for each and every row, we have 225 features. That's correct, right? Okay. So now I'm doing something like this. First, I will run this and then I will show you why we're doing this. See, this is something that this is the form in which your LSTM requires the data to be. Okay. It needs to be a three-dimensional data, right? So in order for LSTMs to run, right, for whatever data that you are passing, right? So you can just imagine how is this? If you try to imagine this, this is what? This is a square. This is a rectangle of the dimensions 2789 cross 225, right? If you just visualize this data, this will be what? This will be something like this, right? But for LSTMs to run, you need your data into be a three-dimensional format, right? So if you see, we have just gone ahead and we have actually added one more dimension over here, which is a blank dimension, right? There is nothing that we are passing over here. And this is something that you will always have to do whenever you are working with LSTMs and two-dimensional data, right? So this over here, if you see, we have just added one dimension, making this as a cube. Okay, 2789 comma 225 now has become 2789 225 comma 1. Okay, might not make much sense, but this is what this is how we actually have to do pass the data when we are actually working with LSTMs, right? Now I will tell you at a later stage how you can leverage this third dimension as well, right? So at times you will also want to have additional features, right? So let's say you are working on a stock prediction model, right? You will obviously be using the historical data for stocks, but you will also be using some additional features such as, let's say, market triggers, right? When was the stock launched, or let's say there is something, what is the current scenario in the market, right? How is the country performing, and so on and so forth, right? If you want to include all these parameters as well in the data, then you can include all this in the third dimension that we have over here, right? So we will talk about this later, but as of now, you can just understand that this is how your LSTMs will process. Your data should be in a three-dimensional format for LSTMs to process, right? First of all, you will have your rows, then you will have your columns, then you will have your height, right? Now over here, obviously this is blank, right? If I would have, let's say, added a new dimension to this, then this would have become 2. Okay. See, now we will start with our model, right? And you are just saying, see, you can consider a 2 cross 2 matrix, right? Let's say you have a 2 cross 2 matrix. Either you can consider it as a 2 cross 2 matrix, or you can also consider it as a 2 cross 2 cross 1 matrix, right? Assuming that the height of the third dimension is what? It is 1. It is not adding value to your data, right? It's just that you are visualizing it that way, right? You can consider a chessboard as a 64 cross 64 matrix, right? But you can also consider it as a 64 cross 64 comma 1 cube, right? And saying that the width of the cube is very small. You can do that, right? So that is what we are doing over here. We are just, because the LSTM models work in such a way that they need three-dimensional data, right? These are complicated models, right? Hence, we are actually, so if you talk about CNN data and all, image data and all, whenever you will be feeding your image data to LSTM models, that will be a three-dimensional data only, right? So in order to meet that uh, constraint that we have when we are running LSTM models, we have to transform our data from 2D to 3D. And that is what we are doing over here. np.reshape, we are reshaping xtrain. What are we giving? We are giving the same shape that it has before, shape 0 and shape 1, but we are adding one more dimension to it as well. So now let's get started with the model building. I'll show you this, how we apply an LSTM model, right? So now see, everything is done. Our train data and our test data is ready. Our xtrain, mytrain are ready, right? Now we will move forward with the model build part, right? So if you see model, we initialize the model as sequential, right? And now in add, instead of, if you remember previously, we added a dense layer, right? Now the only difference that will happen over here is that in case of LSTM, you are adding an LSTM layer, right? Now this LSTM layer that we are adding will apply every theory, the of whatever the back propagation is happening, the cell state, the AND gate, OR gate, right? All those things will be defined over here. So you don't have to worry with that. It's just that you are defining an LSTM, right? Now this LSTM framework that you have defined over here, you have defined it with 128 nodes, right? Neurons will be 128, but these 128 neurons will be of the type LSTM. Okay, activation becomes ReLU. Return sequences is true. I'll tell you what this means. Okay, so return sequences equals to true means that to the next layer, to the layer that is going to succeed this layer, right? To the second layer, you have to return everything, right? So you remember the cell state part that we talked about. So this is something to do with this, that all the sequences and all the interactions and weights that you are getting from this first unit, you have to uh, take them forward to the second unit. You have to take them forward to the third unit, right? This is what return sequence equals to true will do. Now, input shape over here, obviously, we will have to give the input shape. Now, if you look at this, what is xtrain.shape1? This will be the number of features that we have, right? So if you see, this is 225, 1. Once again, if you see over here, we are just focusing on this part. Now, if we would have multiple dimensions of the data, over here, you would have, let's say 225, 2, 3, whatever, depending upon the number of dimensions that you had in the data. But over here, the feature space is only one dimensional. But because LSTMs work with three-dimensional data, we have to give this shape in this particular way. Okay, this is the first layer that we add. Then we add a dropout of 0.2. Then we add one more layer, LSTM 128, activation ReLU, return sequences is true. Input shape we don't have to give now because this is a layer which is connected to a previous LSTM layer. Dropout is once again 0.2. Then again we add one more LSTM unit, same, activation same, return sequence becomes false, right? Return sequence becomes false over here. Why? Because after this we are defining the final layer which will make our predictions, right? So for the output layer, so now whatever this LSTM layer will get, this will be the final output that will be fed to the dense layer. Okay, so see, input shape over here, right? So you saw this was the shape of the data, right? Now if you look at this data, it has 2789 rows, and each row will have a dimension of what? 225, 1, right? So that is what we are giving over here. Now, assuming, let's say you had multiple features, right? So in case of LSTMs, if you are adding a feature, let's say apart from the target variable that we are capturing for the last 225 days, we also wanted to capture what was the wind speed for the last 225 days, right? That would have come in the second dimension. So then in that case, my data would be 2789, 225, 2, right? But over here, because obviously we are going ahead with only single feature, so we have to give 225, 1, right? And that is why the input shape that we are giving. Again, the basic funda is that LSTMs are intended to work with three-dimensional data, right? And that is why the standard LSTM code that we have in Python works with three-dimensional LSTM data. Now, out of the three dimensions that we have in the data, one dimension is what? One is the number of rows that you have, right? So that, if you remember, in case of a neural network model, you are only feeding the features and it will iterate through the rows one by one, right? So we are not focused on 2789 here. We are feeding this 225, 1 to the model. And that is what we are feeding over here. Yes, we eventually passed a 2D data, but see, it is not 2D. At the end of the day, it is what? 225, 1, right? So it is saying that these are 225 values, only one dimension. The second dimension doesn't have any value. There is no second dimension over here. Just to make the LSTM run, because the LSTMs are working with three-dimensional data, we are making these changes. LSTMs, and we are feeding 225 features. It might be possible that some of the temperatures in the past might not be dependent upon your future temperature or vice versa, right? So that's why, because 225 features are a bit too much, and LSTMs we are giving, right? So LSTM once again is a complicated model. So hence, in order to make sure that the model is not fitting very well to the training data only, we have given. It's not that over here I'm assuming that 20% of the neurons will be deactivated, but after seeing the performance, if you're seeing that no, this 0.2 is a very small value, you can go ahead and you can increase that as well, right? This is the same exercise that we have done before, right? You will have to see that how your model is performing, and on that basis you will have to tune these parameters. Okay. Okay, so after the third LSTM layer, you can see that we have just finally added the dense layer, unit equal to 1. Okay, now this is the final, and then we compile the model. Optimizer is Adam, loss becomes mean squared error, right? Let's look at the model summary. So this is your model framework. Now you can look at this. This model will be tuning 330,000 parameters, right, to get us our predictions.
Let's have a quick quiz question, guys. And the question is, what was the name of the very first AI programming language? And your options are Lisp, Fortran, IPL, or Basic. Please mention your answers in the comment section below.
Okay, so this is done. Now we will fit our model, right? So model.fit, we are passing X-train and Y-train. Epochs are 25, batch size is 32, validation spread is 0.1 that we are giving over here. And everything else remains the same, right? We run this. This will take some time. Okay, this training will take time because again, this is an LSTM model. And I think this will take more than. So now if you see, compared to your simple ANNs and your CNNs, your LSTMs will obviously take much more time because there is lots of processing that is happening, right?
Well guys, moving forward, let's talk about top 25 artificial intelligence interview questions most commonly asked in an interview setup. So let's begin with the first question on our list. The first question we have is, what is ANN? Basically guys, ANN is an acronym for Artificial Neural Network. ANN is a computational model based on the structure of the biological human neural network. The human brain has billions of neurons that collect the information, process it, and drive meaningful results out of it. The neurons use electrochemical signals to communicate and pass the information to other neurons. Similarly, ANN uses artificial neurons, or what you can call as nodes, and applies mathematical transformation to convert given information or input to the desired effective output. There are three layers in the artificial neural network. The first layer is input layer. The input layer has neurons that take the input from external sources like files, datasets, images, videos, and sensors. This part of the neural network doesn't perform any computation. It only transfers the data from the outside world to the neural network.
Then comes the hidden layer. The hidden layer receives the data from the input layer and uses it to derive results and train several machine learning models. The layer can be further divided into sub-layers that extract feature, make decisions, connect with other sources and predict future actions based on the events that has happened by now. After that comes the output layer. Once the processing and computation is done, the data is transferred to the output layer for delivering it to the outside environment. So this is how you can explain what an ANN is. After that, the next question we have on our list is, what is the difference between AI, ML and DL? Machine learning and deep learning are subsets of AI and are used to achieve the goals of artificial intelligence. Now let's highlight the differences between AI, ML and DL. Artificial intelligence consists of the algorithms and techniques that enable a machine to perform the task commonly associated with human intelligence. The AI applications are trained to process large amount of complex information and write decisions without human intervention. Some of the popular examples of AI applications are chatbots, autonomous vehicles, space rovers, and the simulators for mathematical and scientific purposes. After that comes the machine learning. Machine learning is a subset of artificial intelligence and is mainly used to improve computer programs through experience and training on different models. There are three main methods of machine learning. First one is supervised learning, then we have unsupervised learning, and then comes the reinforcement learning. In supervised learning, the machine gets the input for which the output is already known. After the processing is complete, the algorithm compares the output produced from the original output and measures the degree of errors in it. After that comes unsupervised learning. In this case of unsupervised learning, the instructor has no output or historical labels for the input data. So the algorithm is expected to figure out the right path and extract the features from the given dataset. The goal is to allow the algorithm to search the data and some structure in it. Now, next one is reinforcement learning. In this method of learning, there are three components: the agent, environment, and actions. An agent is a decision maker, repeat, an agent is a decision maker whose goal is to choose the right actions and maximize the expected reward within a set time frame. Reinforcement learning is mainly used in robotics, where the machine learns about the environment through trial and error. Now, let's talk about deep learning as well. In machine learning, where the model tends to surrender to environmental changes, deep learning adapts to the changes by updating the models based on the constant feedback, facilitated by artificial neural networks that mimic the cognitive behavior of the human brain. Now that's the end of our answer for what is the difference between AI, ML and DL. Now moving forward, let's talk about the third question on our list, which is, how is overfitting avoided in neural networks? Now this is a very tricky question and it is most commonly asked in most of the interviews. Overfitting is one of the errors that you'll have to deal with while doing machine learning or deep learning projects. So how you guys can answer this question? Well, here is a sample answer. Overfitting is avoided in neural networks by making use of regularization techniques called dropout. By making use of the concept of dropouts, random neurons are dropped when the neural network is being trained to use the model so it doesn't overfit. If the dropout value is too low, it will have a minimal effect. If it is too high, the model will have difficulty in learning. The other methods for avoiding overfitting are feature selection, feature extraction, and regularization. By performing regularization, you can get your data regularized and there will be the application of penalty which will stop your model from overtraining or overdoing the learning phase. And same goes for feature extraction and feature selection. Feature selection ranks the features available inside your dataset, whereas feature extraction converts given set of features into the minimum number of factors or features by resembling the total variance represented in those large number of features. Alright. Now let's talk about the fourth question on our list, which is mention some of the algorithms used for hyperparameter optimization. Now there are many algorithms that are used for hyperparameter optimization, and the main three types are Bayesian optimization, grid search optimization, and random search optimization. Now after that, we have arrived to the fifth question on our list. How does face verification work? Now face verification is used by a lot of popular companies these days. Facebook is famous for its usage of deep face for its face verification needs. There are four main things you must consider when understanding how face verification works. First thing is input, then comes the process, then there is output, and then there is training data. Now input is basically the cluster of images, then the process is the main important part of our whole face detection scenario or face verification scenario. It detects the facial features, then there is then there is feature comparison going in the background, then key pattern representation and final image classification is also achieved in this step. After that comes the output, which is face representation, which is a result of multi-layer neural network. Then comes the training data, which involves the usage of thousands of millions of images. The implementation of face verification in Python requires special libraries such as Glob, NumPy, OpenCV, and face recognition. Among them, OpenCV is one of the most widely used libraries for computer vision and image processing. OpenCV is a beginner-friendly cross-platform Python library that is mainly used for real-time image and video processing applications. With OpenCV, you can create applications used for object detection, facial recognition, and object tracking. It can also be used to extract the facial features and identify unique patterns for face verification. Now, the sixth question we have on our list is what are dropouts? Dropout is a simple way to prevent a neural network from overfitting. It is the dropping out of some of the units in a neural network. It is similar to the natural reproduction process, where nature produces offsprings by combining distinct genes while dropping out the others, rather than strengthening the co-adapting of them. Now, the seventh question we have on our list is what are the hyperparameters of RNN? Basically, there are three hyperparameters out there when we talk about RNN. The first one is learning rate. The learning rate is how fast the network learns its parameters. Then comes the momentum. Momentum is a parameter that helps to come out of the local minima and smoothen the jumps while gradient descent. The third one is number of epochs. The number of times the entire training data is fed to the network, while training is referred to as the number of epochs. We increase the number of epochs until the validation accuracy starts decreasing, even if the training accuracy is increasing. The eighth question we have on our list is list different activation neurons or functions. Now there are many activation neurons and all of them are listed on our screen over here. The first one is linear neuron, then comes binary threshold neuron, then stochastic binary neuron, sigmoid neuron, tanh function, and ReLU function. All of these are different activations that are applied to transform the given input into the desired output. Now, the ninth question we have on our list is what is the bias variance trade-off? Now, this is very important question. For sure, many a times you'll come across this question in an interview setup. So basically guys, bias is error which is used to measure how much on average the predicted values may vary from the actual values. In case of high bias, the error occurs when we have an underperforming model. Now, variance is used to measure how the predictions made on the same observation differ from each other. A high variance model will overfit the dataset and perform badly on any observation. The 10th question we have is what are the components of relational evaluation techniques? The first one is data acquisition, then comes ground truth acquisition, cross validation technique, query type, scoring metrics, and significance test. The 11th question we have is, what is perceptron in machine learning? Perceptron is an algorithm that is able to simulate the ability of the human brain to understand and discard. It is used for the supervised classification of the input into one of the several possible non-binary outputs. That brings us to the 12th question, which is, what is a backpropagation algorithm? Backpropagation is a neural network algorithm that is mainly used to process noisy data and detect unrecognized patterns for better clarification. It's a full state algorithm and has an iterative nature. As an RNN algorithm, backpropagation has three layers: input, hidden, and output layer. The input layer receives the input values and constraints from the users or the outside environment. After that, the data goes into the hidden layer where the processing is done. At last, the processed data is transferred into some values or patterns that can be shared using the output layer. Before processing the data, the following values should be there with the algorithm. Dataset. The dataset which is going to be used for training model should be provided. Then the target attributes, the output values that an algorithm should achieve after processing the data should also be provided. The weights and bias should also be provided as well. Backpropagation is a simple model that follows a standard approach for training ML models. It doesn't require high computational performance and is widely used in speed recognition, image processing, and optical character recognition. Now that brings us to the 13th question on our list, which is, what is FOPL? First order predicate logic is a collection of formal systems where each statement is divided into a subject and a predicate. The predicate refers to only one subject and it can either modify or define the properties of the subject. The 14th question we have is, what is partial order planning? A problem has to be solved in sequential approach to attain a goal. The partial order plan specifies all action that need to be undertaken but specifies an order of the action only when required. Now, 15th question we have is, what is a Turing test? The Turing test is a method to test a machine's ability to match human level intelligence. A machine is used to challenge human intelligence, and when it passes the test, it is considered intelligent. Yet, a machine could be viewed as intelligent without sufficiently knowing how to mimic a human. The 16th question on our list is, differentiate between parametric and non-parametric models. Now, there are four factors that we can differentiate these two models on. The first one is features, algorithms, benefits, and limitations. When we talk about features, parametric model comes with a finite number of parameters to predict new data, whereas non-parametric model comes with unbounded number of parameters. Now, while we talk about algorithms, the parametric model uses logistic regression, linear discriminant analysis, perceptron, and naive Bayes. When we talk about non-parametric model, the k nearest neighbors, decision tree like CART and C4, 5 and support vector machines are used. The third differentiating factor is benefits. The parametric models are quite simple, fast, and uses less data space on your system. Whereas when we talk about non-parametric models, they are flexible, powerful when it comes to performance. Now, when we talk about limitations, the parametric model is constrained, it has limited complexity and poor fitting. When we talk about non-parametric models, it takes more data, it is slower, and there is possibility that there will come overfitting. Now that brings us to the 17th question on our list. How are route weights optimized to reduce the error in the model? Basically guys, weights in AI determine how much influence the input is going to have on the output. In neural networks, algorithms use weights to process the information and train the model. The output is expected to be the same as the target attributes. However, the output may have some errors. which need to be rectified to produce the exact output. For example, in the backpropagation algorithm in the backpropagation algorithm, when there is an error in the output, the algorithm will backpropagate to the hidden layer and reroute the weights to the optimized output. Now the 18th question we have is, what is naive Bayes? Naive Bayes machine learning algorithm is a powerful algorithm for predictive modeling. It is a set of algorithms with a common principle based on the Bayes theorem. The fundamental naive Bayes assumption is that each feature makes an independent and equal contribution to the outcome. Now, having said that, let's move to the 19th question, which is, what is the difference between strong artificial intelligence and weak artificial intelligence? So basically guys, weak AI has narrow applications with very limited scope, whereas strong AI will come with widely applied scope and it will have humongous impact on the way things work. For example, you can consider ChatGPT. After the incarnation of ChatGPT, the world has started talking all about AI and its immense power. Now, the another differentiating factor between weak AI and strong AI is that weak AI is only just good at some specific task, whereas strong AI has incredible human level intelligence. Alright, so that was it for the difference between strong AI and weak AI. Now the 20th question on our list is, mention some real-time applications of AI. Now the first one is robo-readers for grading. Many schools, colleges and institutions are now using AI applications to grade essay questions and assignments on massive open online courses. In the era of technology where education is rapidly shifting towards online learning, massive open online courses have become a new norm of education. Repeat, thousands of assignments and essay questions are submitted on these platforms on daily basis, and grading them by hand is next to impossible. Robo-readers are used to grade essay questions and assignments based on certain parameters acquired from huge data sets. Thousands of hand-scored essays were fed into the deep neural networks of these AI systems to pick up the features of good writing assignment. So the AI system uses previous results to evaluate the present data. Now, another real-time application of AI is online recommendation systems. Online recommendation systems study customer behavior by analyzing their keywords, websites, and the content they watch on the internet. From e-commerce to social media website, everyone is using these recommendation systems to provide a better customer experience. There are two ways to produce a recommendation list for a customer: collaborative and content-based filtering. In collaborative filtering, the system analyzes the past decisions made by the customer and suggests items that he or she might find interesting, whereas content-based filtering finds discrete characteristics of the product or service and suggests similar products and deals that might excite the user. The same process goes for social media apps and other websites. Other features are navigation and travel, fraud detection, and autonomous vehicle. Now, in this world of discoveries, autonomous vehicle is yet another discovery of this age. Human error is responsible for more than 90% of accidents happening on the road every year. A technical failure in vehicle, roads, and the other factors has little contribution towards the fatal accidents. Autonomous vehicle can reduce their fatal accidents by 90%, although self-driving systems require a person to supervise the action and take control of the vehicle in case of emergency. They prove to be very effective when driving on an open highway or parking the vehicle. Also, advancement in technology will further improve the ability to drive in complex situations using high-end AI models and sensors like LiDAR. The 21st question on our list is, what is ensemble learning? Ensemble learning is a computational technique in which classifiers or experts are strategically formed and combined. It is used to improve the classification, prediction, function approximation, etc. of a model. 22nd question on our list is, list the variants of RNN. Basically, there are four main variants of RNN, that is LSTM, GRU, end-to-end network and memory network. The 23rd question we have is what are the components of the generative adversarial network, that is GAN, and how do you deploy it? Basically, there are two main components of GAN, that is generator and discriminator, and there are 4 steps that you can perform to get it deployed. First thing is train the model, then validate and finalize the model, save the model and load the saved model for the next prediction. The 24th question on our list is what do you mean by TensorFlow cluster? TensorFlow cluster is a set of tasks that participate in the distributed execution of a TensorFlow graph. Each task is associated with a TensorFlow server which contains a master that can be used to create sessions and a worker that executes operations in the graph. A cluster can also be divided into one or more jobs where each job contains one or more tasks. The 25th question we have is what is deep learning? Now we have discussed this concept in the second question itself. But to define deep learning again, I'll say deep learning is a subset of machine learning which is used to create an artificial multi-layer neural network. It has self-learning capabilities based on previous instances and it provides high accuracy.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective as it is taught by IIT professors and industry experts.